Great. Thanks, everyone. It's funny to hear myself on the mic. It's so excited to have Land Model Working Group in person again after a 2-year vacation of sitting in my basement. And there's a few things that I kind of want to go over just for our kind of managing our first hybrid meeting. Some of that's for people that are online, and some of that's for those of us that are here. But before doing that, I wanted to share the NCAR Code of Conduct, and so this is something that we've all seen before. And I think one of my favorite, this is, I think, my favorite meeting of the year. It's fun to see all the young scientists that are coming in and sharing their ideas. And it's also, I think, a really nice time for our community to get to visit with each other and to kind of encourage the innovation and teamwork that I think the land model is one of the strengths of the Land Model Working Group. So just keep these in mind during the presentation, and I look forward to the conversations that we're all going to have. Paul and Nick have asked me to make a few comments. One is that the Mesa Lab seminar room is brand new. There's only been one giant coffee spill so far, and they'd like to minimize that. So as much as possible, leave your food and drink, definitely food and preferably drink outside, or if you do have an ability to mug, put a lid on it, please do. Another comment was that hopefully when we have discussion today, we want to have participation from online folks, participation from in the room. The easiest way to do that for in-room participation is with these little red lighted hockey puck mics, and they're really, really sensitive. So if you're in the corner having a conversation with your new best friend that you met at the working group meeting, those are going to get picked up, streamed to YouTube, and recorded for posterity. So for those of us in the room, it really helps if if you're not shuffling papers, if your phones are muted, you're not having side conversations, especially when those little lights are green, because during the Q&A, we'll be live and everyone can hear it. So I guess they're very sensitive, and it's also nice because then we don't have to pass the mic around for when people have questions. I'd also encourage you. Oftentimes I feel like one of the advantages of having online meetings is the chat, and there's oftentimes lots of interesting information that happens in the chat. So I've asked Daniel to be our chat moderator in the room, because we actually, when I'm presenting, we don't see the chat that's up here. And so if you want to join in companion mode on your computer, feel free to jump on, and that way if stuff is shared in the chat, if links to papers or other things that are interesting, you can still participate that way. People online obviously have that already. And for those of you that are presenting online, Nick might pull you off into a side room just to kind of get ready before your talk so he can check the audio levels, and so that when you present for remote presenters, that you sound good and look great when you're presenting for those of us that are here in the seminar room. I think that was the run through of stuff that we had to go through. The meeting's going to be tight on time. We had 52 people request talks, which is awesome, but we only planned for 2.5 days of speaking, so you can do the math. 52 talks in 2.5 days means we're going to be going pretty fast here. Also, I've already screwed up more than one thing on the schedule. One of those was that there's actually Iris got a half an hour for her talk today, which she doesn't need. And so we're going to actually have a little bit of time before the break today to have a little bit more discussion. So as much as we can, I'd like, the value of these meetings is the exchange. And so hopefully we'll have some more discussion that way. Hopefully I didn't make too many more mistakes. We'll see, I guess, going forward. So for both people online and in the room during the meeting, go ahead and raise your hand. That really helps kind of let everyone share the air and get to ask their questions. Again, for questions that are posed in the chat, Daniel, I've asked to go ahead and you can just read those out loud for the whole group. Again, use the chat even if you're in the room. Talks are only 10 minutes, and again, that's just to kind of get everyone through. And please provide feedback, both to the people that are presenting, but also for us, so that we, as we're moving forward, we can try to provide valuable hybrid meetings. I think that I'm so excited to see new faces here, people, graduate students who have been part of the working group since they started and not been able to come to Boulder. So it's awesome to see those of you that are here. But it's also awesome to have a big online community. So we had over 150 people register for the meeting, for just the land and biogeochemistry part of the meeting as of Saturday. And so having that online participation is something that we'll hopefully be able to keep supporting moving on. So please provide feedback as much as possible. And then during our talk, I'm going to kind of transition into updates for the land model working group. And I'll talk about wins, some of our plans for CTSM 6 development, and then also talk a little bit about the Slater Award. But before we kind of get started on that side, do folks either online or in the room have questions about what to expect moving forward in the next couple days? Yeah, Dave?
What's the LWMG, land working model?
Oh, man. I had to send you my talk ahead of time so you can proofread everything. Thanks. Others? Cool. Okay. So the LWMG, thanks. Got it? LWMG, got it. I got it there. Okay. So first thing I want to say is thank you. Like the last couple of years have been tough for, I think a big part of what NCAR does well and what the Land Model Working Group does probably as well or better than other working groups is have a really big community that's very active and very engaged. And that's hard to do when we can't get together. So I wanted to thank all of you, especially folks that came in from out of town, people that are continuing to engage online. I think it's really important that our communities stay vibrant and active. And I think the last couple of years of, again, doing that, at least for me, from my basement, has been challenging. So I really appreciate, I appreciate people staying engaged. I think it's really important that we've been able to do that. So, last year I think we had 230 people come to the working group meeting. This year, like I said, we've got over 150 that are already registered. So that kind of engagement is great. I was trying to think of other ways to measure engagement. So I went back and looked at the CLM5 overview paper. It already has 500 citations on it. It's only a couple, 2.5 years old. So there's lots of people that are using the tools that we develop, and I think that's exciting. And then more recently, the CTSM 5.1 tag is like a couple of years old, maybe, probably less than that. It already has nearly 120 tags on it. Of those, about 20 are scientific tags, and about half are from external collaborators. So there's a lot of activity and a lot happening in the working group, and that speaks both to the efforts of people in-house, especially the software engineering team, in terms of getting maintaining our science and enabling more of that to happen, but also external collaborators, and we'll hear a number of those presentations today. So of the presentations that are coming in the next couple of days, I think 32 of the 52 were from postdocs and graduate students. That's a big number, and that's awesome to have such a young, early career scientists that are participating in the working group. I think that's important for us. So thank you for those of you that are coming to present. I forgot I had all of these animations in there. So yeah, great number of talks, early career participants, Dave's paper, and then GitHub. The other thing I wanted to mention about GitHub, some of you might have noticed if you're on GitHub more often, we've enabled GitHub discussions. And so that's another platform to engage. And I think we're kind of trying to figure out what's the best way for people to communicate with us. Or should, people ask should I post to the bulletin board? Should I post a discussion? Should I file an issue? I think we're still trying to navigate that. If you have, if you find a bug, that's an issue, post it on GitHub as an issue. If you want to kind of engage in more of a science discussion, the discussions forum is probably the right way to do that on GitHub. And if you have more of a technical question, I'd argue that probably the bulletin board is the best way to do that. But it's also best to pick just one of those. So don't, spam all means of communications with your question. Pick one, and the liaison, the software engineers, other scientists will help kind of answer your questions. So yeah, I think I'd also like to reemphasize we're all sort of learning how to best communicate and enable open science, and so any suggestions that you have are great. Yeah.
Does everyone know the location of the bulletin board?
Oh yeah, so the mics aren't live, so I'll repeat the question. Daniel's asking if people know the location of the bulletin board. My guess is no, although it is on GitHub. And I don't even know the address. It's BB something. And
Ask CESM?
yeah. Discuss CESM. And it has changed. Well, the address hasn't changed, but it's sometimes a little harder to find when you're Googling things now that we've updated our websites or in the process of updating our websites. Yeah, Ryan.
So is there going to be any talk over the next couple of days about which of those forms is used for what purpose, or
So
we should ask you later?
yeah, so Ryan's question was how do we, will there be a discussion about, when do you post to the bulletin boards versus discussion versus filing issues? I think the best time to do that is over coffee. There's not something formal planned. And I think it's something that we'll try to work on more, but I think that helps. It's tricky too, also, with FATES also. FATES has all the similar types of resources, and so is it a FATES question or a CLM question? Sorry, I'll go back here. Any other questions or comments here? This is a thank you. So again, thank you. All right, I'll go ahead and move forward. So I wanted to have a couple science highlights. So this is a paper that EFON just published. It came out a couple weeks ago, maybe a week ago. That was in Water Resource Research. He'll talk about this, I guess, right after I'm done, so I'm not going to go into the details of the paper very much. But I thought it was a really neat example and that I wanted to highlight because it used both hill slope hydrology that Sean Swenson's been working on. It uses the PPE infrastructure that Katie and Daniel have been working on, and they'll talk about tomorrow during the seminar. And then EFON came up with this regionally calibrated high-resolution model focusing on a bunch of watersheds in Alaska for a convergence project that he's part of. So just a really nice example of some of the cool science that I think some of these new tools are able to allow us to start working on and questions that we can ask. Another paper kind of for science highlights that I wanted to give a shout out to, this actually came out a little while ago, uses the CLM urban model, which I think enables some really cool capabilities for, again, having kind of more actionable, people relevant, decision maker relevant science. Besides using the CLM urban model, which we'll hear, there's a whole session on the urban model coming up, I think, tomorrow. And some cool new developments with the urban model that are allowed. This paper didn't have it, but the new capabilities of the urban model are allowing for transient urban, so that urban regions can change with time. But this paper also used the CESM2 large ensembles, so it's shown here with the blue squiggles. And the solid line is the CESM2 large ensemble, which is a 100-member ensemble of CESM2 that was run out to 2100 under RCP 4.5. I'm sorry, RCP SSP 370. And it's a really neat resource to start looking at variability in the climate system. And here they used it to look at urban heat waves. And so, in addition, then they also took CMIP5 model output to look at urban heat wave intensity in a few regions. And so what's shown here is for the Great Lakes and for Southern Europe. But just another cool application of a whole bunch of tools coming together for some questions about urban heat islands. And then the last science highlight that I wanted to talk about was work from a paper that Donica will be submitting this week, next week, sometime soon, that uses the NCAR NEON system that we've been putting together. So NEON is the National Ecological Observatory Network that's housed here in Boulder, but has 47 terrestrial sites across the country. NEON is really interesting because they're collecting a whole bunch of data, but notably what we're mostly using is their meteorology and flux tower data to drive single point simulations that are configured for individual NEON sites. So we've come up with this whole workflow that works, it really facilitates running single point sites at NEON, but it also has kind of made both our single point and regional workflows easier to kind of manage and extend to new sites. So in particular, we're using NEON observations in this improved infrastructure, and then some of the new capabilities are these containerized and cloud versions of CTSM that really, you don't have to have Cheyenne access to run CTSM anymore. So you can run single point sites on your laptop. You can run also on clusters or in the cloud pretty seamlessly at this point. And we're kind of building this library of tutorials and visualizations to help get new people that are trying to learn the model up to speed quicker. and then also including new capabilities. So Tegan will talk tomorrow, I can't remember when your talk is, about some work that she's doing with expanded PRISM data sets. Adriana has added some new functionality to let us run fate simulations at the sites. And we'll have a workshop on this in May. That's another kind of a continuation of the NCAR Neon workshop that we've had pre-COVID. So there's some new faces on this screen. Brian Dobbins is, I'll talk about Brian in a minute, but he's working on the containerized part of this. Adriana's again doing fates, and Tegan is coming on board and doing some nice work, starting with the PRISM data. So other wins that I wanted to kind of highlight are that there have been a lot of changes in TSS and in CGD in general. And so Dave is now no longer section head. He's acting lab director for another month-ish. So JF, Jean-Francois, left in the fall. Dave stepped in as interim lab director, and we'll do that until March 3rd or so. In the meantime, Gordon's picture is up here because I don't know if it's a win for Gordon or not, but he's now acting section head until Dave comes back. Mariana Verenstein left also in the fall, and Brian Dobbins has stepped in to kind of lead the software engineering team in the short term. We had 2 babies in the section, so Adriana and Donica both had babies in October. And they're back now, but have been gone for a while, so we're really happy to have them back. And some cute kids that'll be running around the section in a little while. Megan took a job in Sizzle, so she's no longer in TSS and CGD anymore. It's a win for her because it's a great position and a good fit for her that keeps her local. And Tegan has stepped in at quarter time to do some of the Neon work that Megan was doing. So Tegan King is a new associate scientist in CGD and is helping out. So welcome to Tegan. Bill Sachs has moved half-time to ESMF. So he's still here, but not working with us as much. But it's another cool opportunity for Bill and something that he's been able to do. And then Keith is both a grandfather and in phased retirement. So he's only half-time now as liaison. And so we have active searches. One is a half-time liaison position that's posted and hopefully will get filled in the next weeks to month. And then the half-time of Bill's position will also hopefully be posted as a full-time software engineering position, maybe even as soon as this week, with that position hoping to be filled with a start date of May 15th. So there'll be some new faces, so lots of new changes, and then new faces. So Linnea, Gochang, Summer, and Katie are all postdocs that have started in the last less than weeks to year. So a bunch of new postdocs coming, and there will be some new people coming in. So the new half-time liaison and a new software engineer that'll be joining the team here at NCAR. Okay, switching gears, I want to talk a little bit about development timelines, and this is going to be a little bit compressed because I want to have time for discussion. One thing I didn't say is you're not supposed to touch the screen, and we also don't have a pointer, so I'm going to just gesture for those of you who are in the room. You can't see me online, so I apologize. But we're basically here, kind of in the middle of this open section between summer of 22, summer 23. And 2 important things have happened. So the PPE branch came off early on in CTSM 5.1 development and is continuing to work. We'll hear from Daniel and Katie about that. And then a new branch started maybe 6 months ago, which is the CTSM 5.2, where we're updating surface data sets. That's work that Sam Levis and Peter will talk about later on this morning. The plan generally is that when that 5.2 branch is done, which hopefully won't be too much longer, and it comes back into the trunk, we'll be on CTSM 5.3 then, so it will be kind of an answer changing tag. We'll be done with 5.1, switching to 5.3, and hopefully that happens sometime close enough for us to start what I'm calling CESM 2.x testing. So they've done some smoke tests with CAM and the full coupled model, just proving that they can continue to freeze the Labrador Sea, which they can. But moving forward, hopefully that stops. And this summer is kind of the timeline for when these new coupled model tests are going to be started. And then I don't know the timeline between summer CESM2X testing and when the CESM3 tag will be released. And the longer that window is, the more science we can cram in before that tag is done, is kind of what I'm imagining. So there's a lot of science that we're trying to fit into the model. This is kind of the development goals. They're up on GitHub. When you get a chance to look at this presentation, there's links that'll take you to all of these things. There's a ton that's going in here. I'm not going to go through all of them individually. We'll hear about almost all of these projects, I think, over the course of the next couple days. But I do want to note that most of these projects are relatively independent of one another. And some of them may come in and only kind of be able to be used in limited situations. So again, I think the timeline for how much of this gets into the main, CESM3 branch or CESM3 tag kind of depends on how much time we have. This is going to be hard. Like, there's a lot. This timeline is compressed. There's a lot we want to do. And so getting it all to happen is kind of given many of us at NCAR pause in terms of thinking about, like, okay, how do we get this done? We sort of have limited resources, limited software engineering capabilities. And so it sets up, potential conflicts or not, it's raised questions about how we're setting priorities and how we're kind of meeting the goals that we have, the science goals that we have with the resources that are available. So I don't want, I'm going to just pick on Eric because he's not here, but I don't want Eric to be the only one who's pushing this box across the finish line. There's a lot of us that are going to be working on this, and hopefully we can do it without grimacing as much as this cartoon person is. Okay, so when I think about what CESM is trying to do, and especially what the land model working group is trying to do, is kind of atmospheric coupling. That's the first thing that we do, is we couple the CAM. And then very quickly, where I like to think about is more on the land side of it, is thinking more about terrestrial impacts and mitigation. So at the land model summit this year, it was kind of described nicely. It's like, how do we grow the food? Where do we put the carbon? And how do we get enough water? So it's kind of like in those three things. And if you look at our strategic plan, that really nicely aligns with the kind of questions in terms of terrestrial impacts and mitigation that we're trying to think about. So that's in reality, like, from a pure science perspective, this is what we're trying to do. We're coupling to CAM and thinking about climate change impacts and mitigation strategies. In reality, though, there's actually a lot of maintenance costs that end up going into making CTSM work and CESM work. On top of the maintenance, then there's kind of this kind of burgeoning infrastructure that as we add more capabilities to the model, and, we want to run with Fates, and we want to run with Hillslope, and we want to have the crop model, and we want all those things to work together. It's a ton of infrastructure to try to get all of those pieces to play nicely with one another. So I think a combination of the maintenance and infrastructure that goes into just making this increasingly complex model system work is a challenge that we face. And then on top of it, there's continued demands from the broader CESM community in terms of updating to different BVOC schemes or changing dust emissions and things that maybe don't have a huge impact in terms of land model processes, but they're really important for the coupled model. Similarly, running in different configurations like paleo or any number of things from the CESM community that we need to be responsive to. So as a result, there's a lot that as a working group we're trying to maintain, and balancing all of these competing priorities is hard. I think it also was evident to those of us that got to go to the Land Model Summit this fall that as a community we're actually really good at it. I think I walked away from that group, which was being really proud of what we're doing here in the working group. But I also recognize that I think we can do better. So that's kind of what's prompting these discussions. I'm totally not going to have time to get into all of this in this setting. And so in terms of thinking about priorities, development priorities, I think we obviously need to pick things that are land model working group focus areas, but that's a relatively broad category of questions we're trying to address. In the process of going through these discussions, we discovered that expectations for new pull requests weren't ever clear, but basically that's like, you need to improve something in the model, you need to not break other stuff, and you need to document it, whether that's in a paper or in technical documentation. But that was never written down, so we've clarified that, and that's up on GitHub now. again, it still doesn't really help us in terms of thinking about practical considerations. And so this is where I think we can have some conversations, both in this session and at the breaks. I think it's easier for us as a software team to bring in external pull requests that are more mature and easier to integrate. That said, we recognize that getting external pull requests into the code takes help, and so we're here to kind of help you with that. Those pull requests that offer broader benefits to the CTSM and CESM communities are easier to prioritize. And then also pull requests that augment land model working group resources. And so, anytime that, especially it seems like we're always short on software engineering support, as much as university collaborators can help us out by, providing some additional resources, especially in terms of software engineering time, that really does help us out. Timing and availability of students is really important. And so if you get to come and visit NCAR for a month or a summer or semester, whatever it is, that's a really great time for us to work with you. And so we recognize that, the timing of when you're going to graduate or when you're finishing your postdoc is important. And as much as possible, we'll try to, use that time together as much as possible. But the other thing that it really clarifies is that we need frequent communication with the CTSM team and the land model working group co-chairs. So we're going to hear some really great presentations today about new science that's coming. And as much as possible, we want to continue those conversations moving forward. I think that's probably about as much time as I have to talk about that. And then I guess, so the other thing that we've tried to do is take this huge list of things that we want to accomplish and put them, oh man, who put all these animations in here? Put them into a project board so you can kind of check on our progress. You can see where your favorite thing lies, and trying to prioritize, like, okay, what stuff that is easy to move, like easy to bring onto the trunk, and what stuff that's going to be later on. None of these cards are set in stone. You can move them around really easily, and so if there's particular developments that are critical for your science that you need help moving forward, please let us know about that. And as a team, we're trying to visit these more often to make sure that the work that we're doing is aligning with the goals of the working group. Okay, lastly, I want to talk a little bit about the Slater Award. And for those of you who knew Drew, he was a key member of the working group community who was really incredibly dedicated and brought a lot of, I can't think of a better word, but joy to the research that he did, and not only to the research that he did, but also the fun that he had. And he was infectious. He shared that with everyone in the room. And so winners of the Slater Award also make kind of similar meaningful contributions to the working group. And those could include creative applications of the model, significant model development activities, identifying things that we're not doing well or gaps, and then also having a high level of engagement with the working group. So in the past, the Slater Award has been given kind of post hoc. Everyone gives their presentations, and then after the fact, a distinguished committee of people gets together and figures out like who made the best contributions this year. We're trying to reshape that a little bit. So at the end of the meeting, actually this year, we're hoping to announce the winners so that so that we get to celebrate you at the meeting. And then moving forward, it might even be something that we announce at the beginning of the meeting for people that are, I'm not exactly sure where we're going in a year's time, but hope that's something that we've talked about, is being able to kind of celebrate people that are doing a great job and recognize those accomplishments while we're here together as opposed to after the fact. If you look at who's won this in the past, it was fun to go through and put together this list. It's a pretty distinguished list of contributors, many of who are still in the room. So thank you for sticking with us. And like I said, the winners from this year hopefully will be announced, winner or winners. There's nothing, we've done 2 every year, so I guess that makes it a pattern. But we try to recognize, 1 or 2 people that are doing a really exceptional job. So so hopefully some people that are in the room or online that'll be contributing will be added to this list soon. I don't know how I'm doing on time, but I think it's probably, I'm finished without any time for questions. That is awful. We do have a little bit of time because Yiddish doesn't need a half an hour. So in the interest of time, maybe I'll just ask if Yifan, if you want to come down. Is that, and while we're switching? Yeah. Oh, the other thing I was told. Scratching sound that you just heard. Yeah, you're actually here. Just take this one, it's easier. People that are using the mic, don't put this thing in your pocket with your phone because it'll pick up weird static.
Okay.
Yeah, in other ways. And then it's off right now, but you switch it on the top there.
Oh, okay. Cool. I can just hold it in my hand, right?
Yeah, that's
Okay.
fine. Yeah. Let's see, oops. What's the word, Paul?
They're in the Finder window. They're under down in the downloaded.
Oh, you already got them.
Yep.
Cool. Thanks.
Cool. Thanks, everyone. It's great to be here. To be the first speaker, I'm a little bit nervous. So today I'm going to talk about the climate impacts on Alaska and Yukon hydrometeorology, and it's a modeling effort that is guided by the indigenous knowledge. And I want to shout out to all my collaborators, and a lot of them are sitting here in the room with us today. So this is an SF. This is part of an SF navigating the new Arctic project, where we closely collaborated with indigenous people to investigate the climate impacts on Alaskan and Yukon rivers, fish, and communities. And under climate change, the Arctic is rapidly changing, such as increasing air temperature and precipitation, decreasing sea ice, and changes in seasonal snowpack. And all these changes lead to the change in the freshwater system in Alaska, which the indigenous Alaskans heavily rely on for subsistence fishing as well as transportation. So the goal of this project is to strengthen the understanding of terrestrial hydrological changes in the Arctic and the potential impacts on the rivers, fish, and indigenous communities, as the goal is tangible to the daily lives of indigenous people. So it is critical to involve them in the research process. So that's why we formed a project-specific Indigenous Advisory Council consisting of 10 members, as you can see from the right top corner. So the Indigenous Advisory Council actually helps the project investigators to make decisions about research designs, deliverables, and analysis. And also their participation also trying to make sure that indigenous knowledge and perspectives are included, protected, and valued in the project. So here I visualized collaborative mechanisms that support knowledge co-production in this study, especially how we use indigenous knowledge to guide the regional climate modeling, and hope that the climate information we provided can not only be useful, but also usable to the policy making or decision making. So this is a fairly complicated diagram. I want to highlight two things. The first, if you see the yellow arrow here, the knowledge co-production involves not only the indigenous community and climate and earth scientists, but also social scientists. And I especially want to highlight the long-term connections between the social scientists and the indigenous community, which the scope of the connection goes way beyond the project level collaborations that we have with the indigenous community. And this lies the foundation for the collaboration in this study. And the second one is we actually designed a climate information survey to collecting information from decision-making authorities to inform the regional climate modeling. But not all, a lot of the modeling decisions in the regional climate modeling is not easy to understand because it requires domain knowledge. So that's why the social scientists and the Indigenous Advisory Council actually co-produce the climate information survey from the help of the climate scientists, and to make sure that the climate information survey is relatable to the indigenous people, but also can provide useful information for climate scientists. So in this study, we are trying to provide a high-resolution, high-fidelity regional climate modeling, and for the Alaska and Yukon River Basin. The first reason for the high resolution in this study is because through our communication with indigenous people, because the most useful information for them is sub-watershed or high-resolution stream flow or other sensible weather variables such as like 2-meter air temperatures. And the other reason is for the from the scientific perspective is we can see in the Corsair model mountain ranges are simply high terrains with little realistic details. So the high resolution model being used in this study can more faithfully represent the ridge valley patterns, as you can see from the maps in the right side. And using high resolution topography can also increase the fidelity of the precipitation distribution as well as air temperature distribution. So, however, increasing the spatial resolution inevitably increases the computational cost, which can reduce the capability of doing the uncertainty quantification, but we still prioritize using that because it fits better with indigenous knowledge and co-production model, and the better process representation can improve our confidence in the projection. So I want to highlight, so in this study, we're using a model framework that is specifically designed for the Arctic region called the Regional Arctic Systems Model. And this is a fully coupled land atmosphere, sea ice, ocean, and river routing model. In this study, we mostly focused on the coupled land atmosphere interaction. So we use prescribed sea surface temperature and sea ice data from ERA5. And we use offline river routing model, means route. I want to highlight in this study, we specifically replace the land model to CTSM because CTSM has great process representations that can help us capture the hydrological cycles in the cold regions such as Alaska. And I want to highlight some of the results here. The first is to increase the land process fidelity for Alaska. We actually developed an optimization workflow for CTSM, which we just mentioned is recently published in WRR. And that's a regional application specifically focused on river flow and snow. And you can see the optimization actually generally improves the hydrological simulations in Alaska, and especially greatly reduce the summer, the late spring and early summer flow biases for the Yukon River at the Yukon River pilot station, which is the largest USGS station in Alaska. And we actually also just finished the high resolution coupled WRF and CTSM simulations for Alaska. And you can see the bottom two plots the simulated climatology from the model. And the left plot is mean annual precipitation, and the right plot is mean annual air temperature. And you can see the clear temperature gradients from the south to north, and as well as the mountain valley patterns and topographic impacts on the precipitation and air temperature distribution. We also, like, except for the basic evaluations, we also do comprehensive evaluations of terrestrial hydrology as well as hydrometeorology. We also evaluate evaporation precipitation ratio, snow fraction, terrestrial snow, and stream flow. So, what time is it? Okay. Okay. So here's the last slides. And in this study, we are trying to also evaluate the climate impacts to the hydrological cycles, and we plan to use a method called pseudo-global warming method, which is, this method is trying to impose the climate signal from the global climate models to the historical climate simulation. And there's two important modeling decisions that we need to make. The first is what future period that they are interested in, and the second is what global climate model to use. The first one, the future periods of interest, is easy to understand, so we can directly ask the indigenous people in the surveys that we send them. However, like, the selection of the global climate models is not directly easy to understand, as I said before, because those selection requires you have domain knowledge about what's climate modeling and stuff. So in this study, instead of directly asking them to make the selection, we ask them some more relatable questions, such as their event of concerns. An example would be what seasons of like air temperature, precipitation changes concerns you the most, and some other questions. And then we make corresponding meteorological variables and then do the GCM selections. So I want to highlight that this kind of questions may not like have a big impact from the science perspective, but it greatly affects the usability of the information that we provide to them. So main takeaways. The first is we actively engage indigenous participation in the project to ensure that indigenous knowledge is included, valued, and protected. And the second is we developed an optimization workflow for CTSM, and GitHub page is under construction, so please feel free to contact me if you are interested. The third is we will provide the coupled WRF CTSM climate hydrology data sets to the community with variables available from sub-daily to monthly for the past 30 years. And the next step is we will kick off the PGW rounds this month, and there's more high-resolution regional rounds because we will awarded the ASD program for the launching of the retro edge high-performance computer. Thanks.
Questions for Yifan, but I'm going to kick you out of here. Yes. I had a question. What's PGW?
Pursuit of global warming.
Oh, yeah.
Sorry.
That's fine. Awesome. Yeah, go ahead. Yeah.
So you've had great talk and great project. I was just wondering, like, you're saying that you're providing WRF CTSM data to the communities. Do they have the capacity to use that data, or how do you go about building capacity within the community?
So we will not directly provide the WRF CTSM data to them because that's really hard to use. And this is actually the next step that we are going to do is we will work with the social scientists and also the indigenous advisory councils to decide what kind of data that they can use, because we have like council members directly works for the tribes. So they can tell us, we need to discuss with them because they also don't know what the model result looks like, and so there need to be some guidance from us and make sure that we are not passing some wrong information to them. Yeah, Dave.
I guess I had a similar kind of question, which is what is that engagement going to look like? Obviously, they're not going to be plotting up WRF output, right? So you planning like a workshop, or is it like, you imagine this needs to be sustained? Like it's like they have a comment, you do some work, they have another comment, you do some work. So I could imagine like a series of meetings, or and then it could go beyond the end of the project. So I guess I'm trying to envision how that interaction is going to work.
Yeah, so basically now we have this, by we is like the social scientist project lead is having like monthly or bi-monthly meetings with them. And now, so last December, we actually have an Arctic River Summit where researchers and a lot of like indigenous people and our indigenous advisory councils actually get together to, so mostly it's like we listen to them and also like to listen to them and what they need. And there is a process that, which there is a discussion has already been undergoing is we, not only we are providing the information from this survey, but also we identified a lot of questions that we can follow up with them and to see whether there's more funding opportunities, because we want to keep this a long-term kind of collaborations going on.
Probably move on.
Yeah.
Thank you.
Thank you.
Are you gonna be around this afternoon, or do you have to go to see?
I will be here this afternoon.
Okay, good. Our next, I guess I'll use that real quick. So our next presenter is Iris.
Oh,
Oh yeah,
yeah.
you're there. Yes.
I'm there.
Can you see your slides?
Yes, I can see them.
And I'm advancing them for you. Is that how it's gonna work?
Yeah, please.
Okay, awesome. Go for it.
Thank you. Yeah, that was the only option. So I'm Iris, and I'm a PhD student at the University of Oslo and at CICERO Center for International Climate Research in Norway. And I will talk about the preliminary results from the evaluation of WRF CTSM with the hill slope hydrology configuration. You can move on, please. But first, I would like to acknowledge all the help and support that I received from NCAR scientists and also software engineers who have helped me in, you can click the next one, in setting up WRF CTSM on the Norwegian supercomputer and also setting up WRF CTSM that uses hill slope hydrology configurations. So these efforts have been done for the first time. Yeah, we can move on. And I would like to just first say what are the main differences between using the hill slope hydrology with WRF CTSM and the default WRF CTSM. So in hill slope hydrology, each of the grid cells can be separated into hill slope columns, and each of those columns have different insulation, different water capacity. So if you click the next one, we can see that on the hill slopes and on different columns, we have different LAI and snowpack variation or ground temperature, for instance. And then that all varies with different slopes and aspects. So if you click the next one, this is the setup that we are using. So it's 2 columns per hill slope, so a lowland and an upland, and 8 columns in total per grid cell, so for each of those 4 aspects. And we can move on. So further about the setup, this is the domain of analysis. It's in Northern Europe on a 10.5 kilometer resolution, and it includes Norway, Sweden, and Finland. So I will be showing the results for the year 2018, and the spin-up period that is used here is 16 years. So 16 years of WRF CTSM spin-up is used for the default option, and for the hill slope hydrology, the last 2 years are using the hill slope hydrology configuration. So in the next slide, we can see that spin-up has a very strong role in how these 2 configurations are compared. So I'm here showing the 2-meter temperature results for the spring and summer of 2018. And with only using 3-month-long spin-up in the first row, we see that hill slope hydrology option is showing a slight cooling in all months. But if including 16 years of spin-up in summer, the difference is more pronounced, and we have even some warming effect when including the hill slope. And in the next slide, please, we can see the overview of all considered variables in this study so far. And first, the panels showing the 2-meter air temperature and surface temperature. So these are the averages of the entire region for the year 2018, and the effect on temperature is small, but there is an increase when using the hill slope option. And when considering the sensible and latent heat, especially sensible, we see that hill slope hydrology has a much higher values. And then soil moisture and total water storage throughout the entire year, we see an increase in when using the hill slope hydrology option. And in the lowermost row are the snow variables, and during winter time, hill slope hydrology again has higher values. And please move to the next one slide. Thank you. And this is the summary of all the differences that we have seen so far, just expressed in a table. And the intensity of colors shows the strength of the increase when we have, or decrease when using the hill slope hydrology option. So what could be seen is that some of the variables listed here, starting from latent heat and going to the bottom, these are more affected by directly by water availability. So throughout the entire year, they seem to have higher amount, higher values than default WARP CTSM option. And then we can move to the next slide. So where I will be focusing on the 3 variables that are validated against the observational datasets. So starting with 2-meter temperature, here I'm showing the absolute differences and showing the 2 months for spring and 2 months for summer. This is EOBS dataset, the graded observational dataset on the same spatial resolution as the model run. And we see that the hill slope option has a stronger cooling effect in spring and a stronger warming effect in summer. But if we include another observational dataset, if you can click one more, please. This is Nordic graded climate dataset, which is on 1 kilometer resolution. So here, the hill slope results seem to have so the spatial pattern is very similar, but the hill slope results seem to have in 3 out of 4 months better fit with the observational dataset, which was not the case for EOBS, for instance. So there is some uncertainty in the observational datasets themselves. And we can move to the next variable, which is surface soil moisture. So comparison with a GLEAM satellite-based dataset, and in both cases, WARP CTSM and also hill slope hydrology option included have the wetter spring and summer months than the observations. And if you click one more, we will see another comparison dataset, which is ESA CCI, and the spatial pattern here is similar. But in this case, WARP CTSM in the default mode seems to have a slightly better fit with the observations. And then the last variable in the next slide is the total water storage. And I'm using Gray's dataset that is just showing the non-mountainous area. And here is the comparison with WARP CTSM in a default mode, and we see that it's slightly wetter after 16 years of spin-up than the observational dataset. And if you click the 3 more times, we will see that in the panel to the right, these are the absolute values for the year 2018, where we see that the hill slope option has more water in the entire soil column than default mode. And this is similar if we consider the entire area, which is in the lower panel, the figure that I showed before. So these differences are the most prominent in the lowland area, which is here corresponding to the more blue area in the figure to the left. So that is where the difference between hill slope and WARP CTSM is the strongest, and where WARP CTSM with the hill slope option is wetter. And then the next slide is just showing the main points. because the role of the spin-up is crucial, and in our study and also based on some previous work, we found out that at least 8 years are needed for the soil to reach the soil moisture and the temperature equilibrium, and that the differences in model configurations are larger for specific areas than looking at the regional mean itself, and that most of the variables are higher when have higher values when the hill slope hydrology configuration is used. But there is also an uncertainty in the observational data set, and the next work will include more years and more variables, and this will be presented at EGU in April in case any of you will be there. So thank you very much. That is all from my side.
Great.
Yeah, you can just click one more time. That is just a thank you slide. Yeah, perfect.
Can they hear me without the mic?
I think so, yeah, the
Okay,
mic there, you're on.
Quick question. With the hill slope model, did it improve the simulation of those variables, and did you figure out why is it better as compared to the normal configuration?
So not in all comparisons, it is a better fit with the observations. And it seems like based on this limited analysis that I have here, that when including the higher resolution observational data set, then the hill slope has a better correspondence with observations. So it's still uncertain, and I would like to work on snow and evapotranspiration and runoff, because that's where the most work has been done so far with the hill slope hydrology option.
Cesar, online, can you unmute yourself? We can't hear Cesar in the room. I don't know if you can hear him online.
I cannot hear anything.
Oh, you can't hear anything either.
No.
Cesar, I don't know if you can put your question in the chat maybe, or try it again.
No, sorry, it
Oh,
was
there.
in.
Now we hear you.
Sorry.
Yeah, go ahead.
I think it wasn't a question.
Oh, not a
He was
question?
He was trying to clap.
Oh, sorry.
My guess is.
Okay, great.
But I have a,
Okay, Dave, go ahead.
or actually, Dan, will you? I guess, you know, it's a comment as much as anything with hill slope, I think, and we're gonna see the same thing with fades, is it's actually much harder to analyze, I think, with observations. So I'm wondering, you know, are those observations actually able to capture the really fine scale stuff that the hill slope is capturing to make it a reasonable comparison? So, you know, hill slope is not necessarily designed to make the mean state better, maybe it would be, but it's designed to capture the variability better within a grid cell. So I think we have to like evolve our evaluation methods to be a little bit more subtle, which is really challenging.
Yes, exactly. And I think that point scale observations should maybe be prioritized when comparing with hill slope and seeing its model skill.
Gretchen and then Daniel.
In terms of the model comparison, do we understand the mechanisms for why it seemed like for all of the components of the surface energy balance, the hill slope hydrology model was higher? You know, like mechanistically, does that make sense based on, you know, what we know about how the model runs? As a way of sort of vicariously understanding if the performance is getting better if we don't trust the comparison against obs?
Yeah, I think that hill slope hydrology retains more water within the soil, and that's why we see that increase in those variables, especially who are more water directly related. But then the second level comes the effect of the surface temperature, and yeah, that's where I think we are now at, and then we will have to look further for some other variables and years.
Yeah, that was my question too. Okay. Awesome.
This related question, since you did see these big differences in sensible latent heat flux, there seemed to be very small difference in temperature. Why is that?
Yeah, I'm not quite sure. I would say that this temperature comes, as I mentioned earlier, like in the second level after the fluxes. There is a change in fluxes first, and then we see it in temperature change afterwards. So that is my explanations at the moment, but I'm still not sure exactly.
Jonas, thank you. It's awesome.
Thank you.
At least on my end, this remote presentation looks great. So you were our guinea pig. You did a great job. Gochang is next. He'll be talking about improving hydrological performances of CESM with parameter estimation.
Okay, yeah, this works. Good morning, everyone. I'm Guo Qiangtang from CGDTSS NCAR. And today I will present our ongoing work about improve the hydrological performance of CTSM. And first, I'd like to thank the contributions from Andy and Sean. So in our research, we often use a model to represent the real-world hydrology. And model representations require choices of model structure and the physics. However, these choices and input specifications are inherently uncertain. This is a long-standing challenge. This picture shows a diagram of hydrological modeling. A model is often affected by many sources of uncertainties, including the input uncertainties, model structure and parameterization uncertainties, and even the calibration data uncertainty. And different communities approach this challenge in different ways. The Earth system modeling community advances model fidelity through improved estimation and refined parameterization and more complex process representation. The philosophy is that we can eventually represent everything through better observations and physics improvement. On the other hand, the applied hydrology modeling community tried to advance model performance and emphasize more on the optimization of model parameters and the structure, among other influencing factors. So the philosophy is that we will never represent everything, but can at least optimize what we don't know. And the presentation and this project brings an applied hydrology mindset to ESM development context. So many new water security related projects are exploring the use of CTSM in many applications, such as the climate change studies and flood, drought, and hydraulic prediction applications. The presentation will describe initial work supporting a climate change project sponsored by USACE. The overarching goal is to develop land models that can represent current hydrology and climate change impacts on hydrology. The immediate goal is to develop CTSM configurations and parameter sets that perform well for hydrology. And the presentation will show the first steps to use common parameter estimation approaches from applied hydrological modeling for CTSM and to develop a large sample small watershed CTSM implementation. In the past decades, many algorithms and much theory are developed for hydrological model parameter estimation. There are actually multiple packages for parameter sensitivity assessment and optimization. Some examples include Dakota, Ostrich, SpotPY, and the PEST. And there are also many individual researchers' methods. For example, Ifan's work calibrated CTSM model in Alaska and the Yukon River basins. That study used the MO-SMO algorithm, and the mean scale of daily stream flow improves after the calibration. And the presentation will present a preliminary version of the CTSM parameter optimization workflow. And before the workflow really starts, we need to prepare the data. And of course, that's the essential part for every research work. And this part actually requires a lot of time input because of the different formats from different data sources. The main workflow is composed of 4 steps. First is building the model, and then creating the calibration setting, and then forcing subsetting, and the final step is model spin up. The workflow is written in Python with one configuration file controlling everything. So for practical application, you just need to prepare one configuration file and the workflow can be automatically completed, generating everything. And of course, you need to submit the calibration task by yourself. And in the following slides, I will introduce a few components of the workflow. So for the parameter list, it is a CSV file containing the parameters you want to calibrate. So for example, in this table, the parameters are selected based on the PPE parameter table and the manual identification of key hydrological processes. But in reality, you can put any parameters in this table. And the file has some features. So for example, it supports calibration of parameters in the parameter netcdf file, surface data netcdf file, and name list text file. And it supports multiplicative and additive factor calibration, and it also supports binding variable parameter calibration. And for the calibration setting part, we currently use the ostrich package. The ostrich package provides many algorithms for parameter optimization. And in this work, we use the dynamically dimensioned search algorithm. The DDS algorithm is simple, but it's useful particularly when the iterations are limited. And this slide shows the forcing subsetting part. Forcing subsetting is important for small watershed simulation because it can greatly reduce the time cost by forcing reading and processing. Particularly for calibration, we need to run the model many times, and we don't want to want to process the forcing from a continental or global data set every time. And for the workflow, it will automatically subset the forcing using the mesh filer of the domain. And it also includes a time merging step. So the time merging step will merge the monthly forcing filers to a target time step defined by the users. This is useful because it can enable easier file management, and it can avoid excess file numbers because in some HPC systems, there is a limit of file numbers. And for this work, we use the large sample watershed modeling to support learning and development. Large sample watershed modeling has many advantages, like the improved accuracy, statistical robustness, regional variations, improved understanding, and better representation. So the large sample hydrology kind of reach the balance between the depth and breadth. We use the CAMOS dataset for this experiment. The CAMOS dataset is widely used in hydrology research to develop and evaluate hydrological models, variability, and predictability. It contains 671 basins in the United States, covering different ecoregions and climate regions. And the model has been widely used in many research, including the machine learning modeling in recent years. And the dataset was originally developed by NCAR. In the future, we may extend to other datasets in the global scale, but anyway, we will start with the CAMOS. And for this experiment, we randomly selected 10% of the CAMOS basins to test the workflow because the workflow is still under development and we don't want to spend too much computation resources when the workflow is unsure. And each basin is simplified as a mesh grid. We ignore the spatial variability. This may cause some loss of the fidelity and accuracy, but this will enable large sample modeling. And all the basins will be included in the future studies. And for the calibration, we use a modified Kling-Gupta efficiency of daily stream flow as the objection function. So 1 is the best value. For the calibration, each basin only has about like 40 iterations. Normally for model calibration, we need about hundreds of iterations or more to achieve ideal calibration performance. Despite the limited calibration, we can still see the notable improvement of the simulated stream for example, the modified KGE increases in 66 out of the 67 basins, and the median Kg increases from about 0 to 0.17. And if we look at the mean improvement of the modified Kg, it's even larger. It's about like 0.53. This slide shows two examples of the calibrated basins. So the Kg metric, of course, is improved. And if we look at the simulated stream flow curves, they are improved at the daily and the monthly scale. So for example, if we look at the first basin, the original parameters have meaning 0 stream flow values in a year, where for the calibrated parameters, the simulated curve can match the observation better. It can catch the no flow, and probably due to the base flow parameters. So this is a summary and next steps slide. So this presentation shows a streamlined CTSM calibration workflow and hydrology test bed. So this actually will support a larger project to assess the robustness of different hydrological model configurations. And this implementation, CHEMOS and the CTSM implementation offers a useful and efficient test bed for evaluating and improving CTSM model configurations and the parameter estimation. And our next steps will include actually a lot of work. So for example, we will need to improve the parameter, improving the parallel computation. We will need to include multi-objective calibration, and we will need to refine the parameters. There are also many other aspects will be coming in the future. And finally, we will also assess different structural configuration options and the hill slope parameterization. So currently we use the standard version, but the hill slope will definitely benefit the stream flow simulation, particularly when we look at the daily scale with more variability. So that's all the presentation. Thank you.
Questions? Katie?
Yeah, thanks for that talk. That was great. I think we should definitely chat about infrastructure and methods because there's a lot of overlap with our global CLM parameter estimation work. I guess I had a specific question on how you determine the number of iterations when you showed the map across CONUS and you had different colors like 30 to 40. So how did you pick that number that varied across the different
You mean
locations?
the basin selection?
I think so, or it was like the number of iterations that you ran for each.
Yeah, that's a iteration. So we assign one CPU and 12 hours. For every basin, and so but some basins have more iterations and some basins have fewer. So there is a pattern that high latitude basins have fewer more iterations. So probably that model is faster in high latitudes, but the sample is still limited. So I don't think I can conclude now, but in the future we can see more clear pattern after involving all CHEMOS basins and longer calibration.
I'm not sure exactly how to ask this question, but, how would you compare the ability to, calibrate CTSM to improve stream flow with whatever, a leading hydrological model? Is it equivalent, easier, harder, not as good? Is there any way to sort of characterize that, or?
I did calibrate sophisticated hydrological model before. It's called SUMA. So I think actually it's quite different. So because CTSM is very sophisticated and is well structured. So for many hydrological models, we just need to call an executable program to run the model. But for CTSM, it has its own structure and its own model building processes. But overall, I think it doesn't bring too much complexity here. And since the structure is clear, so in the workflow, I try to make it a modularized type. So I can actually extract useful information from the built CTSM case. So I don't need to like read from configuration every time. So I think that's a good point of CTSM. So everything is contained in the case. So just need to give me the path of the case. I can get everything of the model, the output, the parameter, and the forcing. Everything is contained there. So that makes things actually convenient.
I could just add to that. I think, having spent a lot of time calibrating models, the biggest thing that affects your ability to calibrate the model is kind of the speed of the run. If you are like these runs are 30 to 40 iterations, and typically we'd want to see a few hundred or more. And because that just allows you to explore the parameter space that much deeper. And so as one of the objectives will be trying to find a way to run it faster and more efficiently so that we can do that. And I think it will calibrate similarly to other models.
Probably move on. I think Ahmed's online. Is that right?
Yeah, can you hear me?
Yeah.
Yeah, so good morning, everybody.
Hang on. Ahmed, I'm going to interrupt just for a minute. You're a little quiet. I don't know if you guys can turn up the volume or.
Can you hear me okay now? Fine.
Yeah, that seems okay.
So, yeah, my name is Ahmed Cook. I am a PhD student at Michigan State University. My advisor is Dr. Yadi Pukrel, and I would like to give a shout out to our collaborators and acknowledge funding from the National Science Foundation. Can you go to the next slide, please?
Oh,
yeah. Sorry.
Oh, I shouldn't be steering this. Or I guess I'll do this one too. Sorry, Ahmed.
Yes. So here I'm showing two studies from Millen to Millennium, which motivated my work. So these studies show a widespread in model runoff sensitivities to precipitation and temperature, both models that are coupled and models that are run offline. Next. So our objective, since these models have high biases compared to observations, we ask what are the most sensitive parameters for runoff sensitivity in CLM. And next, and we ask how parameter values affect model sensitivity. Next slide, please. So this study focuses on 3 basins in the Colorado headwater region. Next, just go 4 times, please. Yeah, and these basins were considered in many climate change studies, and here we are using the CESM 5.1 development version with satellite technology and global surface data set, and all model runs which performed here are over 60 years period from 1951 to 2010, and we use precipitation temperature forcing from ESNA, while other meteorological radiation forcing from GSPW3. And finally, we calculate or estimate the temperature and precipitation sensitivities for runoff throughout regression with a correction for storage. Next slide, please. So, since the model has many parameters, we follow recent work by Shen, Yifan, and Dagon, and use the perturb parameter symbol to do pre-screening of these parameters according to 6 metrics that deal with snow and runoff. And we select 37 formative parameters for hydrology in southwestern US. Next slide, please. Next, please. So using these 37 parameters, we generate the latent Herbicube sample of 200 and run the model a sample for 60 years. And here I'm showing the distribution of runoff sensitivities from perturbing these 37 parameters over the 3 basins. And we can make 2 observations here. First, using the baseline parameter set from CLM does under or overestimates these sensitivity to temperature, which we call beta. Next, please. And the second observation is uncertainty in parameters can influence sensitivity, which ranges between -21 and -6, decline in percentage of runoff per increase in degrees Celsius. And this uncertainty is much higher than the one reported in the literature between different land models. Next, please. So we also here we are showing the bias in the sensitivity of runoff in the y-axis compared to errors by calculating the RMSE to compared to USGS observations in these basins. We can see like that a range of parameter sets can have a similar RMSE, but highly different biases in runoff sensitivities. And this leads to the conclusion that reducing errors in runoff will not necessarily improve runoff sensitivities of the model. Next, please. And this also affirms conclusion of previous studies. Next, please. Next. So we have these 37 parameters, and we ask which of these 37 are the most sensitive. And for that, we are using the surrogate model approach proposed by EFA to isolate the influence of each parameter on the sensitivity. So in this plot, I'm showing the contribution of each parameter to the precipitation sensitivity of runoff and the temperature sensitivity. And here we are using different sample size in the x-axis to ensure that the ranking of parameters stabilizes. And by 200 at the 200 sample, we can clearly see that a group of parameters are very sensitive compared to the other. And next, please. Next. So we use these. So we reduce these parameters and only focus on these texts and use a much more detailed approach for sensitivity analysis, the delta approach. And here I'm showing the sensitivity of each parameter in the x-axis compared to biases in data, which is the sensitivity of runoff to temperature. And we make two observations here. In regions where the model underestimates the sensitivity to temperature, we see that the K factor for saturated area fraction and the midlane intercept are very important, while in areas where the model overestimates the sensitivity to temperature, parameters that control the surface resistance to solid separation are very important. Next, please. Next. So we can even go deeper and inspect these regions, and we can see like in regions where beta is underestimated, we see flashier total runoff, which is due to an enhanced surface runoff, decreasing infiltration, and decreasing subsurface runoff and evapotranspiration. We also see that higher stomata resistance can lead to less transpiration, especially during the melting season, summer and fall. And in regions where beta is underestimated, the surface resistance parameters are very important and can lead to less surface resistant evaporation, more soil evaporation, and which inhibits subsurface runoff. Next, please. And finally, the soil parameters like the adjustment factor for porosity have direct effect on latency, especially soil evaporation and total runoff, and can either increase or decrease evaporation surface runoff, which leads to biases and the sensitivity temperature. Next, please. Next. So we have explored using the optimization proposed by EFA and combine these sensitivities with a single error metric and optimize these 6 parameters. And we found out next. We found out that we can reduce biases by 52 from 52 to 28%, which is mainly a reduction in bias in the sensitivity to temperature. Next. And we also see improvement in other metrics like NSD and long-term bias. And next, and we also think that because we are using global surface data set, if we used high resolution surface data, we could further improve these biases. Next. So to conclude, we found out that reducing errors in runoff does not necessarily improve long-term sensitivities, and this puts the question on model optimization that only considers short period, like 5 years or 10 years. We also, our sensitivity analysis suggests like that the surface runoff parameterization, resistance to soil evaporation and transpiration, and soil hydraulic constants like porosity are important sources of bias in runoff sensitivities in CLM. And this work also illustrates that consideration of long-term hydrologic sensitivity could help to guide model development. And finally, as the previous presentation, we need to expand this analysis. There will be a requirements for development workflow, similar to the single point, which could reduce the computation cost significantly. And thank you very much.
Great, questions for everyone? I guess I'm kind of struck, and this is maybe more of my own naivety with how hydrological modeling and calibration works, but I'm curious. It seems like from the last few presentations, you can kind of calibrate CTSM for a basin or for a watershed or something. Curious how that, if there's any way to translate that information back to a larger scale simulation. Like what can we take from these kind of smaller scale hydrological calibrations that we can apply to larger scale simulations, or is it really different questions that we're asking? That's like a giant bowling ball. Sorry on that.
I also don't know the answer to that answer. It's like, I think that's one of the problems that always come up throughout the year. How to generalize the parameters.
I mean, that's essentially the problem of regionalization. And so for many years, people have calibrated in individual places and tried to do a parameter transfer to the larger domains. It's not worked out, as well as you might have hoped. And so now that's where people are trying to learn more about parameter relationships using things like machine learning and deep learning. And maybe that holds some more promise. But. I guess I do have a question for the speaker. Very nice talk, very interesting to see this kind of work in local basins. I'm curious about the first conclusion, reducing errors in runoff does not necessarily improve long-term runoff sensitivities. I think if you read Mendoza, which you cited before, it did actually help to constrain runoff sensitivities. I think maybe there's some misinterpretation. I've seen that Mendoza also cited to say that there's not necessarily improvement, but if you look at the results carefully, there is. And I wonder, in what you were showing, you're basically showing that you have reduced errors in runoff and then sensitivities in just in one dimension, temperature, for instance, were not improved. You think that's something where you have to look at both sensitivities together to see that there is improvement, or is there another way to go back and look at that result? Because I find it a little bit counterintuitive, I guess.
This figure that you're talking about? Or?
I think an earlier one.
Yeah, honestly, I'm not sure. I don't know, because I need to further inspect and see, why this is happening. Because these are the results that I got. If you change if you minimize the RMSE, there are different parameter sets that will give you different sensitivity. And that could be, as you said, because also of precipitation sensitivity.
All right, we'll move on to Naoki and then have a little bit of time for discussion before our break. Go ahead. Hang on, wait a second until we get the screen figured out up here. Turn on your mic.
Yes. Can you hear me? Good? Yeah, it's okay. So my name is Naoki Mizukami. I'm a research scientist across town research application lab, mostly doing hydrology. Today, I'm going to talk about some recent work on mesout coupling into CTSM. So 2 topics. First one is kind of CTSM interaction between mesout and then CTSM. And then originally, I wanted to talk more about lake modeling and mesout, in CTSM framework, but I found some problem, so I reduced number of slides. So, but I wanted to touch. So Mizra has been in CTSM coupled for maybe a few years now. There's two other models, RTM and Mozart. Both just a big difference between RTM, Mozart, and Mizra is how spatial discretized in space. So RTM Mozart use regular grid, and then Mizra but use unstructured grid, very complex catchments, but can be run in a regular grid. So we are prepared for 4 different grids. You don't have to worry about too much name, but this is kind of product name we took. So HDMA is a coarse resolution, and the hydro is maybe 10 times higher resolution than HDMA. And then recently we added HDMA lake, which include lake for about 4,000 lakes in the globe. And then also we have some grid network, so we can kind of compare Mozart versus Mizra, so that's useful. One drawback using a catchment like unstructured grid is too slow in the computing, like weight information in online. So we needed to pre-compute like a regrid mapping file, and we have to provide, otherwise we're not gonna do Mizra. And then here is example like how grid versus Mizra catchments. Red is Mizra, like gray, and then catchment is Mizra grid. And then this is 6 grid boxes coming into Mizra remap like runoff and irrigation demand if you turn on irrigations. And then we have to do other way. If you pass something from Mizra to CTSM grid, you have to take Mizra catchments and then putting in a computing weighted average into a CTSM grid. This looks kind of weird, but that's happening right now. So this is a kind of zoom up and to Grove. This is the HDMA lake version of grid, but you don't see a catchments. And then one thing I should point out is Greenland in Antarctica is missing, so you have to do something when you couple it to the ocean. But if you zoom in, you can see a catchment in the gray polygons, and then also you can see lakes. So everything mapped into a catchment and then lakes, and then water is moving across the line and then lake. So I'm going to talk about a little bit coupling. So it's been CTF's Mizra coupling. It's been probably for a few years now. So this is the first thing we did, one-way coupling. So CTSM can pass runoff, total runoff through mediator remapping to Mizra catchments, and then you can route. So nothing coming from a Mizra to CTSM. But if you turn on irrigation, so we have to pass irrigation demands in addition to runoff. So Mizra can subtract water, and then that affecting river discharge and then volume. And then further, this is a two-way coupling. So if you turn on CLM name list, limiting irrigation based on river volume. So basically what happening is taking Mizra river volume pass through mediator back to CTSM, and then kind of reduce irrigation demand that's passed back to the Mizra. So it's going to be affect the river discharge and then volume. So we did this like end of last year, and then what we did is we ran a CTSM Mizra and then CTSM Mozart 3 years, and then we use the same gridded network, and then 3 types of simulations. One is no irrigations, second irrigation but unlimited, so no threshold, and then third one is limiting irrigation based on the river volume. And then we can compare to kind of evaluate some effect. So I'm gonna go through like a quick, because I have 22 slides, but it's gonna be quick. So this is a Mozart, but taking total runoff from CLM, and then left is no irrigation, right is irrigation. So you see some difference in runoff coming into routing model. That's something I need to talk about later to CLM group. Why is that? And then same thing happened with route. And if you route, okay, just a moment. Oh, shoot, am I? Oh, yes, oh, yes. So you see most of river discharge, if you do irrigation, it's reduced and because the water is taking out. But some of regions are increased because of a runoff change. And then same thing happened in Mizra. It's, I just apologize, it's got a 360-degree kind of map, so it's hard to compare, but it's actually similar. And meanwhile, and I turn on like a threshold, so limiting irrigation based on river volume. And then again, looking at the CLM runoff, left is irrigation, but unlimited irrigation, and then right is limited irrigation. You see again some runoff change coming into river model, and then so it's gonna be just a little bit reduced in the Indian subcontinent if you turn on volume limitations. And the same thing happened in Mizra, of course. And then looking at the river discharge, so if you limit irrigation, it's supposed to river discharge increase. So you see some increase in the blue line. This is Mozart example. And in Mizra, similar things happen. It's more blue line. So that's, we have to look into more detail, but there's some difference between Mozart and Mizra. So this is a pretty preliminary work, and then I need to testing and then analyze different way for water balance. And then, but so far we see a similar behavior in the Mozart and then Mizra. But if you limit irrigation based on the volume, it's maybe a little bit difference. So finally, just touch lake. So I wanted to show this in this working group, but we found some regridding issue, and I couldn't figure out what's going on. So, what I decided to do is to use the standard on Mizra, but taking CLM runoff and then precipitation and lake evaporation data to force Mizra, and then run about 30 years, 30 years of period. So this is kind of a big picture in the growth, showing 24 major river outlets and seasonality in 20 years, 1990 through 2010. And then assuming lake is all natural lake, no reservoir management. So very simple equations, but there's 3 parameters we can tune, and also storage of lake each time step affecting discharge, and especially okay. So like most interesting is St. Lawrence. If you don't do a lake, you see a snow melt coming in and then increase in the discharge. But if you have a lake, because St. Lawrence has Great Lakes, big lakes, so it's got flat. And depending on lake volume, that's gonna be affect the magnitude. And then you can see other river too, like Columbia River Basin too. So lots of things to do in a lake. Have to fix the regridding issue, and then we have to make sure water balance closure in the lake, river, and also irrigation whole system. And then we can do more testing for lake model itself to understand how it behave, and then finally moving to a reservoir model too. And then finally just acknowledgement. So that's all.
Questions for Naoki?
Just to clarify, how did you incorporate the irrigation information in the model? And I think that was global data related to irrigation. Where was that information
So
coming from?
irrigation model is from CLM. Like I think it's a crop model. I don't have much expert in crop model, but I think it's all simulated how much water needed. So it's not from a data driven.
Other questions for Naoki? Go ahead.
Hi, Naoki. I'm curious whether, great talk. I'm curious whether there would be like a convergence between the lake model and the reservoir operation model that Ian developed. Are going to keep it like separate model so you
No,
eventually
it's
want
gonna
to-
be, so right now it's 4,000, whatever number lakes, all natural, even lake made in Colorado. But it's gonna be, okay, this lake is gonna be managed. There's some parameters to tell, this is managed, this is natural.
Okay.
And then can use lake model. It's already in the code, but it's gonna be a lot of debugging for sure.
And then I'm assuming the lake data set that's coming into the new 5.2 surface data sets is consistent with.
Yeah, that's a good question, I guess. So lake like polygons is coming from a completely probably different source. I don't know, like we use the hydro lakes data set, it's polygon. And then we use straight like we're not doing any gridding, so it's probably similar, but I'm sure it's gonna be discrepancy between.
Looking over at Peter and Bill, I don't know if.
I think Bill might know better than I do, but I believe that provided the new lakes data set as well as for CTSM, as well as meso route. So I assume they're the same data,
Oh, okay,
but I
so
don't know that as a fact.
Yeah, if it's coming from but probably hydro lake.
Right.
So,
Yeah, I don't know for sure that, I don't know what's being used in Israel, but,
But maybe Sam will give the first talk to the next session. He might be able to.
I just add, well, I mean, the ultimate vision is, right, is we get all this working, we would have the capability to do reservoir management for the lake, for the reservoirs. There's a lot of steps that Naoki showed here, and probably even a lot more that he hasn't really showed. And then there's the coupling to CSM3, to the ocean model, that has not been addressed yet at all. So I don't know whether that's gonna pose a significant challenge or a minor challenge. I think that's an open question yet. So in the near term, we're hoping to get to a stage where this is like useful for CTSM research on its own, and then trying to push that into the coupled model. But the pathway remains unclear.
Yeah. Can you go back a slide, Naoki? I think that was what your like next steps. Forward, yeah, that one. Is I think that this is this kind of the to-do list then for what needs to happen to make it CTSM science compatible?
So I just came up maybe yesterday, so it's from my friends. It's actually, yeah, we have to maybe formally have to think about what to do. But yeah, the last 2 weeks the first recruiting issue, it's kind of trying to figure out what the hell going on.
Yeah.
I think, this is for the lake coupling, but there's other things that need to be.
Other parts of the.
Other things like, output management and restarts, and, there's a lot of these things are working, and Naoki knows the list better than I do, but there's a long list of things that gotta get ticked off, and Naoki and Eric have been steadily working through them.
Yeah, there's a lot of usability, trying to improve usability, like we have to be able to output like a monthly other than every time step. Yeah, restart is another thing. I think it's working, but not yet.
So, Naoki, I was wondering, do you think having lakes in the river network makes it easier to do some form of optimization of a catchment, or is it harder?
I would say probably becoming harder. Even natural lake maybe, but especially if you put like a, because lake model is very imperfect.
Right.
So, especially if you put in a reservoir, it's a lot of compensating, like because lake is not perfect. So, other parameter, CRM parameter probably compensating like some deficiency in the lake modeling.
Right.
So I think it's a little bit harder, I would expect.
Can you explain a bit more about the lake model? Is it a one-dimensional model? Is it only simulating the temperatures, or is it more involved in the dynamics of the lakes?
Yeah, so that's a good question, but it's not happening lake itself, like mixing or just trying to get some water balance, how much coming in and how much coming out. So
It's just a point, and you just put in inflow and outflow, and
Yeah,
something is
pretty much.
happening, evaporation from lakes,
Evaporation
or
is
storage
taking-
from lakes, but
yeah, evaporation is happening, evaporation and precipitation input.
Can I just clarify there? Because it's actually a little complicated, right? Because there's the lake model in Mesorat and there's a lake model in CLM. So lake model Mesorat is monitoring the water balance. But lake model CLM is doing like overturning, mixing, lake temperature profiles, ice formation, all those kind of things. And then generating, the surface energy balance, including the latent heat flux. So, and the effort that's going on here is trying to merge these two activities together so that it's more comprehensive. Does that make sense? So,
Yeah, thank you for
yeah. But there's not 3D. There's no 3D mixing. That's the only thing. Only vertical.
Just curious, is carbon and nutrients tracked in the rivers and lake schemes, or it's just a water balance?
Just for now, water balance, but we have been talking about tracer.
Okay, cool, just curious, thanks.
Yeah, that's.
Well, there's another activity out of the Norwegian group that's adding DOM fluxes. So for sure DOC, and I think developing nitrogen presumably too. And they have that coupled right now to Mozart, but there's no tracers enabled right now for Mesorat. But I think that's like, to me, one of the holy grails for the biogeochemistry working group would be to actually pass carbon to the rivers, have the rivers do something with it, and then export it to the oceans. So that capability is forming in Mozart, but it's not applied in Mesorat right now at all. One of the, I guess it's a parallel challenge to many other things where we kind of have parallel developments on different tracks. Figuring out how to maintain the old stuff and build in new capabilities and add new features like DOC is a challenge. Marius is going to talk on Wednesday about that work.
I guess I have a question. That prompted by Peter's question about, is it easier to kind of constrain the model with lakes or without lakes? I feel like there's so much, unresolved, lake and reservoir behavior out there. Like this data set has 4,000 reservoirs for the globe. US has something like 97,000 dams of various sizes, and probably more like stock ponds. And I kind of wonder if there's a limit to what the ability to represent explicitly all this reservoir and lake behavior. But does that mean there's a bulk parameterization for everything else that could kind of factor that in? Because without it, I feel like there'll be a lot of unresolved, lake reservoir detention and, modulation that will only be a source of error if you try to constrain everything, including the lakes and the reservoirs.
Right. I guess I was thinking more like, the St. Lawrence River, like you're trying to get base flow to do what the lake is doing, and that seems to be like you're using the wrong process. And so no matter how much you tune that up, you're still getting, even if you get the right flow rate, it's for the wrong reasons. Whereas having the model actually represent the lake process in there, even though it might be more complex, might actually get it was more of an open question rather than like having a point of view on it.
Yeah, no, I think that's reasonable. I mean, I guess my thought is you can get partway there you know, with all the lakes you know about and can actually specify. But then there's still this other part that is kind of like subgrid or sub-resolution, and I just wonder if there's another way to handle that that means that you could put it in. It's more bulk, you know, all the little things that are under a certain surface area, then they get lumped into a bulk parameterization.
Sort of abstracting out to this whole set of talks, how do we want to think about the fact that we're trying to optimize parameters in an uncoupled mode, and we know that like the surface temperature responses and the latent heat flux responses will be different. So we're trying to like compare regions or watersheds to observed properties and then modify the parameters, but we know that we'd get a different answer if we coupled the atmosphere. Which I like to be a squeaky wheel about, but like, what are we gonna do about it? What's the process that we're gonna deal with optimizing when we know, if we're trying to match observations, that that's not the right optimization?
So
Yeah, you did it coupled, right?
I did coupled, and also I used the optimized parameters in land models and do that in the coupled modeling. So it is definitely possible that the optimization will deteriorate the coupled modeling performance. So what we did in the project is, because we're doing like very high resolution regional simulation, we're doing 4 kilometers for Alaska, so it's very expensive. And we end up using just like the 12, experimenting different optimization. And you inject the optimized parameters into the coupled modeling and test it at the relatively coarse resolution, and finger crossed like it's not messed up things. So we end up finding, so when we are optimizing the parameters in Alaska, we find we have a very high metalline intercept, which leads to a excessively high transpiration, and which leads to a misty and cold summer in Alaska. So the solution that we came up with is to shrinking the range of the parameters for that specific parameters for Alaska. But I think there's definitely other like sensitive parameters which would be sensitive in the coupled modeling that we did not know when we're doing the optimization for specific hydrological applications. So, but I think Claire at University of Washington and yeah, Claire. Sorry, I between person. So Claire and also like Abby is like working on. Oh, you.
This is why we have to more in-person meetings.
Yeah, so you guys are working, and also like we actually recently just submit like a proposal to look at like sensitive parameters in the coupled model. Okay, that's very
So good. That's the best advertisement for in-person meetings ever.
But I've been wondering if we might be able to come up with ways to have transfer functions or something that at least gives us some sense about what the conversion is going to be. Is it going to be for specific parameters or different regions, or some way that we can get some idea of that mapping? Because it's really hard to do it at the resolution you need to do it in the coupled model, and we won't always be able to do that. But it feels like we also can't ignore that fact when we're calibrating it offline.
Yeah, yeah. Well, and it's curious too, like Yodis's work with WRF is all, that's another example of coupled model calibration. And I don't know if there's any convergence. I can't really pay attention enough to the knobs you all are tuning to get the right answer, but I don't know if Medland intercept is a big one. If there's like consistent results coming out of all these different regional studies and WRF and ROMs and other studies, that would be helpful to think about.
There's a familiar parameter list.
Yeah, it was FFF, whatever that is. Daniel?
I'm raising my hand for Andy Newman online.
Cool. Andy, do you want to unmute yourself?
There is still muted.
We can't hear you yet, Andy. No.
While he's trying to sort that out, Abby, this comes up all the time, and I mean, it sounds like maybe you guys have a project. I don't think we have a great I don't think that's a great solution, right, that we know. The only solution we have is that we can run the coupled model and use that to force, as the forcing to use the calibration. Of course, and then that misses the feedback of those parameters as they change. So you could iterate, do that a couple times. You know, if we got super efficient with how we calibrated so that we could turn this around in a couple of days, right, at calibration activity, you could actually imagine iterating in the coupled system. I don't have anything better than that. But it might be better than nothing, right? You know.
How about now?
Yeah.
You can hear me now?
Yes.
Yep. Great. Yeah, Dave's point is one way to attack it. And I think with like work like EFON and others are doing, you know, we'll get the automated workflows to be able to iterate. And it is really important to have as close of, I think probably Andy has said this already, or somebody has said it, it's important to have as close of the forcing data to what the coupled model might look like for your calibration, right? The climatology should be similar. The other thing I was going to say is a hierarchical system design, or HSD, HFT, whatever, like our, you know, hierarchical system testing, right? Moving from offline to single column to smaller regions to bigger is something that I think can work really well with optimization. And I think there are some groups that do it. We're trying to start doing that. So like, you know, calibrating with an SCM, right? So you have coupled at some level, you know, it's not, maybe not advection and everything, but doing those kinds of things and iterating across complexities of models and optimization will help. Pulling in different diagnostics is going to be important to trying to really understand where the feedbacks flow information. So those kinds of ideas. So that's all I wanted to say. But yeah, this is good discussion.
Thanks. Bill?
I guess this is sort of a question for the whole working group and maybe the CESM community at large, which is what should we be calibrating to? Because there's an argument to be made for calibrating it to what we think is the best possible observations, even if that isn't what matches the coupled model, or there's an argument to be made for getting it to work well in CESM3. And I guess, I don't know, Abby, you posed the question, do you have a feeling on that, or do others have a feeling on that?
Well, I guess my feeling is just that the impact of the parameter will be different in the coupled model. So even if you're aiming for the same observational data set, yeah, maybe you have two different sets of parameters for whether you're running it offline or coupled, because they're going to give you a different match to observations in those two systems.
Charlie has his hand raised online.
My point is slightly different than this. So if anybody has further things on this, I can wait, or I can go if this discussion's done.
Yeah, I think you can go, Charlie.
Okay. The question I had was to the point earlier in about the hill slope model and the sort of dimensionality of the hill slope model and how we deal with that in post processing. And I'm just wondering, like, how, I guess, how formalized are these kind of workflows for dealing with that? Like, other land models are also developing hill slope models, and are there any emerging standards for how to do that? Yeah, just want to throw that out there for discussion.
I don't know about emerging standards, but I think when you're in this calibration, computationally demanding, intensive, iterative process, one of the emerging or one of the guiding objectives is always just to make it as efficient and fast as possible. And so that may lead to some kinds of standards in the way people do things. But aside from that, I don't know if any formal standards have been developed.
I don't know if Sean wants to comment, but I haven't seen, Charlie, in the groups that are implementing some sort of a hill slope or subgrid, any sort of standard method. I think everyone is struggling with the ways to evaluate. I will say one activity that's happening in the CLASS project, the Coupling Land Atmosphere Subgrid Parameterizations, CPT, is using the really high resolution skin temperature data to try to evaluate the model. So that's not really like a method, but just, as one of the few things that we have that's higher enough resolution to maybe start to tease out and understand the differences. And the result that they're finding there is that the skin temperature variability is actually quite intense. On our normal grid scale, it's really big, and it's partly driven to, the land use, but it's actually, as much as anything, driven by the historical weather over the past few days. Did it rain at that location or not? So, not super satisfying, but there's, I think Meg might even has a proposal to try to, explore that a bit more.
Thanks.
It's time for a break. So if you're online, I think Elizabeth sent a link to a virtual breakout room if you want to pop in and see who's having coffee or tea there. For those of us in the Mesa Lab, there's snacks and coffee outside, and we'll get back together at 11. For those of you who are new to the building, there's a women's bathroom on the first floor over that way. There's a men's bathroom on the first floor over that way, and then there's a unisex bathroom on the second floor, right back there.
We're like on the floor and a half right now.
We're on the floor now. Yeah. you, oh, Sam, are you online?
Yeah, can you hear me?
Yep, it's a little quiet. Maybe, I don't know if you can get closer to a mic or maybe Nick can turn it up in here. That's better.
Can you hear me now?
Yeah, maybe down a little bit, Nick. All right.
Okay, testing again.
Yeah, that sounds good. Great. So one of the new features that's coming into CTSM is a whole bunch of new surface data sets. So a whole team of folks has been working on getting the surface data sets together, but Sam and Peter will kind of give the lowdown on what to expect as we switch over to this new surface data.
Great. And Sam, I'm going to advance your slides, so just start.
Okay, so we're going to talk about updates to the surface data sets. I have a long list of contributors that I gathered from various discussions on GitHub and issues on GitHub, and I hope I haven't missed anyone, and I apologize if I have. That's the next slide. So in summary, we will be providing new raw data sets. These are the files that are used for generating CTSM surface dataset files, the what's it called FSURDAT files. And we also will be providing a new Make Surf Data tool to replace the old one. Mariana Vertenstein is the primary author of the new tool. Mariana and I have done a lot of the testing, and then a longer list. The group that I've listed here, and probably others, have contributed in various ways to the development of the new tool. Next slide, please. So let's start with a summary of what's changing in the data. So we have new raw data sets for glacier, lake, urban, plant functional types, leaf area index, soil properties. We have new raw data sets for transient data, specifically for lake, urban, and plant functional types. Lake and urban didn't used to, so in the old tool, we don't have the capability of, well, we weren't using transient data. We didn't have raw data sets for transient data with lakes and urban, and now we will. There are other updates, improvements in the calculations, and in particular here I mention an improvement to the coastal land unit areas for calculating those more accurately. And then just for show and tell, I show here two maps. I could be showing any of the new raw data sets, but I'm showing percent lake from the new raw data on the left, and the difference between the new and the old on the right. And if you could advance to the next slide. Again, I'm not going to go into details, further detail on this, but if you would like more information, please go to the GitHub discussion, number 1868, where you'll find potentially excruciating details on what has been happening with this work. Okay, so if we go on to the next slide, I'm going to talk about the new Make Surf Data tool. The old one was called Make Surf Data Map. The new one, Mariana named Make Surf Data ESMF. This is intended to build and run on any CESM/SEAM supported machine. It is a distributed memory parallel program that uses MPI and parallel I/O. It also uses the Earth System Modeling Framework for regridding. As a result of these changes, the new tool eliminates the need for mapping files that were, I think, a cumbersome piece of the old tool. So mapping files are the files that enable mapping between the raw data set grids and the surface data set grid. The new tool scales well in terms of performance and memory. as the resolution increases, and so it permits generation of surface data sets at much higher resolutions. And so again, all of this makes it more likely that as a user, you'll be able to run on non-NCAR systems with the new tool. Okay, if you advance to the next slide, this is a juxtaposition of the new tool and the old tool as a schematic. And this is not the entire tool, so we're going to advance, as we advance through the slides, we'll see additional detail. But at this scale, the two tools look very similar. So if we start from the bottom, the goal is to generate a surface data set, and you do so with a Fortran executable. The Fortran executable needs a name list and a text file to run, to have information about what data sets it's going to use to generate the surface data. So now if you advance to the next slide, we'll see that here's one of the major differences. The old tool required mapping files to be generated and then used by the Fortran executable. The new tool does not require the mapping files because of ESMF doing things behind the scenes. And that improves the flexibility for users to potentially generate surface data sets at custom grids. The user still needs to generate a mesh file in this case for the new grid, the custom grid, but then the modifications to the name list where you'll point to your new mesh file are sufficient for the tool to then generate the surface data set for this custom grid. So flexibility increases with the elimination of mapping files. So let's move to the next slide, where I come back to a slide that I showed earlier, but I want to focus again on the advantages of this new tool. So the mapping files have become obsolete. The performance and memory scale well as resolution increases, which allows higher resolution data sets to be generated. And you're more likely to be able to run on non-NCAR systems with this tool. And if we move on to the next slide, this is a summary of my part of the talk. So we're updating CTSM's surface data sets by providing new raw data sets and a new make-surf data tool. And this will come, Will mentioned this in terms of version numbers. It will, so the changes are happening on a branch that we refer to as CTSM 5.2. And once that gets merged to the main trunk of the CTSM, then we will be proceeding with further developments in 5.3. Now I can hand this over to Peter to go on to more details about plant functional types, leaf area index, and so on.
Thanks, Sam. So I'm going to give you just a bit of an insight in terms of the first level of analysis we're doing with new land use, land cover change data sets. So for CTSM 5.2, there's a lot of feedback, that's okay. All underlying data has been reprocessed at the 0.25 degree resolution annually for the 850 to 2300 period. So we've got a data set, a series of these land use time series now that we're starting to go through and evaluate. As part of the process, we went through and we took out all the NCL components, and it's all now in Python with shell scripts for the whole workflow. There are C tools in there as well, but everything is now connected through this workflow through Python. All the land use tools are available on GitHub, which is currently under my GitHub account right now, but we're going to move that across to the CTSM GitHub, so you'll be able to have access to that. One of the key things that we did was looking at the way we did crop distributions, because in CLM5, we had the old Merca 2000 data set. We've updated that to this new product, which is the EarthStat 2000. And then combining that with the UNFAO's FAO stat annual data, country level data from 1961 to 2016. And I'll show you why that matters and how that's a really important way to evaluate crop distributions. We've also brought in the climate data and climate rules when we're doing extrapolation of areas that have been previously cleared. And that changes some of our historical forest distributions in terms of tree densities. There's also a lot more documentation for this whole process now. So I'm finalizing up the CLM land data tech node, this is the CLM5 version. Obviously, this will be updated for CTSM once we get all these data sets in place. We have shifting cultivation now that's actually on the data. It's off by default when you run CLM or CTSM, but you can turn it on. And there'll be high resolution 0.5 and 0.1 degree data sets so that are consistent with the 0.25 degree data for any particular year. And that'll be made available, that's in process right now. So what I want to do before I sort of go into the data is just explain a little bit what land use data sets are. And so basically when you're running CLM or CTSM in satellite phenology mode, biogeochemistry with crops, or a couple of the FATES configurations, you need to be able to tell the model what the distribution of vegetation looks like for any particular year, how that changes as you go through time. You also need to tell things like wood harvest, fertilizer application, irrigation, those components. So what we do is we have this thing called a land use time series and a surface data set that tells the model what the distribution is. So it's a prescribed distribution of vegetation for each particular year. And there's a set of tools that we work on that to generate those time series. So what we do is we take the land use harmonization data, which came out of CMIP 6, and that's a time series which we can then put plant functional types and crop functional types together with. So we build up what the description of each of those land use harmonization land units look like in terms of plant functional types and crop functional types from current day crop distributions and vegetation distributions. We can then extrapolate to areas that have been cleared based on these climate rules. And on the right-hand side of this plot, you can see the time series running from 850 Common Era through to 1850, then 1850 to 2015, 2015 to 2100 of the time series for the historical and then 3 particular SSPs or future scenarios. So the question is, we're changing a lot of the data, we're changing a lot of the process around how much of an impact does this really make in terms of the data set. So what I'm doing here is I'm comparing for trees, grasses, shrubs, and crops. The green, which is the new CTSM 5.2, the dotted black line, which was CLM 5, and then the future scenarios under CTSM 5.2. And so if we start looking at the treat areas, we see that we basically, current day, we're pretty close to what we had in CLM 5 and in CTSM 5.2. The new methods actually prescribe more forest back in 1850. And it's not a major difference, but it will make a difference in terms of carbon cycle, and we're going to start having to evaluate those sorts of things. That increase in trees going back in time also corresponds to a decrease in grass cover going back in time. So we have less grass in CTSM 5.2 in 1850 than we do in CLM 5. It's small, and I'll go into that in a little bit. What you can see is in this bottom left plot, the green line and the dotted black line lie over the top of each other. So the LUH2 cropping areas are prescribed exactly the same regardless. We haven't changed the cropping areas. The dotted red line we've got there is this UN FAO, FAO stat data. And starting to say, well, globally, what do crops look like? And you would sort of expect those two to lie over the top of each other. But what you can see is at the end of that red dotted line, it actually converges with the LUH2 data. And you think, well, why doesn't it just overlay for the whole time period? And this is because the land use harmonization data actually starts with HIDE, which is a reconstruction product that's based on population, and then it has to meet the UNFAO data at the 2015 point before it hits the integrated assessment models, cropping areas. So everything has to merge together. So you see there's this convergence as it hits current day. We see that also that the shrub areas haven't changed very much at all. Okay, so just having a look at current day tree distributions globally for CTSM 5.2 versus CLM 5. And you can see that they're very similar. There's a couple of places like in China where the new way we put the tool together end up having slightly less trees in this, I guess I can bring this in here. So this area in here end up with slightly less trees. I don't know why it's doing that. In CTSM 5.2, but there are other areas where we've got an increase in trees. So it basically balanced itself out. And here we can see that the crop distributions, in CTSM52 and CLM5 are exactly the same. So we've got this consistency in terms of the crop areas. So while we have consistency in terms of crop areas, the breakdown into the crop functional types, the individual types of crops, and I'm going to put a big thanks into Sam Rabin here, who was our guinea pig and started testing some of this and said, there's some problems here. And so we're trying to work this through. But we're doing a lot better in terms of hitting UNFAO numbers this week than we were a week ago. So what we can see here as each of these different types of crops, we have corn, and you can remember the green line is the CTSM52, the dotted black line is CLM5, and the red line is this is target we'd like to hit through the time series. And we can see that, well, first of all, CLM5 isn't actually that far off the UNFAO data to start with, which is a nice thing to see, considering that we didn't have the data we have now. But there were certain things, like if you look down here at cotton in the bottom left, there was a big discrepancy between the UNFAO distributions and the EarthStat distributions in CLM5 that's been resolved in CTSM52. We also get a lot of that interannual variability through that UNFAO period because we're using that data now. So what does that look like in terms of spatial distributions? If we look at corn, you can see that the actual spatial distributions don't change very much for corn. So this is for 2015. It's the Merca data set and the EarthStat data set have a lot of commonality to them. And so the areas that you would expect to see come up in both data sets. And the differences between the two are pretty small. If we look at wheat, however, we can see that the wheat distribution is quite different between the EarthStat and the Merca data set. And that comes through in terms of having more wheat in the central US, going down to Arizona and Texas, more wheat into Russia. But then we have less wheat in northern India and in China. So things kind of balance each other quite a bit there. And we can go through and look at the other crops as well. And we can see that this new green CTSM52 data set actually matches the UNFAO data much better than the CLM5 does. And for these sort of crops, so barley, cassava, citrus, these are very small areas, which means that they're hard to hit, like because you've got a big data set and you're trying to get small targets. But we're matching up much closer with these data sets. You can see that again for pulses, rapeseed, rye. Okay. And I will finish on that slide there. There we go.
Time for a few questions.
That's good. Okay.
Thanks.
Go ahead, Abby.
Where's the change in tree cover prior to 1970, location-wise? You showed 2015, but there's a big difference in the time series of trees from the old one to the new one. So where is the difference?
I haven't got that slide up
Okay.
here, but yeah, I was definitely, this is going through a process of doing the analysis now. And I just wanted to give you an update right now. We haven't done that. We haven't run the model to see where the carbon changes are. We haven't done any of that yet. So.
Well, I just meant like spatially.
Yeah.
Look up where the locations are.
Where the differences in the differences are. Yeah. So the time series differences.
Mm-hmm.
And the spatial patterns haven't changed very much. There's just a couple areas. I did actually plot it out for 1850, but I didn't put the slide in the talk. And a lot of it's in South America and marginal areas sort of transitioning from the Atlantic forests into the savannas. That's sort of like where you see more trees coming in.
Other questions for Peter and Sam? Right.
Well, first I'd like to really thank Sam for ridding the world of one more Perl program. I don't want to offend Perl writers, but I really appreciate that. But I actually had a question for you, Peter.
Yeah.
So you said that like you're kind of like making these two different data sets converge, like the FAO and then the HIST line, which I sound like had some high data in there.
So like the land use harmonization data has already done that convergence, so that we get that product straight from LUH2. So that's George Hurt and Louise Parsanjani. They've already done that process for us.
Okay.
But the reason why the UNFAO data doesn't match the LUH2 data until the end of the time series is they've done this harmonization process to take one data set that isn't actually matching UNFAO, because it's all population-based and it's sort of like reconstructed, to actually then meet that point. And then they suddenly hit the integrated assessment models, and they're all over the place as well, and they have to bring those together at the same point. So you want to have this continuous time series of crop distributions, which means that you've got multiple targets you're trying to hit, and that's what that harmonization process does. So
I was curious, why didn't they try to get the start of the FAO data matched? But it sounds like you're trying to get a lot of things all hitting the same.
I think it's just because the end point, we trust the data more. We've got remote sensing now, we've got sort of more comprehensive national statistics, that sort of thing. So I think that's why
Higher confidence.
Yeah, exactly. And also there's some, with the integrated assessment models, I think there might be a discontinuity between the historical period and future period, so they needed to align those anyway.
yeah, they just do it like kind of in one spot, I guess. That's the yeah. But it's a process, right? It's basically the sausage needs to be made somehow. It's kind of ugly sometimes. Great. But yeah, it's gonna be exciting. Like having a new model, having new data sets, like going through this whole evaluation process will be an exciting process.
Yep.
Yep. Cool. Okay.
Thank you.
Great, thanks. Nate, I don't know if you can hear us online, but as much as we can.
Yes.
Yes. And we can hear you, but if you can share your screen, I think I'd rather let you steer your own presentation than have me do it.
Okay, we'll give it a go. Are we working?
Getting there.
And sorry, my camera is on, but doesn't seem to be projecting anything. Apologize for that. Am I good to go?
I'm getting trained. Okay. Yeah, you're good to go. Thanks, Nate.
Okay. Hey, I'm Nathan Collier, and here to talk about ILAM and some developments that we've been working on changing how we do the scoring. And of course, we realize that this community is changing a lot since we first built ILAM, and a lot of people may not really know what it is. It's a lot of things, especially if you're in the DOE community. You hear the acronym quite a bit. It's a group. Fundamentally, it's a group of scientists really enthusiastic about benchmarking our models, comparing them to reference data sets. Could be the methods that we've assembled. We've written some papers about kind of best practices for how we evaluate those. It could be the software package. There's a lot of competition among packages these days, but you can install it. That's on CondaForge or pip as well. I don't have that listed there. It could be the data sets that we curate. More on that in just a second, or some of the results catalogs that we have. We have a big collection there, and there's just some of those with historical runs comparing CMIP 5 and 6 models and LandHist models and even the ocean. One plug, we recently revamped our ilam.org website, so a lot of this information is, I think, much easier to access now. So we encourage you, and as well as if you tried to go there in the past and got some scary certificate message, those should all be fixed now as well. And so we encourage you to check it out there. One of the things I wanted to point out is we get feedback from this group a lot that people are using our data sets even for their own research, simply because a lot of this data we reformat to be useful for modelers. It comes into a format that modelers understand. And the original format a lot of times isn't that way. And so if you go to the dataset page now, you can just click these links and get the datasets downloaded immediately. But I also want to make a little plug for an intake catalog that we built. If you haven't been part of the intake craze yet, it's just a way that you can have programmatic access to our data. So if you install the intake Python plugin and then point your intake open catalog to this very scary looking URL, but you can just copy paste it and it's on our website, then you can access this cat like it's a dictionary. And what I've done there is I've kind of started to access the dictionary and hit tab so that you see just everything that's available there. And if you let that complete, say like I went and grabbed just the weekend GPP data, then you can issue this read command, and the intake catalog is built in such a way that it will just go down and download it and immediately give it to you as an X-ray data set ready to go. And the nice thing is that it will also cache it locally. So if you already have done this on your system, it will just read that cached value instead of just always hitting the download. So this is super nice because then you can have programmatic access to our data, which means you can write your script that does some kind of analysis and then move it to a bigger machine and not have to worry about the data at all. It just comes down. So we just wanted to make a plug for that if you're interested, and that you can check it out. But the rest of this talk, really, I want to talk about some changes that we've been making to our methodology. And what we try to do in ILAM is to synthesize model performance across the globe. And that is actually pretty hard to do well. And that's because an error that you have in the tropics, the order of magnitude of that error is just very different than you might see in another part of the globe. And so what we've done until now is we normalize by the variability of the reference data set. And what that leads to a lot of times are variability that's very high in kind of the mid and high latitude areas because there's a stronger seasonal cycle, and very low in the tropics where the cycle might be driven by something else with lower order of magnitude. It's led to a methodology which really kind of emphasizes perhaps too much the tropical regions. And so we've been brainstorming, how do we circumvent this, or what's another way that we could normalize our errors? And what we've settled on here is to take a set of regions, something like Whitaker biomes. If you take a Whitaker plot and use observational precipitation and temperature, you can back out and get a latitude and longitude map of those biomes. Or you could take Köppen climate regions, which I believe Köppen was a botanist, and he definitely had vegetation in mind when he made those regions. But if you take those regions, we could say that, if you were to look at errors inside each of these biome regions, that we could treat them as commensurate because there's similar types of drivers going on in those regions. And so what we're doing is, for each of those regions, we're going to take quantiles of errors that come from a selection of models. So we're taking the models that we include in our CMIP 5 versus 6 collection, and we're computing quantiles of, let's say, the absolute value of the bias. You could just compute a quantile of any error. You could do this with any type of absolute value of error. And so then we're just going to pick one. In this case, let's pick the 98th quantile there across all models for a given region. And then what we can do is just say that the score at any X location is 1 minus the absolute value of the error at that location divided through by that quantile. It's just a way of normalizing the errors in a much simpler fashion. And the overall scalar score then is just a global integral there, but we can avoid things like mass weighting. If you have read our papers or familiar with our techniques, it also heavily weights towards the tropical regions where you typically have a lot more going on. So that's a lot of words, but maybe some pictures will help a little bit. The top left-hand panel there is the 98th percentile of GPP across all the products that we have in ILAM across the models from the CMIP 5 versus 6. So it's showing you, where you have large errors in the last couple of generations of Earth system models. And not surprisingly, you see a bunch very high errors in the tropics and lower as you go to higher latitudes. If you look over here at the top right-hand panel, you see the bias. That's the bias of CESM2 with respect to the FluxCom data product. And what you'll notice that's kind of anomalous are these high biases way in the high latitudes over like up in Alaska and northern Canada. That's very strange for CESM, but also with respect to other models as well. And if you look at the old way that we scored the models, you can see that those signatures are definitely there, but they're kind of obscured by the fact that just the maps are hard to interpret, because there's a lot in this score map it's going very poorly. But in this new method, these large errors in the tropical zones, those are not anomalous. Lots of models have large errors in the tropics. The ones that are anomalous here are these top ones that start to stick out a little bit easier. And so what we found is, as we've looked at this, it produces score maps that are a bit more one-to-one with the bias itself and easier to interpret. So one question then is, okay, well, which quantile should you use? I mean, the 98th quantile was picked to kind of capture the maximum error, removing some high anomalies. But we've actually played around with lots of different ranges. And here I'm showing you kind of a scatter plot across all of our variables and bias and RMSE. You can you follow this link here and animate it yourself and play around with changing the quantile and seeing how the new score is affected by the old one. But we're actually honing in a little bit more on maybe the 60th quantile, because it just maintains a better spread of scores across the full interval 0 to 1. If you pick something in a higher interval, then you get all the scores scrunched down into the 0.81 interval, and you're not using kind of the full interval that way. But we're still playing around with that. What does that do to kind of our understanding of CMIP 5 and 6 models? Well, here's a similar plot where on the left panel, this is the methodology as we have it, and these are the CMIP 5 to CMIP 6 improvement plots showing you versus an island from an ILAM score point of view, how well have these different models done from the CMIP 5 to CMIP 6 eras. And you'll see that if you pick something that's around 60, here on the right-hand side, you see it, there are definitely some anomalies, but the spread is overall maintained, and you don't really see a huge shift in our interpretation of what happens to models. If you push that all the way to 98, the 98th quantile, you see what happens. It really scrunches everything up here and becomes just harder to see differences between those scores. Another question then is, well, which regions should you use? I'm showing you stuff with these Whittaker biomes that we computed, but you could use Köppen as well. And this is a simple comparison across all of our variables, performance Whittaker to Köppen. And you would expect and hope to see that you get things pretty much on the same line, because both of those regions are both trying to kind of capture biome specific information in different ways. It really doesn't matter. And we, as a methodology, we think this is a very good sign, simply because it means that our methodology isn't sensitive to the way that you have chosen those regions. It shouldn't be, right, if it's to be kind of objective. The ones that are a little different are, this is a static image, but if you go here, you can mouse over and see there the biomass and runoff. Some places, precipitation, places where you see high values over regions that get partitioned in Köppen but aren't in the Whittaker, like the high latitudes especially. So that's what I have, and appreciate, as always, any comments, or if you have any questions or want to contact me, I'd be happy to have a chat with you. Thanks very much.
Questions for Nate on Island? Sorry, I can't see.
There's a hand up.
Nicole?
Nikki.
Oh, Nikki, good. Nikki, can you unmute?
So I don't know, can you hear me, guys?
Yes.
Okay. I wrote a question in the chat, Nathan. I'm just curious to know how you handle the different amount, the observational data density in your skill metric or score. Some regions are very heavily observed and others are less so.
Yeah, my gut reaction is I don't think we really do. We kind of treat reference data products without kind of making a judgment about them. We provide you several different options that you can look at. But for example, if you were looking at a FluxCom product, which was built out off of FluxNet data, we don't have something kind of built in to more heavily weight where there are more flux towers, if I think that's what you're asking.
Yeah, that's what I'm asking. Okay, thanks.
Although, Nate, this is Dave, if we employ the observational uncertainty option in ILM, it's effectively capturing that. So if the observational data set is correctly interpreting low data density as high observational error, then we would essentially downweight the impact of those biases there. So
yeah, that's totally true. We just need more data sets that provide that uncertainty window, but there are some that do.
Other island questions? Nate, as always, it's really cool to see the developments you guys are putting together. It's awesome.
Yeah, thanks so much. Sorry I can't be there, but would love to. Glad to hear what's going on, though.
Awesome, thanks very much. All right, next, Chris Still from OSU will talk.
share again. Such a rookie.
Oh, sorry. I think you can all hear me now. Thanks, Will, and the organizers, for the opportunity to talk about this. This is a bit of a switch of gears. It's less of a modeling-focused talk and more of an argument for things that might need to come into models. I've worked on this most closely with Linnea Hawkins, who's in the audience, now at NCAR in Columbia, but she was a postdoc with me at Oregon State, and we continue to work together. I've got a bunch of collaborators at various institutions, including especially Forest Service and a couple of universities here, and then I want to acknowledge the various agencies that facilitated this. And my title's a little bit broad. I should have been a little more careful. Really, this is a gigantic topic, and what I'm going to really show is a case study of one example of an extreme heat event, a heat wave that hit the Pacific Northwest in June of 2021. At the time, it was called the heat dome event, and there have been many heat domes since then, but this was sort of a more famous one because of the really extreme magnitudes of what happened. And it was, unlike other heat wave events, it was not that long lasting. It was 4 to 5 days, depending on how you defined it, with 2 really sharp, incredibly intense days right in the middle. And that's shown here, June 27th and 28th of 2021. These are air temperature anomalies from reanalysis at 2 meter for the 27th on the left and the 28th on the right. And you can see the spatial scale of this was really quite remarkable, extending down into California and across big parts of Canada. But really the center of all this, the most intense areas were Oregon, Washington, and into southern British Columbia on those 2 days. And depending on where you were at, it was more intense on one day or the other. And it was well known because it broke many, many all-time temperature records in multiple locations at these sites. It's drawn some attention in the literature, in the climatological and meteorological literature, trying to understand the things that drove this event and whether or not it was more likely with climate change, and that the answer is definitely it was. But this is just one example of a nice paper that was published last year in Science Advances, talking about it being among the most extreme heat wave events globally, defining this as standard deviations from the mean, where they mentioned that it's up to 4 standard deviations away. And just a quote from the article, a little bit, this doesn't show up at the bottom, but it says, over 4 standard deviations away from the mean. Throughout the entire globe, we have only 5 other heat waves found to be more extreme since 1960. So this is a truly remarkable heat wave event. And if you were living in the Northwest or in this area at the time, it was just shocking. It was almost hard to believe, very surreal. This goes on to say, and it got cut off a bit, that it was exceptional and certainly the most intense in that area that had ever been observed. This is an example of weather station data of previous daily max from a lot of weather stations in southern British Columbia, throughout Washington and throughout Oregon, showing the previous range, and then this was the heat dome event. You can see just the absolute magnitude of this heat wave, and then you can see this also in where it sits in the distribution of previous values. It was literally what they call off the charts hot, very likely enhanced by climate change, and very likely to have more and more of these sorts of events, as we all know. So heat waves are an increasingly hot topic to study for a lot of good reasons. And so this begs the question of what actually happened to forest ecosystems from this event, which is the focus of this talk. And obviously a lot happened, or I wouldn't be standing here talking about it. But just as a little bit of background before we talk about the impacts, I want to highlight this review paper from Teskey. If you're interested in this is a good place to start. Heat stress physiology has really lagged drought stress physiology. That community of ecophysiologists is really focused on hydraulics and drought stress over the last decade or two. I think heat stress physiology is lagging, but very likely to be the new focus going forward for quite a while, and especially interactions between water balance and heat stress, because they're really hard to disentangle. This paper highlights the fact that there are interactions across scales from cellular organelle impacts, things like impacts on photosystem 2 functioning, which is directly related to light harvesting and JMAX and things like that, membranes, Rubisco enzyme, heat shock expression. These are showing what happens with these things, whether or not there's evidence of acclimation. Leaf scale, big impacts on photosynthesis, respiration, VOC emissions, conductance, transpiration, and whether or not there's evidence of acclimation from studies to date. And then finally, at the canopy scale, lots of things like leaf area development, shedding, bud burst, growth, mortality, fecundity. So this is a good place to start. If you're interested in heat stress physiology, again, it's a rapidly changing field. I think this is really where a lot of the community is going to have to shift going forward, given the prevalence of heat waves. One take-home message from this paper and from the results I'll show here is that they do range across scales, and there's a lot of interesting variation in what we call thermal tolerance
which is a bit of a squishy term, but I'll talk a little bit later about that, both within species, within genotypes, and across species, and also at forest stand scales, lots of variation. Having said all that, many of these approaches that actually look at heat stress or thermal tolerance use a fairly standard approach, and that was done in this study here looking at two really important species, Douglas fir and ponderosa pine. So for the western US, it'd be hard to find two more widespread, economically and ecologically important species, so that's why they focused on these. And the classic approach is you take chlorophyll fluorescence, where you're measuring fluorescent light coming off individual leaves, or in many cases little discs of leaves. You expose them to temperatures, and then you measure what happens with temperature. So for example, in the top plot, this is related to light use efficiency. It's a classic measure called the variable to maximal fluorescence, where this is normalized to 100% is operating really, really well. And a classic thing you see is starting right around 40, you start to see a decline on this FEFM. And it varies a bit by species, but for many plants between 40, 45, 50, lots and lots of negative things happen. This community there's a lot of definitions for what you might call different things. This is an example of what's called T-crit, where you're just measuring the background fluorescence rate by leaves, and as you start to affect that photosystem 2, and all things happening with photosystem 2, the chlorophyll harvesting and things like that, lots of negative things happen. So this is, you get a ramp up in the amount of light, fluorescent light coming off. You get this decline in this FEFM, which has been called T50. So there's a lot of analogies with like the toxicology literature, like the dose response literature. This is also analogous to hydraulics, where they look at like P50 values that are, entering into the models nowadays. And then there's things like our Tmax. And the literature is a bit scattered. There are different definitions, but this is basically when you've reached the point of irreversible damage, and the leaf is essentially dead functionally. And one question is as you get into these areas, how functional is that leaf? How reversible are these as you go back up this temperature curve? And I'll get back to that later on. And how would you actually think about that with the models? There's a final approach using what's called electrolyte leakage, which is related to whether the cells are breaking apart the cell membrane. Okay, so after the heat dome, getting back to that's a little bit of background, but after the heat dome, one of the various things that happened right away immediately within days to a week or two, and people in the Northwest can, Claire and Abby can comment on this, we started to see this phenomenon where there was large-scale sort of bleaching of trees, almost like coral leaf bleaching. But the bleaching didn't turn them white, it turned them reds and oranges and yellows. Lots and lots of discoloration of canopies. We had nice green canopies. This was not exceptionally dry going into it. There are some areas that were droughted for sure, but it wasn't exceptionally dry. And drought impacts would have different patterning in time and in space compared to what we see with this. So there are lots of clues that it was heat impacts. If you zoom in at the scale of just individual leaves, this is a young Douglas fir. You saw things like this where it was orange and reddish here at the tips, and then apparently green beneath. And one of the questions this has always begged to me is, are the green leaves still functionally, are they the same? Clearly the yellow ones are dead. And depending on the species, they fell off right away, or they hung around for a while. But are these other green ones where they impacted, and to our eyes they look the same, but if you probe them with ecophysiological instruments, are they actually damaged and still functional? There's lots and lots of fascinating patterns I don't have to go into time. I don't have time to go into here, but we saw things like in some areas, it was the older cohorts of leaves, the second and the third year cohorts of leaves on Douglas fir that were impacted, whereas the new ones seemed to get through it okay and still look relatively green. We thought that was a pattern that was going to hold true until, of course, nature being nature, biology being biology, we found counterexamples where it was the younger leaves, the current generation that got really hammered, and it was the older ones that survived it. So what I'm giving you is just a tiny introduction to the massive complexity of things that we think affected leaves. There was enough concern about this that the U.S. Forest Service actually launched these low-lying aircraft. They have an aerial damage survey system that flies around the U.S. forests all the time at low elevations, and just trained observers with binoculars are looking at stands and marking whether they think it's a drought, some sort of pest outbreak, some sort of beetle or something, or in this case, heat impacts. And they saw, and this was incomplete. They didn't actually sample anything sort of to the west. So this is an incomplete sampling given the time constraints, but they saw lots of areas, especially in the western parts of Oregon and Washington, where there was extreme damage, foliar damage following the heat dome. And if you look at where the science circle is, it's actually this photo here taken from one of those aircraft. And one thing you see that's a hint about this is there's a very strong aspect effect, which is to say the west sides of hillsides and the south-facing sides of hillsides showed this sort of bleaching or scorching, whereas the east sides typically did not. So that gives us hints about what was going on. In short, we think the effect was that the hottest part of the day in the afternoon corresponded with relatively high solar radiation. This was right around the time of the solstice, so the solar angles were high, lots of solar radiation blasting heat. Physiologists have known for decades that heat plus lots of light is extremely damaging to plants. And that's what we saw here. So big aspect effects that you can see from airplanes and from satellites. We did some experimental work after this to sort of simulate in situ, in canopies, what might happen. Whereas the previous studies I showed you were all done in sort of very controlled conditions in a greenhouse, maybe with a tiny clip of a leaf put into a water bath to heat it up. We wanted to get away from the artificiality of those and to really try to do this in the field. When you're working, in some cases, 50 meters off the ground, it's really impossible to bring some sort of electrical heat, or the fire risk is really dangerous. So some collaborators of mine at the Andrews Forest developed these really simple passive heaters, just sort of a dark background you put behind it. And normally we had clear backgrounds on the controls. They don't actually show in these photos, but within, you can show that in this approach during a moderately warm period in June, when things are still really wet in this forest from the rainy season, you can bleach needles or discolor them or scorch them relatively quickly, on the order of minutes to hours, which again is another clue that this is not simply a drought effect or a water hydraulic stress failure effect, as some have supposed. We measure temperatures using thermal cameras, and you can measure that the control, which is these two here, reached maximum temperatures during sort of a small heat wave about a year ago in June, or last June. We're in the sort of 35 to 40, whereas the ones we artificially heated were pushing into that danger range. And we then went back within about 6 weeks and measured photosynthetic function using a pyrometer and a fluorometer, putting on leaves. And we can see that the control leaves were relatively unaffected, so pretty good electron transport rates, which links to Jmax on the models, but really greatly depressed electron transport rates. So real damage to photosystem 2. And this was not cherry picking just on these needles we essentially knew were dead. This was looking at other needles that still had quite a bit of green on them in the heated. So the electron transport was damaged, and again, this was many weeks later, and stomatoconductance was similarly perturbed. So one of the things I want you to take home is heat damage is not just a one-time thing. There's a real lag, and it damages leaves for weeks and potentially for the rest of the growing season. Moving along to other impacts, moving away from leaves a little bit, there's a lot of impact at the whole tree scale. And there was an earlier intense heat wave, not as intense, but a good heat wave in June 2015 in Southern Oregon at a site where a bunch of young Douglas fir trees were monitored in a common garden site using automated dendrometers that measure every few minutes the changes in the girth of a tree. And they showed that after that heat wave, which happened in late June, similar timing, all the trees essentially stopped growing. So there's something going on here. It's not just a leaf damage effect. There's some other series of signaling cascades we think that are affecting growth. So if the tree just gives up. It just stops expanding its stems after a heat wave. They created a statistical model to model the probability of growth cessation as a function of the maximum daily temperatures achieved and the photo period. So the longer the day, the greater the likelihood of cessation. That's not just a solar angle thing. We think there's actually a large component to the phenology and the genetic expression. It turns out that most trees do most of their growth right around the summer solstice within 10 to 15 days before and after, and there's a huge amount of cool genetics going on in the leaf gene expression. Nonetheless, so this was young Douglas fir. We saw a similar pattern with old Douglas firs at a different site in Oregon. These are Douglas firs that get close to 3 meters of precipitation a year. They're about 500-year-old trees, 60, 70, 80 meters height. This is an example for the change in the growth for the 2 years before. This is leading up to the heat dome is the blue line. This is 2019. 2020 was a nice, little bit better year. But then 2021, which is the heat dome year, was going on with about the same rate of growth until you hit the heat dome event. And then the trees shrank radically. And this is a common thing you see when you have these dendrometer bands, which you can automate and measure. Trees shrink a lot during heat events. They're losing tons of water out. They dehydrate relatively quickly. And then in the case of this individual, it just stopped growing. So basically, in fact, it shrank a little bit, and then it started to return once the fall rains had come in the fall. It started to swell back up and grow again. So again, another example of just a stoppage in the growth of the tree after a heat event, sort of a big shock to the system. If we look at fluxes, at a different way of looking at this, we've been looking, Lenny and I, at lots of different eddy covariance flux sites in the Northwest. And if we contrast a younger stand on Vancouver Island in Canada that's Douglas fir, it's a plantation forest, and then we look at an old growth stand. This is the Neon Wind River Ecological Forest site. So there's broadly similar species. This is 400 to 500 years old. This one I think is like 50 years old. And what we have plotted here on the top is evapotranspiration. The black line is the climatology over, I think, about a previous decade or so. The gray line is the historic range. And then 2021, which includes the heat dome year, is shown in the blue line. And so if you look at the data going in, they more or less look similar to what had happened before. There was a massive loss of water from that ecosystem. As the tree shrank, water was sucked out of the system, soils, et cetera. And then in this younger site, the evapotranspiration was depressed for a lot of the rest of the growing season. It didn't really start to recover into more normal values until the rains came. So it was a big shock to the system in this Douglas fir for water loss. The Douglas fir lost excessive amounts of water, higher than ever before measured. But then after that, it more or less seemed to return. So there's a function of forest age here. It seems to be more resilient. Carbon exchange, similarly, lots of carbon lost in the young stand. And it didn't really recover. It lost down into here and then started to recover with the fall rains. The old growth site, more resilient. It lost a ton of carbon, but then it kind of returned back to its normal. Okay, so just to wrap up, how would we model this? Linny has been taking the lead on this. How would you model these sort of irreversible or non-elastic heat impacts where the heat is carrying on and having impacts? Because the models currently don't seem to do that. This is an example of these similar fluxes for observations. Linny created for the SPA canopy model, looking at the percent of Jmax, sort of a similar thing. And these are essentially recovered. You go up and down this, and the Jmax is affected based on the temperature following that curve. But if you then try to do what Lynn is calling non-elastic, or in some cases maybe irreversible or partially reversible heat stress, again, the control plants from a study where they went out to 14 days, and then the heat impacted ones, there's a massive change in this photosynthetic efficiency, this FEFM, for day 1, day 0, day 2, day 7, and then by day 14, it seems to have recovered. So Linny came up with an example function where you depress your Jmax from its maximum possible, something like this after a heat event, a heat shock event, and then it slowly recovers to something like normal across some period of days. So that's one strategy that Linny has taken for how to model this impact and model the lags. So in conclusion, the response was individualistic at different trees. I showed trees that shrank the growth. There are a couple of examples of ponderosa pine trees that we saw where it affected them, they shrank a little bit, and then the growth afterwards is actually a little bit faster. But in general, most trees either halted growth or had greatly reduced growth at the stem after the heat event. The responses varied from obvious visual foliage to leaf damage that's not obvious from the eye to tree growth impacts and anomalous ecosystem fluxes. I didn't talk much about this, but we think there's an important role for phenology here, and whether the leaves as they develop in their cycle can actually do what's called hardening off for heat, where they kind of are more prepared for the heat. These heat waves have been hitting, the heat dome hit right around the summer solstice when a lot of the leaves, depending on where they were at, if they were coastal or interior, had maybe not hardened off. So phenology, we think, is really critical. And with that, thank you, and I'd be happy to take questions if there's time.
We'll have to save questions for lunch, unfortunately. I know.
I'm sorry I went a little
It's
bit.
so good. It's so fascinating. It's really cool. Maybe as we're switching, Daniel, do you want to ask your question? And Cesar, if you can start sharing your screen.
Yeah, Chris, see if you get the leaf temperature right and then predict the right amount of stress for that leaf temperature if we were doing it in the model. Can you compare the relative difficulty of those two tasks for us going forward?
Yeah, I'm going to defer that question to Linnea because she's been working on more or less exactly that.
Yeah, the leaf temperatures, can be 5 degrees warmer than the air temperature often, and there's a feedback then on the stomatal conductance and how much water it blows off to cool. So yeah, getting that feedback right, and then having that feedback influence the heat stress response is kind of a balance. So yeah, I think it's tricky.
Cesar, can you unmute yourself?
Hi, how are you? Can you see my screen?
Yeah, it looks great. You sound good. Go for it.
Perfect. Thank you very much for opening this space to share the results of the different projects. And also I would like to thank Chris, because this one has been a really nice introduction before my talk, so it will make a little bit easier for me to present some things on the research. Now I will present one point scale experiment that we carry out in Luxembourg within the framework of the capacity project This project has been carried out with the support of the Luxembourg National Research Fund, and I really would like to thank the support of all the team, that Mauro Sulis, Stan Szymanski, Kanish Kamali, Ginevra Fabiani, and Remy Skupas, because all of them, they have been providing really good ideas. So as it has been mentioning, the increment in the frequency of heat waves and droughts has been going up through the different countries worldwide, and this one is changing depending on the location, close to the sea, inside the continent. In this case, we are taking the example of Luxembourg, where we can see that the anomalies in terms of increment in maximum temperature, the soil stress, and also the number of days that every year is experiencing the drought is increasing. And in this way, we wanted to focus on, during the last 10 years in one experimental catchment in Luxembourg, the Baerbach catchment. In this catchment, we were able to run the model during 10 years, from which 4 of them, they experienced like a large total number of days with respect to the historical. We did this exercise because we saw that the new implementation of the plant hydraulics in CLM5 provides a really good tool to assess the hydraulic stress experienced by the vegetation. So in this context, we took the advantage of this catchment because it has been monitored for several years, more than 10 years. And they have a really good data set from where you can assess the reliability of the stress produced by CLM. So some characteristics of this catchment is small, it's around half a square kilometer, but it has a nice example, is a nice example of the main land covers that dominates here in Luxembourg, mainly broadleaf deciduous trees dominated by oak and beech, needle-leaf evergreen forests, from where both species, Douglas fir and spruce, are not native from this region, but those ones are has a high frequency in the forest. In this site, they have a large network of sensors, soil water content, groundwater, and then we took also sensors of subflow to determine the transpiration catchment scale, taking almost 19 trees from where we estimate the right transpiration values. And then as we know in detail the different conditions of the site, we tune the lower boundary conditions based on the description for this site, and also we tune down the atmospheric forcing to the nearest meteorological station to have a really good description. In this case, we want to test if the plant hydraulics allow us to identify these stress periods that we can identify in the forest. First of all, we did some small changes into the model, and following the recommendations of this paper, adding a fracture bedrock to allow the vegetation to extract water from deeper soil layers, from where the default configuration of CLM doesn't allow the vegetation to extract water, doesn't matter the type of vegetation. So we have this is the mixed response of the model, from where the correlation is quite good, about 90% with the default configuration, but we have a lot of stress values coming out from the model. And this stress is seen as the beta factor, that is the relationship between the stomatal conductance under experiences, stomatal conductance, above when you don't have stress. But when we add the fracture bedrock, we allow the model to retrieve actually the observed transpiration, having all the data improve the correlation of Pearson, and also the mean absolute error. But nonetheless, we have a strong change on the stress that we see. So we came out with the idea, okay, we are able to improve the model responds to one of the variables, transpiration in this case, but nonetheless the stress, we don't know exactly if we are experiencing or not stress. So here we came with the question of how we can go to test this accuracy. And then in this case, we went through taking field data. In the first instance, we went to taking the variability of the measured soil moisture of this site, and here we are presenting the data of the fracture model configuration because it's the one that provides us a good representation of the transpiration observed in the model. What we have here is for the period of the non-stress years, we can experience some values around 0.80%. Here is no stress going towards zero. It's a lot of stress in the model. And we can see the amplitude of the stress given by the size of the different peak, points, that the variability is not that big. But during the stress years, we can see an increment on the size of the pixels related to the amplitude of the individual daily values that increases the stress experienced by the canopy in this case. And here we are representing 3 years, 3 continuous years with droughts, with heat wave, 2018, 19, and 20. But nonetheless, the correlation is not that strong, and we are not getting drastic values of this beta factor. So we took the advantage of the installation of these additional devices, the dendrometers, that actually allow us. This is a dendrometer placed on the trees, and then as Chris mentioned before, these allow us to see the daily and hourly variations on the diameter, on the circumference, and this one is related to different values or different variables that may affect the readings, not only water stress, tree growth, freezing temperatures. That's why during winter periods, you can still have variation. Here, what we have is the tree water deficit that corresponds to the variability, the daily variability of the shrinking or swallow, this one is the shrinking of the stem. Here we have all the different species, and to describe the stress or the water deficit of the forest, we went by using the mean. Taking the mean and comparing this also, again, with the beta, with the canopy stress factor, and seeing the variability on the amplitude, we can see that there is a correlation coming up with the increment on the tree water deficit that we are able to describe or to see in this forest. Nonetheless, there are different factors. This one is related to how different sizes of the trees and how individual trees can reflect the stress that they have during this heat wave. In this case, here we have the data from 2020 and 2021. From this period, 2021 was not considered as a dry heat, as a heat wave event for Luxembourg. To finalize, the main take-home messages that we want to show is that the fractal bedrock framework that we apply actually improves the transpiration model representation, but it also decreases the canopy stress reported by the model. But nonetheless, this doesn't mean that the vegetation is not experiencing stress as we saw it with the dendrometer data. There is a timing. I didn't show the variability or the seasonality, but the timing of the canopy stress given by the beta factor actually goes together with the tree water deficit and the variability of the soil moisture. And also that the extreme stress conditions given by beta, sorry, here is less than 0.5, were not detected, but the amplitude of the daily values shows the seasonal variability that correlates with the stress saw in the forest. Thank you. I will take any question or commentary about it.
Any questions?
Yes.
Gordon, I have a question. I'm going to say, sorry, that was a great talk. Thank you very much. I have a question for you, and then I have the same question for Chris. So I will get my question in for Chris. When you guys are observing heat stress in canopies, are you noticing any difference between the overstory and understory? Are you seeing, for example, it's maybe the upper trees in the canopy that are getting heat stressed and the lower ones are not getting heat stressed? Have you noticed any of that in your observations?
In our site, there is no understory. So actually, beneath the Douglas fir and spruce is just like mosses that is growing because we have a high density. And beneath the broadleaf deciduous, it was mainly beech seedlings. We saw some yellowish leaves after the drop in 2019, but none in 2020. Something interesting is that we saw an important flowering fruiting event on the beech trees. So this could be another indication of the stress. Changes on phenology, all the trees trying to put all the seedlings, trying to give like the last chance to leave their progeny on the field. But extreme changes in Luxembourg or in this site, we didn't see it.
We definitely did, yeah. I think it was the solar radiation played a huge
Yes, I wondered about if there's some interaction with solar radiation, leaf water potential just getting dried out in the upper canopy, and the lower leaf layers are doing better.
Yeah, we definitely saw that. And then, like, if there was a big tree next to a small tree that didn't get the afternoon sun, the small tree seemed not.
Yeah, you would get those shading patterns. Okay.
Yeah, so it was a very dramatic shading, yeah, impact, yeah.
Thanks.
Great. Adrian, is that, sorry,
Yes.
Is that your screen that we're presenting?
Yes, can you hear me? Can you see? Because I don't have any feedback on if you can see my screen or not.
Maybe
I am? Okay. And you can hear me fine?
I can hear you, but we can't see your screen yet.
Oh,
What's that?
Is ours still presenting?
Oh, I think it might be on your end, Adrian. If you can try again.
oh, wait, I'm trying again.
And then
Is it working now?
you might have to shift to your slides though. We're just seeing like the Google Meet screen.
Okay, I think that's because I'm in full screen. I'm sorry for that. Is it better like that? Wait. Is it working or not?
No, we're still just seeing your Google Meet screen.
I really don't understand why is it happening.
Maybe if you get out of full screen.
Oh, okay, now I see it. Oh, I'm really sorry.
That's okay.
I feel really bad. Now you can see it now.
There we see it. And now
Yeah.
you can go to full screen.
Yeah, sorry for that. Well, thanks anyway for inviting me. Today I'm going to talk to you about
Looks like his internet might not be up to.
sorry?
You try sharing in full screen. It's very pixelated what we see on our side. Like the quality is not very good.
But wow, it's really confusing. I don't understand usually when I do that. Going to start again.
Do you have the slides if we need
I
them?
don't think I have. Did you share your slides with Elizabeth, Adrian? Because the other
Okay, is it now? I changed something. It's still not good.
Now I don't see anything. Okay.
I don't understand why.
Mine on my laptop now looks good.
It does. Oh. Okay, maybe Nick has no idea either. Maybe try, I don't know what you did the first time, but to make it work.
So now it's not going well.
So it looks like we're just not seeing it on ours.
I think now the problem is us, because
It's
it's
us.
fine on the laptop, so I would work on our end instead of having him change something.
Okay, I'll, oh, yeah, it does look really good here.
Not everyone sees it online.
Oh,
there we go. There we go. Okay, great. All right, now I think we're ready, Adrian.
Yeah.
That looks great. Thanks. Thanks for your patience.
It's fine. I will try to hurry up.
Oh, no, it's fine. Don't,
Okay.
you're good. Go ahead.
Okay, nice. Well, thanks again for inviting me. I wanted to share with you some of our first results about, we did an evaluation study over the Arctic with CTSM. And as you can see, since I've uploaded my abstract, I realized then in 10 minutes and now even less, I won't have the time to share with you some results we made about sensitivity studies with different atmospheric forcing and soil properties. But I made some additional slides if you want to talk about it after my presentations or if you want to read about it in the PDF. But no, today we are just going to focus on an evaluation study. So first, for that, I need to explain you quickly my model setup. We are using about a year-old version of the model. The concept is a satellite phenology, but we plan to use fates in the future. We are using an Arctic domain above 57 degrees north using a triangular grid of 12 kilometers square. We use this kind of grid because we plan to couple it with an atmospheric model. And this model is using this kind of grid. We are using ERA 5 as well for the atmospheric forcings. The period is 1980 to 2021 after a spin-up of 30 years. And probably the only things that we really changed was a couple of snow parameters. That's because after running a first spin-up, we realized that many Arctic islands were showing very high snow depth values. They were completely glaciated, as you can see here. There are values above 12 and sometimes even 16 meters. So we try to twist some of those parameters.
Your slides aren't advancing, so you should try that.
I know.
Yeah, we have a very nice picture of the Earth, but that's all we're seeing. So
The title slide.
yeah, we're just seeing your title slide.
Maybe we should.
I don't know if Nick, if we should go to YouTube to watch, or
Stan, why is it only me?
I don't know. Maybe as we're figuring out the technical difficulties.
Let's just have us drive the presentation then.
I don't think we have it.
Adrian, you did upload it to the...
Yes, I uploaded the PDF. I won't have nice animation, but I guess it's better than nothing.
There it is. There you go.
I think the challenge might be is sharing one screen instead of sharing his entire screen. And when he makes navigations, that happens sometimes. So instead of just sharing one screen, he can share entire screen.
But like when you asked me the first time, I shared the entire screen and you said it was not working, but I can try.
I think we'll just maybe try from our side to advance your slides, and then hopefully it works. Are you able to see, if you stop sharing your screen, Adrian?
Sorry.
And then, can you, if you go back to YouTube now, or I'm sorry, to Google Meet, do you see our screen here?
I see it in very small. Okay, now I see it well. Yeah.
Okay.
Okay, so you miss a bit everything, but anyway.
Is this a good place for us to be, or should I go forward or backward?
Yeah, you can go forward. So I was speaking about these very high depth values, snow depth values here that you can see. So some of those islands, as you can see on the left, were completely glaciated in the default setup, and that's why we try to change a couple of parameters on this, and we had what we think is a better distribution of snow for those islands, and it's quite important in our work because we have quite a few observations about those islands. You can go to the next slide. Yeah, oh, this is really bad because there's some animations there. Okay, I will try to do without it. So I told you about the model setup, and now we also need observations. We use 3 kinds of data sets. The first one is ESA-CCI products, which are basically, they call it remote sensing products, but it's basically a model with a very high resolution that is forced by many observations. Here we use 3 different variables: soil temperature, active layer thickness, and permafrost extent. And we can only have years average, unfortunately, with this data set. We also use the CALM network, which consists of 98 stations. There, they measure active layer thickness, again for years average, for a bit longer period. And finally, you cannot see it, but our homemade products is some in situ observations that consists of more than 278 stations, and you can see the location and of the stations over here. Yeah, and just one thing I wanted to talk about before is that all the results I'm going to show during this talk is going to take the period average, except for the in situ observations. And as you can see, there is different data sets and also physical variables and different dimensions. So the storyline that I'm going to tell today for this evaluation is going to be, I'm going to show first the best results that we got to the worst results at the end. So there won't be any sandwich method, unfortunately. So that's why we start with the permafrost extent. And when we compare CTSM and ESA-CCI, you can see there is a very strong agreement between both. There is just a slight overestimations, mostly over Siberia and Russia. Next. After that,
Sorry, there we go.
No, yeah, thanks. After that, we can look to the active layer thickness. So here, again, above 65 degrees north, CTSM is pretty similar to ESA-CCI within 1 meter of range. But you can see that at the borders, what we call the warm permafrost areas, there the active layer thickness is greatly overestimated by the model. And then something that we don't really know why it's happening. There are a lot of processes involved in those, so we need more time to understand that. But if you go to the next slide, you see that we also share the same conclusions when we look this time CTSM to the CALM network that I explained before. So here you can see that all those little dots here, that's at the station side, that's the difference between CTSM and the CALM station. And there you can see that the borders, the difference is really huge compared to the rest. Unfortunately, there is no station of the warm permafrost in Siberia, but we can expect the same conclusion. And finally, next. Finally, the rest of the talk is going to be about soil temperature. And we were quite surprised that the difference between CTSM and ESA-CCI is really huge. It's a strong cold difference up to -8 degrees in Siberia. It's much more significant in Siberia than on the wet side. And we also see the same results when we compare the -5 meters and -10 meters depth layers. So yeah, we were trying to understand more why it was happening, and that's why we want to use this huge data set of that I just explained before, our in situ observations. And as you can see on the next slide, I just want to explain you how huge is our data set with this visualization. We have more than 274 stations. What is great is that we don't have only period average, but months average for those. So we have a lot of different months and also a lot of different possible depth. from 0 to 40 meters. Why that many? That's because this data set is consisting of different data sets coming from the US, Russia, and so on. And those countries have different philosophy on how to measure soil temperature. So that's why there are not that many depths. So my job was really to try to find the best way to visualize it, to compare CTSM with those stations. And an easy way to do it is to, perfect transition, thanks. Easy way to do it is to plot, to just plot all those data in a scatter plot. So here you can see on the x-axis the observations, and on the y-axis the simulation. And so for all station, all months, and all depth. And the only things that I've done here is that I I group all those points depending on the regions. And I calculate a person coefficients to see the correlations. And as you can see, the coefficients highly depend on the regions. And there is a clear gradient from the west, where you can find very high coefficients, to the east, where you can find lower coefficients. So next slide, please. Yeah, so what I've done here is that I took the two examples I showed you before. I took the region of Alaska and Eastern Siberia, so the best and the worst. And I've taken the same data, but I've done different clustering. Here on the left, you can see instead of regions clustering, I take the different soil layer depth. And it's pretty, through the column, the coefficients are pretty similar, so it's good. But on the right, you can see I've done the same, but this time for months. And here you can see that in Alaska, every month's coefficients are lower than the year average coefficients, which might indicate us that the model is not representing very well the seasonality compared to those observations. So that was the best example. Now going to the worst example in Eastern Siberia. And here you can see that on the left, that's something that you can observe actually on the whole east side, but the deeper you go in the soil layers, the less related will be the observations with the simulations. And at some point, they are not related at all, as you can see here. So we think that it might be related because top layers are more dependent to atmospheric forcings, and that's why they are closer to the simulations. And on the right, you can see that when we do the same but for months clustering, then there is no more relations between observations and simulations. So clearly there is something that the model cannot catch here, or we think it might be related to some parameterization or snow representation that are not adapted for Eastern Siberia. And finally, so I've done the same. This was some scatter plot, but I've done the same. This is the same data, but for heat map. Here you can see on the x-axis, I've averaged around the months for the whole period, and on the y-axis, it's the depth again. On the top, it's the difference between CTSM and again the stations, and on the bottom, it's the spread around the mean using Woodman's square error. You can see again the same observation that there is a cold bias pretty much everywhere. There is only a significant warm bias in Canada over winter. And we think that it might be related to the fact that most stations in Canada are on islands. And we saw at the beginning that the snow depth values there are very high. So therefore, maybe the thermal insulation was really high. And therefore, that's why we have this warm bias there. But in general, the model is too cold, and the spread between is really huge. So the final slide. Yeah, so I try to summarize everything I said on this slide. I'm sorry that this talk brings more questions than answers, but we are still at the early process of this study. And if you go to the very last slide, yeah, I just want to point out that I made a GitHub project where you can use your own simulations. and do the exact same evaluations very easily and very quickly. Thanks everyone, and sorry again for the problems. I'm ready for answers if there is any time.
Maybe a quick question for Adrian. Go to lunch. Yeah, Sean.
Maybe two questions. Okay. Well, one, it looks like some of your biases look like they were correlated with elevation. Have you filtered based on elevation to see if there's any relationship that shows up? And then the second is, how can we be way too cold, but the active layer is too deep at the same time? Like, how is that even possible?
So first, for the evaluation, yes, actually, that's something that I had to talk about it with my supervisor, and I think she's here, so she will find it funny. But I look at elevation difference between the stations and the closest pixel to the station, and I'll try to include this difference and to try to put some kind of a temperature difference. But it was not helping, and the change was not very substantial. There was really not anything that we could. The difference was not really big, so we kind of dropped this idea. And also, you have to think that we look to soil temperature. So in the depth, in like below 3 meters. Then you have to argue if it's really important to look to the elevations difference between the station and the pixel of the model. And the second question was, what was the second question again? I forgot, but it was a good one.
Oh, well, how do you have very deep active layers
yeah.
at the same time? How does that work?
Yeah, so that's something I actually don't really have an answer to bring now, because you have also to know that the active layer thickness is only derived from annual mean temperature and maximum and minimum, whereas here, we saw that the bias is also more. It depends on the seasons much more. And secondly, so you can have a good year average, but a bad seasonality. I don't know if you understand what I mean. And secondly, it was only in some at the borders of our domain that we could see those huge difference in active layer thickness. Otherwise, it was in the regions where the bias was the colder, the active layer thickness was not that different from the different data set that I showed you.
Adrian, thank you. Looks like there's some more going on.
Yeah, I see that. I guess I will answer them now.
Cool.
After.
Okay, that's great, thank you. Before we break for lunch, for those of us that are in the room, it's not too early to start thinking about dinner. So there's no dinner plans for the meeting tonight, but tomorrow after the meeting, we'll go down. It's Stout Month at Under the Sun, and hopefully have some time to continue the conversations tomorrow after the meeting. Elizabeth's going to send out a Google form for you to click if you want to go, and then also click if you need a ride, so we can get people down the hill in a timely fashion. Otherwise, lunch is around the corner on the first floor in the cafeteria. We'll see everyone back in an hour. Thanks.
came down and started up, but
Yeah.
it is a little bit more. Yeah, right. Global discrepancy.
Actually, I haven't done a talk here.
It's not even, I'm just saying.
It's not? It's close. It's not close. You got a couple of minutes.
I don't have to look at chat. I'm gonna move to where I can actually see the screen.
Okay. Sounds good.
Sorry, I can't. Close my eyes, I can't focus on it. Yeah, I have to go to a periphery.
Yeah.
Okay, welcome back everyone for this afternoon's session on looking at land-atmosphere exchanges. First up, we have Isla Simpson, who will be talking on a global discrepancy in atmospheric water vapor trends between model and observations. Isla?
Thanks. Is this on? No?
You got turned on. Oh, yeah.
I have turned it. Oh, that's on now. Yeah, good. Okay. So yeah, I want to acknowledge collaborators that are listed here, some of whom are in the room, and also some funding from the NOAA MAP program and NSF funding to NCAR. So first of all, I'll just give you a couple of reasons why we should care about what water vapor has been doing. One is that there are very close links between water vapor and wildfire through the vapor pressure deficit. So the vapor pressure deficit is the difference between the saturation vapor pressure and the actual vapor pressure. So the actual vapor pressure depends on how much water vapor you have in the atmosphere. And this figure here is showing an observation-based analysis of the relationship between burned area over the American West and then vapor pressure deficit in various wildfire seasons over the last few decades. And you can see this very strong relationship. It's actually an exponential relationship. So if you have a higher vapor pressure deficit, which can come from either higher temperatures or lower water vapor content in the atmosphere, then you tend to have a higher burned area. And then another reason is that it's just kind of an indicator of how various processes that are of relevance to the hydroclimate have been evolving. So this diagram is just kind of showing the various processes that matter for the hydroclimate, and with the exception of precipitation, most of these we haven't really observed on kind of a global scale for multiple decades. But we have observed water vapor, and so if we see something going wrong with near surface water vapor, it might be indicating something going wrong with these other processes that are of relevance to the hydroclimate. So I'm going to start by showing you trends in near surface vapor pressure over North America with a focus on the southwest. So on the left here, you see trends from ERA 5 reanalysis, and on the right is raw station data. So these are not independent of one another. ERA 5 is assimilating the stations, but it's reassuring that they're kind of similar. And in particular, you see that over the southwest here, we've had a pretty big decline in near surface vapor pressure. So we just take an area average over the 6-state region here, and we look now at the trends in models. This is the trends from all members from all models in the CMIP6 archive. This is the trends from the CESM2 large ensemble, 100 members, and then these are the observation-based trends. So our coupled models are nowhere near this decline in vapor pressure that we've seen over the southwest. The distribution doesn't come anywhere close to encompassing what we've observed. And that's true even if you give the model observation-based sea surface temperatures. So these are the CSM2 GOGA simulations, which have got prescribed observation-based sea surface temperatures. And that still doesn't get you anywhere near to these vapor pressure declines that we've seen over the southwest in observations. So our models come nowhere close to simulating this negative vapor pressure trend that we have observed. But so the Southwest has had a pretty big precipitation decline since 1980. So I should have mentioned, this is 1980 to 2020 trends that we're focusing on. So we might think, well, this vapor pressure decline that we've seen is maybe related to that precipitation trend that we've had in this region. So we can look now, this is across model members, where the x-axis is the 1980 to 2020 precipitation trend, and then the y-axis is the 1980 to 2020 vapor pressure trend. And so this is across all members from CMIP6, and then on the right is for the CSM2 members. So we kind of learn a couple of things from this. One is when you look across the model members, the trend in vapor pressure is related to the trend in precipitation. So if you have a higher precipitation trend in a model member, you tend to have a relatively more positive vapor pressure trend and vice versa, and that kind of makes sense. But also this whole distribution is kind of offset to positive values. So even if you have zero precipitation trend in the models, you tend to have an increase in vapor pressure over the last 4 decades, and that's because the atmosphere has warmed, and a warmer atmosphere holds more moisture. Now here's where the observations are. So you can see that we have had a precipitation decline over the Southwest that's pretty large over the last 4 decades, but it's not outside of the model distribution. But the observations are very much outside of the model distribution when it comes to looking at the vapor pressure trend. So even if you account for what precipitation has been doing, there seems like there's something off in the models in terms of what the vapor pressure has been doing. So we can kind of look at this relationship based on the model members between vapor pressure and precipitation, and we can kind of define an uncertainty range around this relationship using the residuals of the model members. I'm just doing plus or minus 2 standard deviation of the residuals. And we can look at the difference from what we would predict based on the observed precipitation trend and this relationship across models. And we can ask, is it outside of this range? And in this case, over the Southwest, it very much is. And so we kind of have 3 possibilities here. One is that maybe we're not getting something right about how precipitation and vapor pressure relate to one another. Maybe this relationship should be steeper in reality. And if that were true, it's not totally clear. I mean, that would be a concern, but it wouldn't be totally clear how that would affect our future projections, since in the models, on average, you really don't have a precipitation trend over the Southwest. Another possibility, which would have much clearer implications for our projections, is that maybe this kind of forced thermodynamic rise that shifts the model distribution to positive values is overestimated in the models, and maybe in reality, water vapor is just for some reason not responding that way. Or maybe we're kind of missing some additional variability that's unrelated to precipitation in the models, so that the kind of spread of these residuals around this regression line should be wider so that it could then encompass the observations. So to try and distinguish between those possibilities, we're going to shift from just looking at the Southwest to looking at the global picture and do this same kind of analysis, but at every grid point, where we take the model relationship between precipitation and vapor pressure trend, we use the observed precipitation trend, and we look at the difference from what we'd predict based on the models and ask, is it outside of that gray shaded range? And when we do that, this is what we get for the global picture. So now you see there are many regions, not just the Southwest, where the vapor pressure trend is outside of our expectations based on the model. So where it's gray, the observations are lying within the model distribution, but where it's colored, they're not. So there are a couple of regions where it's positive, but kind of overwhelmingly, the discrepancy is negative in the sense that compared to what the model suggests should have happened, in reality, we've seen a relatively negative vapor pressure trend. So that could be less of an increase, or it could be an actual decrease in the observations. And if we look now at kind of climatological aridity zones using just a standard aridity index, in orange here, you're seeing the arid and semi-arid regions of the world, and you can see that where we see this discrepancy is not randomly distributed. It's pretty much focused in these arid and semi-arid regions of the world. And we can look at that a bit more formally. So here I've taken all of the land grid points and binned them into 30 equal area aridity bins. So we're going from the most arid regions to the most humid regions. And then for each aridity bin, binned into 15 equal area bins according to what precipitation has been doing. And so here I've switched to looking at specific humidity, and it's expressed as a percentage of the climatology from 1980 to 1990, and normalized by land area average temperature change. So we're looking at trends in percent per Kelvin. So if it was following Clausius-Clapeyron scaling, it would be about 7% per Kelvin. And I'm kind of depicting by this white hatching here the grid buckets or the bins where the scaling is close to Clausius-Clapeyron scaling. So the arid and semi-arid regions are between these dashed lines here. And you see that water vapor is increasing in the humid regions, but on average it's not in the arid and semi-arid regions. So in the middle, where you kind of at the 50th precipitation percentile, where you basically have no precipitation trend, you have about zero specific humidity trend. And that means that in areas where you're like the Southwest, where you have a decline in precipitation, you actually have a decline in specific humidity and vice versa. Now here's what the models look like. And they are pretty much following Clausius-Clapeyron scaling everywhere. So in locations where you have near zero precipitation trend, you have about a 7% per Kelvin increase in water vapor. And that's true even in the arid and semi-arid regions. And so when you take the difference here, the difference is really significant in between our dashed lines in these arid and semi-arid regions where you just don't see as big of an increase in water vapor in reality as what we expect from the models. So now we'll just, for the last plot, focus on arid and semi-arid grid points only. And here we're looking at the joint probability distribution of specific humidity trends versus precipitation trends globally in arid and semi-arid regions. So this is for the CMIT models, and this is the average over precipitation bins of 0.5 millimeters per day, or 0.05. And this is a 7% per Kelvin line. So you can see that the models really are pretty close to Clausius-Clapeyron scaling. This is what we see in observations. So what you see is the whole distribution is kind of offset to lower values of specific humidity trends, kind of regardless of what precipitation is doing. And so if you remember our three possibilities here, if we exploit the kind of spatial variations across the arid and semi-arid regions of the world, you can see that what appears to be different here is this vertical offset, where the models are showing an increase in water vapor close to Clausius-Clapeyron scaling, and that's not happening in the observations over these arid and semi-arid regions. So overall, this forced trend in vapor pressure that's kind of independent of precipitation in the models does not appear to be happening in observations. And so something is wrong, which could, I think, have potentially severe implications for climate projections in arid and semi-arid regions of the world. It seems like our models have access to some water, which allows them to increase water vapor as the planet warms. And in reality, there doesn't seem to be that access to water. So there are a number of possibilities of what might be going wrong. And I think the primary thing, which is I guess why I'm talking in this working group, is it seems like maybe our models have too much water availability from the land surface, which is allowing them to satisfy this increased atmospheric demand. And in reality, that doesn't seem to be happening. So I've listed a few possibilities there. Definitely glad to hear any thoughts on what you think might be going wrong, and happy to take any questions if there's time.
Yeah, we do have a couple of minutes for questions. So, yeah, Abby? And the mics are not on. So. Yeah, mics are on now.
Okay, great. Thanks, Isla. I was wondering, for this first point, if there's too much water availability from the land surface, if you've checked or if you've thought about checking like an experiment with tracers of ocean evaporation to see how much of the water over land is actually from ocean or land?
Yeah, I have not done that. I guess I've spoken with Adriana and Bailey a bit about potentially what could be done with isotopes to somehow look at that. I feel like it's a good idea. I thought about doing nudging experiments to see if you change the atmospheric transport, do you change anything? I mean, I feel like just because it's a global problem in all of these arid and semi-arid regions that are affected by different moisture sources, that it's more likely to be water availability from the land surface. But yeah, maybe we could see if models are biased climatologically and with that kind of experiment. Yeah.
I think we've got enough time. Yeah, Chris?
For plant physiology, are you thinking of decline and stomatical conductance?
I guess so, that somehow the plants are holding on to their water much more than the models think they should.
Great, thanks, Isla. Okay, so with that, we're going to transition to the next talk, which is Danny Long, and I think he's online. So Danny's going to be looking at improving the desert dust emission representation in CLM5. And Will, you going to do this part for him? Thank you.
I'll have to maybe stop sharing. There we go. Danny, are you sharing your screen? Can't hear you either.
So I'm going to share my screen.
Great. Do you want to put it in presenter mode? Yep.
Yeah, so, okay, I hope you can hear me well.
It's not in presenter mode right now.
So do you want to put it in present mode?
Okay, yeah.
Great, that's good.
Right, so I hope you hear me well. Thanks for listening. This is Danny from UCLA. Today I'm going to talk about our work on improving the desert dust emission representation in the community land model CLM5 or CTSM. So I just want to acknowledge my co-authors, collaborators, Jasper, my advisor, Lonely and Natalie from Cornell, and then Dave, Eric, Simone, Francis from Anchor, and a bunch of other collaborators in Europe for helping in this work. So today's talk, I'm going to talk about some of the changes in the desert dust emission parameterization, some of the updates, some of the contents are going to be a little bit similar, to what I've shared already before. But I'll also talk about some coding changes and some of the prospect upcoming work. So just a little bit of motivation why we want to do this. It's because, as you see, CESM2 is not really simulating dust cycle really well in terms of spatial variability when it's matching against MODIS Aqua dust observations, AOD. So you see some blocks or hotspots of AOD, really high values over Sudan and Australia and China, for example. So we think we can improve it by adding some of the extra aeolian processes and dust emissions parameterizations or physics into the scheme to actually improve it. So we have done a bunch of stuff, and because of time, I won't be able to cover all of them, but I'll just quickly summarize the third one and the fourth one, which is we are adding in the wind drag partition effects due to rocks and plants, and dust emission intermittency due to planetary boundary layer turbulence. Just a quick recap of what we are doing here. So first of all, it's the drag partition effects due to rocks and plants. So as you know that there are rocks and plants, pebbles that are sitting over the deserts and actually sheltering the desert surface and covering the deserts. So they act to dissipate the wind momentum. So actually part of the wind momentum really goes to the soil surface and induce soil erosion and dust emissions. So it's not all of the wind momentum, but part of it. So we need to account for it because it's mostly not accounted by many of the current climate models. So we come up with a drag partition factor. We call it F effective, ranging from 0 to 1. And that accounts for the amount of roughness due to rocks and plants over the land surface. And so you can see a map here. It ranges from 0 to 1 with the most exposed areas over the Sahara, for example, being the most erodible source regions. And then as you move further away from the deserts to the more vegetated regions, the value goes to 0. And so this value, it's multiplied by the friction velocity, the U star, to come up with a modified U star S. We call that soil surface friction velocity. And then it actually goes to the dust emission equation, which is F sub D, to calculate the dust emission flux. And so this F effective, it's a function of the roughness of rock. We call that C0 rock. It actually comes from a small scale roughness length measurements from the satellite by Pigeon 2005. And this is different from the large scale aerodynamic roughness that you usually see on CLM because it really talks about the length scale of down to 1 meter or less. So we are really talking about the rocks and pebbles here. And then for the vegetation part, we're using LAI. So that quantifies the amount of vegetation roughness on the surface. And so combining these two, we will have a parameterization for the F effective, the drag partitioning effects. So this is the first modification. Another major modification is that we account for the planetary boundary layer turbulence. So as you see that most of the model has a really long time step of about half an hour. And so it won't be able to capture or resolve the instantaneous wind fluctuations down to a time scale of less than a minute to a minute or so. And so we need to put that into the dust emission scheme because it's really important, especially for the rural areas, semi-arid regions, or even high latitude regions, where they have a really high threshold wind speed value. And then over those rural areas, they have wind speed typically below the threshold wind speed value. But if you consider this turbulence effect, really instantaneous high frequency turbulent fluctuations, then there will be a lot of ups and downs and really episodic winds that can really occasionally sweep across the dust emission threshold value and actually generate some emissions over the high latitude or rural areas. And so this is what you can see from the left with model simulations without considering turbulence, and then to the right, models considering the turbulence effect. And the differences are really focusing over Canada, Russia, even the northern states of the US, Alaska. There are a lot more emissions because we are accounting for those really abrupt fluctuations of the winds, wind episodes. And those turbulent fluctuations are quantified by a form of similarity theory by Panofsky. So it really promotes emissions over semi-arid and high latitude regions. And so we talk about two modifications. There are more, but I cannot talk about all of them here. So I just want to summarize the final simulations results by showing you the emissions coming from CLM and dust AOD coming from CAM by, we are doing a land atmosphere coupling experiment here. So you can see the default scheme, which is Sander et al. Being the left-hand side column and the middle column being our study, our scheme. And I just want to highlight, we have a really smooth and spatially smoothed dust emission pattern. And we really get to show some emissions coming from the United States, for example. And then if you look at the dust AOD simulations in CAM, we removed some of the blobs or hotspots over Sudan, Australia, and China, for example. There are some regional problems, such as over Oman. We have some medium hotspots of AOD, high AOD values over there. We are trying to investigate why it is the case, whether it's due to input bias or we have some unknown dust emission mechanics that actually suppresses emissions over there, but we need to find out. And we just want to point out that our AOD simulations are really much closer to the Modus Aqua AOD image shown in the right. So yeah, and then we have some evaluations, again, different data sets. So such as AeroNet ground-based AOD observations. And again, we are showing we're doing a much better job right now capturing the spatial variability of the observations compared to Modus Aqua versus AeroNet. We actually have a very similar performance of about R-square of 80%. So compared to the default simulation of Sander in the middle column. Here, I just want to summarize some of the, briefly summarize the technical changes here. We have a pull request on GitHub 1897, so feel free to check it. We mostly modified our dust module in the Biogeochem directory, where we have the old and the new emission schemes there, and then users can really choose between them in the username list of CLM by specifying whether you want a new scheme, 2023, Learn 2023, or the old scheme, which is Sander 2003. And then we have provided a path for the small scale roughness lane file, and then it also specified the new scheme as default in the name list default. And then we have coded up a stream type module where we actually read in the small scale roughness length as a stream file, and we can regrid it to whatever resolutions we want in different model configurations. And then I just want to mention at the bottom, there are some other changes in progress. For example, we are moving the Sander source function and the global tuning factor from CAM to CLM. And so Francis Fitz is responsible for that. So there's a separate pull request there just a few days ago. And then I'll work on putting both of them into the CLM pretty soon. So for users that really care about dust simulations, aerosol simulations in CAM in general, they have to tune the amount of dust in the atmosphere, but now they need to do it in CLM instead of CAM. The last page before conclusion, this is the upcoming work that I'm working on. This is a new phase of AeroCom experiment, trying to investigate and improve the long-term dust trend modeling. So if you can see from the left-hand side panel, we have shown I've plotted the historical dust loading from CMIP 6 versus the dust reconstructions from ice core measurements, which is the black line. So the black line, which is the reconstruction, really shows a strong increase of 55% of global dust since the industrial period, so 1850s historically. And that corresponds to a radiative forcing of negative 0.07 watt per meter square. But this increase, it's really not shown in the historical CMIP 6 simulations. And we think it's because dust schemes are not really well coupled with human-induced changes, land use land cover change, desertification, and historical wind or soil moisture trends. And so the dust modelers are asking, why don't we take a step back and actually use some data-driven or top-down approach to generate some emission inventory and put it into global climate models. And so we have this AeroCom dust radiative forcing experiment proposed by my advisor, Jasper, as well as some European scientists. And then we are trying to implement historical, spatially and temporally varying gridded dust emission inventory.
Can you move to the conclusion slide, please? We're at time.
Excuse me?
We're at time, so can you move to your conclusion slide, please?
Yeah. So, so what's really relevant is to the CLM committee, it's really, we can decide between a process-based or data-driven approach. So this is a future capacity that we want to add in. Yeah, that's it. And thank you for your listening. I'll be happy to take questions.
We have one quick question. Otherwise, is there anyone online? No? Yeah, Eileen?
I was just wondering now that you have those emissions highlighted, does it depend on if there's snow on the ground?
Yeah, so we actually have considered snow cover in our CESM study. So you can see the middle panel, there are some highlights to emissions over there after considering the snow cover. So it's still quite some amount of dust emissions.
Great. Well, thanks, Danny. So we're going to move on to the next talk, which is by Meg Fowler, and she'll be telling us about modeling the effects of subgrid surface heterogeneity on the atmosphere and CSM. And we can get her talk. Great. Sorry, what?
Agree. Do it from memory.
Yeah. Great, thanks, Meg.
Okay, hopefully everyone can hear me okay. So for those who don't know me, my name is Meg Fowler. I'm a project scientist here in CGD. And what I want to talk today is not really about results from doing this, but more about ways we could think about how the atmosphere and the land could talk to each other a little bit better in reality. So when I think about the ways in which the land and the atmosphere interact with one another, I think one of the important things to keep in mind is that even small-scale differences in surface cover type can actually drive really important impacts on the atmosphere. So if you can consider a situation where you might have differences in surface cover, like having an agricultural center next to forest, grassland, urban area, all of those differences in roughness, length, moisture, and temperature help control where boundary layer cumulus clouds form, where precipitation occurs, and things like that. The way that this happens is really through the generation of mesoscale secondary circulations. So when you have those gradients in temperature and moisture at the surface, the atmosphere wants to equilibrate those. And it does so by setting up these kind of overturning secondary circulations to try and mix out those differences in moisture and temperature. There was a really interesting study out a few years ago from Jason Simon and his co-authors that ultimately looked at a really high-resolution atmospheric model and supplied it with a homogeneous surface. By that I mean every column of the atmosphere was forced by the same grid mean sensible and latent heat flux, and then also forced it with a heterogeneous surface. And so actually representing those fine scale differences in surface fluxes. What they found is that over a roughly 100-kilometer domain, those fine scale differences in fluxes, which occurred on the order of maybe a few to tens of kilometers, could actually impact liquid water path and turbulent kinetic energy when averaged over a 100-kilometer domain. So there's a difference in scale here that's occurring. Now, in climate models, that's really hard to represent, right? When we're communicating between the atmosphere and the land, we're still really relying on just grid mean fluxes. So from an atmospheric perspective, even though we have all this nice heterogeneity in our land models, the atmosphere is seeing a homogeneous surface. It's getting one mean, sensible, and latent heat flux. So moving beyond that is part of a climate process team Dave mentioned earlier called CLASP, which stands for the Coupling of Land and Atmospheric Subgrid Parameterizations. It's a pretty wide multi-institutional effort, and there's a lot of different kind of activities going on within it. But the ultimate goal is to move from the picture on the right to something more like the picture on the left in global climate models. I think this is a really exciting time to start thinking about how to do that, because both land and atmospheric models are beginning to have representations of subgrid scale heterogeneity. So within our land model in CESM, we have representations of heterogeneity going all the way down to the patch level, so different PFTs, different crop types. And practically the way that I think about this, and I'll discuss it today, is breaking down a grid cell based on how much area is covered by different surface types. So you can imagine kind of an idealized scenario where you might have 50% of the grid cell covered by irrigated area, 30% by forest, and 20% by urban. And of course, we don't know that it's contiguous like this, right? We know that it's a percentage. We don't know if it's all connected. But in theory, this is still useful information for the atmosphere to have. On the atmospheric side of things, I won't go too much into the details of CLUB itself. CLUB is the boundary layer and turbulence parameterization scheme that CAM uses. This is one of the main ways it represents heterogeneity. So CLUB basically gives you the variance and covariance of temperature, moisture, vertical velocity, third order moments of those, and a fourth order moment as well. But at the surface, the key thing to note is that CLUB estimates the temperature and moisture variances. We could think about maybe using that patch level information in CLM or CTSM to kind of tell CAM and CLUB what those variances actually should be. So that's one option, but I think there's an exciting alternative as well. So this has been a recent development within the atmospheric model working group to implement not just CLUB, but CLUB MF. MF stands for a mass flux scheme. And so you can think of CLUB as kind of handling small scale eddy diffusivity within the atmosphere, and then mass flux being more organized plumes. So you can have, say, 10 updraft plumes within a grid cell. And what these are doing is basically taking the energy and the moisture at the surface and fluxing it into the vertical in a more organized way than CLUB can do on its own. So the thing that I try and think about a lot is how can we actually link all of this information together? The land and the atmosphere have their own estimates of what's happening at a subgrid scale. And right now there's no communication between the two, but ideally there could be. So if we think about this CLUB MF framework and each of these plumes being initialized in a grid cell, right now what's happening is that the atmosphere is still thinking of things as homogeneous. So each of these 10 plumes within a grid cell is kind of being implemented or initiated with this same grid mean sensible and latent heat flux. But we know that we have more information than that within the land model. So we could think about, instead of just initiating these 10 updraft plumes randomly within the grid cell using the same fluxes, if maybe half of those plumes should be initiated with fluxes that are characteristic of an irrigated cropland, or maybe 30% should be irrigated or initiated then with forest fluxes and things like that. So what I'll propose is that we can initiate these plumes over actual subgrid patches that we have in the land model. In order to do that, we pass patch level data through the coupler to CAM. So this is information that already exists within CLM and CTSM. We have this kind of patch level flux information. It's really just adding an additional dimension to NUOPSI or CMAPS and kind of getting that over to the atmospheric model itself. Now, for testing purposes, what we're really doing is looking at single column SCAM experiments. So just a single atmospheric column initialized over the Arm Southern Great Plains site. So this is kind of legacy from a lot of what CLASP is doing. We're really focusing on the SGP site because it has so many observations and there's a lot of work being done there. What I'll show you is some results from warm season shallow convection days. And this is SCAM being run into 2-day hindcast mode. So ultimately, you run SCAM for 2 days, discard the first day for spin up, and look at the second day to see how the atmosphere is responding to the fact that there's a subgrid heterogeneity. We'll also caution you It's very preliminary results, so I think the model implementation is changing weekly, if not daily at this point. But I think there's really some encouraging signs here for an atmospheric response. So going back for a minute to the study from Jason Simon et al., which should be 2021, not 2019, when I mentioned that what they did was set up a large eddy simulation, so a high-resolution atmospheric model with either homogeneous or heterogeneous surface fluxes, this is kind of what I'm talking about. So this is a case study on September 24th, 2017, and this is a sensible heat flux at a really high-resolution domain, 100 by 100 kilometers at the Southern Great Plains site. So you have this center, which is cooler and wetter towards the east of the domain. It's surrounded by this warmer, drier patch. What in a heterogeneous case, you would actually be supplying the atmospheric model with this exact map. So it's seeing these differences in surface fluxes. In the homogeneous case, you're basically wiping out all of that heterogeneity and taking the mean over the whole domain and forcing every single column of the atmosphere with that homogeneous kind of surface flux. What they found then is that between a homogeneous case, which is your dashed line on the figure on the right, versus a heterogeneous case where you're actually giving that atmospheric model all of this cool information on sensible heat flux, your increasing liquid water path even averaged over the entire 100 by 100 kilometer domain. So it can have a pretty big impact on the atmosphere at the scale of about a grid cell. Now in our simulation, here again we're looking at just this one day, September 24th, 2017. In our control case, which is the black dashed line, this is using kind of the default CLUB-MF implementation. So it's assuming there's a homogeneous surface in a SCAM simulation, and liquid water path increases throughout the course of the day. You'll notice the magnitude on the y-axis is about a scale, about a factor of 10 off. There's reasons for that we don't have to get into. But what I think is really exciting is that when we add in heterogeneity in red, our CLASP simulation, we are seeing an increase in liquid water path and maybe a shift towards kind of an earlier peak liquid water path, which is consistent with what we saw in the LAS results. So again, it's not perfect. I wouldn't take this as an apples-to-apples comparison, but it is a sign that we're moving in a direction that's encouraging and that makes sense with what we're seeing in high-resolution modeling experiments. So there's ultimately a lot of room for additional development as well, which I want to highlight today. What I've done is pretty much the basic implementation of not changing the infrastructure in CLUB-MF or in CLM, but just kind of allocating our updraft plumes according to surface tiles. There's also options to update the updraft area and vertical velocity. So this is work also that's come out of CLASP and has been spearheaded by Khaled Ghanem out at Princeton GFDL. What he's found is that when you're trying to basically inform the atmosphere of subgrid heterogeneity, one of the really effective ways of doing that is changing how wide and how strong your updrafts are as a result of those surface characteristics. What I think is maybe more important to note for this group is that I think this also opens the door for communicating information from the atmosphere back down to the land model. So if we have all these updraft plumes within CAM, each plume has information on precipitation, cloud cover, wind speeds, downdrafts, and now we're kind of linking those plumes to an individual surface patch. So we could start thinking about taking that information from the atmospheric model and conveying it back down to the land model for something that's maybe useful and informative at a subgrid scale. So there's definitely more development I think we need to do, and it's very preliminary, but I think we're almost at a point where we can move beyond treating the surface as homogeneous from an atmospheric perspective, and at a point where we can get some interesting subgrid information from the atmosphere back down to the land. So thanks for your time.
Great, thanks, Meg. We've got time for some questions if people need someone online. Yep.
Yeah, Danny, can you unmute yourself and ask a question?
Sorry, I just pressed it wrong. I just want to give some reactions.
Ah. All right, thanks. Yep.
I can.
Oh, yep, Alan?
I was just wondering if using SCAM, where you're very constrained by the moisture transports, do you think that might be obscuring some differences?
It could be some of what's happening. So I am using the same large-scale forcing, which is nice. It's just kind of coarse inversion for SCAM compared to what they were using in the LES. But I think one of the big things is that they're forcing their LES with a really high-resolution land model. So they're getting all of this subgrid scale storm activity happening, and that's driving a lot of the differences that we're just not representing in SCAM. Yeah, I think that's a big thing.
Great. Well, thanks, Meg. Yeah, that's great. Eric, you can come down and we'll get you all set up. So next
next up we have Eric Kluzak, who's going to be talking on simple land model software as a new component of CSM. Do you need some help with this one, or you got it?
Well,
maybe?
find my
Should be.
right now?
Willard.
Send a message just to everybody who's online, let them know where.
I did send a chat, yeah.
Oh, this isn't gonna work. The
Because your duo is not.
Yeah, the duo isn't gonna work, so.
You just go on. You would talk without slides.
Usually you need to call your.
You swap
As
the
I said,
two talks?
Yeah,
Well,
it's a good
is Yishin online?
No, here.
Oh, yeah, there you are, okay.
Alright, let's do that.
Yeah.
Can you just go on the dates on your phone?
Well, the wireless isn't working though, so.
But
so
if you're on the
cellular network.
5G, whatever, we're on there.
Oh,
My phone doesn't work in the building.
Oh yeah, it doesn't work in this room. I guess you have to go ahead.
oh, okay, right. Well, I can use my computer. Oh, whoops, let me give you the.
See all of it then?
Okay.
Okay, Yishin. On your collar. Right. Let's turn it on. Okay, everyone, so sorry for the interruption, the technical problems we just had. We're going to skip over Eric's talk for now, and Yishin John will be giving us a talk on the effects of forest in dampening the diurnal cycle on land-atmosphere interaction. Yishin, you.
Hello, everyone. I'm Yixin Zhang. I'm from National Taiwan University, and I'm visiting a PhD student this year, and I work with Sean Swanson. And today I would like to discuss with you about our preliminary result about this topic. A lot of people in the morning present about the important role about the forest, and the critical role about the forest. We can. There's a lot of previous study, like due to the evapotranspiration, the forest decrease the surface temperature. You can see the left figure. You can find out the surface temperature in the forest region is quite cooler than other regions. And also the cloud cover increases over the large and uniform forest region through the radiative moistening, dynamic, and some biogeochemical process. Just like the right figure, above the forest, the cloud frequency is higher than other regions. So we would like to focus on the time scale in the diurnal cycle. So we separate to the daytime and the nighttime. So first about the daytime. About the cooling effect is dominated by the competing effect between evapotranspiration and albedos. And this mechanism dominate the spatial changes of the cooling effect by forest. And you can see the figures. In their study, they use the satellite observation about the surface temperature, and they use the subgrid data and to calculate the difference with the open field and the forest field. So the value represent the cooling effect of the forest. So we can find out in the tropical forest region, the cooling effect is quite significant. And move to the nighttime. There's a warming effect on the in the forest regions. The roughness of the forest will generate the turbulence in a stable atmosphere. So it makes the atmosphere well and to warmer the temperature. Besides, the biomass in the forest will receive the net radiation during the daytime and release back the heat to the atmosphere during nighttime. So like this vertical temperature in the forest, and axis represent the biomass temperature. During the daytime, the temperature in the forest will increase. And during to move to the nighttime, when the temperature cooling down, the heat in the forest will go back to the atmosphere to heat up the atmosphere above the forest. So in the same study, they also calculate the difference during nighttime. So we can find out the warming effect of the forest during the nighttime is really significant globally. But we can find out the dash regions. There's no value in the Amazon and Borneo, those rainforest regions. So the dino-dependent effect of the forest is really hard to reveal by satellite observation with only just 2 time slot, like the maximum temperature and the minimum temperature, especially in the dense and the giant rainforest region. Especially in this region, the biomass heat storage might dominate a lot more than other regions. So we would like to use the field observation data and the model simulation to answer our scientific question. How does the asymmetric impact of the forest on the diurnal temperature cycle affect land-atmosphere interactions? So first, we would like to introduce our paired study site. So in Taiwan, we have 2 sites. One is open site and above on the open field. And horizontally 300 meters away from the open site, there's a flux tower. So we would like to compare the diurnal cycle between these paired stations. So the right-hand side is the diurnal cycle of the air temperature, and the dashed line represents the daily mean, and the green line represents the air temperature above the forest, and orange line represents in the open field. So we can find out the daily mean is quite similar in these 2 sites, but the diurnal range is quite different. So we can focus on the daytime. There's a significant cooling effect above the forest and the warming effect during nighttime. So this highlights 2 points. The first one is just a tiny open field in a comparatively large and uniform forest could create substantial spatial variation of the diurnal cycle. And the forest moderate the diurnal temperature range really significantly. So next, we try to determine the dampening effect of the forest by the biomass heat storage use CTSM 5.1. We try to turn on and turn off the biomass heat storage process in our experiments. So in the figure, the dashed line represents when we turn off the biomass heat storage process, and the solid line represents we turn on the biomass heat storage. So we can see the left figures. We can find out the latent heat and sensible heat both decreases when we turn on the biomass heat storage. It's because of you can see the green line represent the diurnal cycle of the biomass storage. So during the daytime, the heat flux redistributions, because more of the net radiation will store in the biomass. So the latent heat and sensible heat will be overestimate if we didn't consider the biomass heat storage in the daytime. And during nighttime, we can see the right figures. If we consider the biomass heat storage, we can see that there's a significant warming effect during the nighttime. So next, we also separate the latent heat flux to each component. We can find out no matter the transpiration, canopy evaporation, and ground evaporation will will decrease during the daytime. And during the nighttime, the canopy evaporation will decrease. That represent maybe the dew in the nighttime will decrease. So go back to the take-home message for today and our ongoing work. And first is about our field observation. Is just a tiny deforestation area in a relative large forest could also generate a local near-surface microclimate difference. So this tells us just a tiny habitat fragment as well increase really dangerous to the ecosystem. And our next scientific question will be how does the temperature of the atmosphere bottom layer change as the area of deforestation increases, just like this schematic plot. And for now, the study site, there's a just tiny little deforestation area. So we can find out there's a lot of difference near surface temperature, but this may not affect the bottom layer of the atmosphere. So if the deforestation area increase, will it affect the boundary layer temperature or another heat flux? So our next step would like to use the air-drone observation to detect how the vertical structure affected by the open field. And another one, we want to use the single column couple model to figure out these questions. And the second part of the take-home message is if we didn't consider the biomass heat storage, the latent heat and sensible heat might be overestimated in the daytime. And the changes in the diurnal temperature range after deforestation might be larger than we thought before. So following Mir et al. Study, they also used the COM 4.5 to try to figure out the effect of the biomass heat storage. So they find out if we consider the biomass heat storage, the daily maxima will be cooler, and the daily minima will be warmer. So we would like to follow this work and try to use the couple model like a CESM to figure out this biomass heat storage. If we consider about this process, the land atmosphere interaction or local circulation, or the forest respiration, what would happen if we didn't consider or if we consider about this process. So this outgoing work is just our initial thought. So we are open for any suggestion and question for now. And thanks. And this is my presentation for today.
Thanks, Yishin. Do we have any questions? Oh, yeah. Chris?
How much the biomass heat storage depends on the type of the canopy structure and the type of the leaves? Is that included in the model?
In the model, I think the most of dominated by the stem and the branch, but the leaf is quite smaller than other biomass amount. Yeah.
Does that include bulk water content as well? I would think that would matter a lot.
Oh yeah, that's a good question. For now, the model just consider about the biomass effect, but in the field observation, we also measure the latent heat storage and sensible heat storage. And we also find out the similar diurnal pattern, but we didn't compare the amount between the biomass, sensible heat, and latent heat storage. So we will compare that in a future work. Yeah, thank you for your question.
Oh yeah.
Joshua, so I'm afraid I didn't follow one thing in your presentation. When you're talking about the small clear cut or small opening having a big effect on climate, is that only for that hole in the canopy, or is it for the whole canopy? Or for that whole area? Does it also change the temperature for the forested areas that are near the?
Oh, you mean other parameter will change or?
No, I'm basically saying, like, if you have a big difference between a place where the trees are removed.
Yeah.
Is that just locally, or does it affect the temperature of the trees next to that area?
Oh, you mean the open field?
Yeah, is there effects adjacent to the open field, or is it just in the open field where you see the differences?
Just in the open field. Yeah.
Great, well, thank you, Yishin.
Thank you.
Eric, do you think we can get your talk to work?
Yeah.
See if I can share it. But we do have enough time to, still have enough time. So. We've got a break at 2:45.
Oh, okay.
Yeah, that isn't one.
Yeah, I changed it, so if you have the link. Yeah, there we go, okay.
Well, thanks, Eric. Eric, we're talking about simple land model software as a new component in CSM.
Okay.
There we go. Oh, that sounds better. Thank you, Meg. Okay. All right. SLIM. Marisa Legou was one of the winners of the Drew Slater Award for working with SLIM, which is a simple land interface model based on CLM 5.0 code to study land-atmosphere interactions. And she's done papers and presentations in her work. Here I'm going to concentrate on the software part of it. But we're going to give a little bit of motivation. So why SLIM? You know, in terrestrial science, it's a simple model to understand basic land in atmosphere interactions. It allows you to change basic surface properties without it being connected to a complex surface physics model or ecosystem model. And so you can do idealized experiments to understand these interactions. So what we found out is that atmosphere science people are interested in this as well for reasons like this, for paleo work, for upper atmosphere CSM, where the land surface isn't critical, which of course is taboo in this setting. Other planets, they're looking at this for Mars and that kind of work. So there's kind of some cool things happen. So what is SLIM? It's the main thing is simple to understand interactions without the complexity that an ecosystem model has. There's no exchange of things like CO2 or VOCs from the surface or dry deposition. There's no connection to a river model or a glacier model. There's no impact of the solar angle on land albedo. And it has a simple bucket model for the soil. So, and it's essentially a land model similar to what was used 50 years ago. So we're going back in time in a way. In the surface data set, it's characterized by, there's 23 different surface characteristics for it, whereas CTSM has over 80. And there's no subgrid heterogeneity, it's only over the grid cell. And commonly what happens is that these come from CLM simulations. So you'll run a CLM simulation and then average surface characteristic for 1850, for example, and then you run SLIM with that. And then you might modify, some of that. So over grids, single grid cells or large paths or large parts of the grid to see what we can change. So it includes things like the albedos and roughness, emissivity, snow mask, dust emission, and simple soil description. So the starting point of SLIM is the CTSM code base, which is a problem because it's large and most of it's not needed for the simple land model. But it was a good place to start with for Marisa because it was fully coupled to CSM and it was already working, and she just had to change out the guts of CTSM to have a simple land model. So, but you're starting with a code base of 440K lines of code, bunch of unneeded externals. There's all these name list items, all these XML options, and just lots of unneeded complexity. So, in removing that complexity hasn't been easy, and that's just because of CTSM is complex, and it's been hard to deal with that. So the solution is that we want to put SLIM on a diet, an exercise regimen, and slim down. So we have an exercise montage for SLIM. So the first tag was SLIM was 190,000 lines. So that's reduced from the 440 at least. But there's like 7 XML variables, over 900 name list options. And so we put SLIM out like Rocky, and we start working towards a leaner version of SLIM. And so the most recent thing we have is 41,000 lines of code, which is about the expected BMI for this code. I was kind of predicting how much we needed, and I was thinking it was like 47,000, and Sam Levis was able to get it down even thinner than that, so that's really awesome. So there's only 2 XML variables, and then there's about a dozen name list items. So it's much easier. We're working on updating it to the CSM 2.3. We have a working, simpler name list build based on Python instead of Perl, so that should make Ryan happy. So victory is close, I guess. We're still not quite there, but we're close. So developing process for SLIM, there was, it was a personal repository. Now it's part of ESComp. So there was a single contributor, Marisa, and now there's multiple contributors. We developed a test list to ensure we have correct answers. We developed a tag naming convention. We are added as an option to seam for SLIM, and we've worked out a process of becoming a component of CESM. And then also for it, we figured out the process for it to become into CSM development tags. So summary is that SLIM is available on ESComp. We're finishing up the work for it. We plan on having it generally available for use in the spring. We plan for it to be part of CSM tags when that happens, and possibly will be part of CAM tags as well. So, thanks.
Well, thanks, Eric. We've got some time for a couple of questions before. Oh, here we go. Daniel?
Just a process level question. I'm curious, Marisa had this as part of her PhD project.
Yeah.
How did the funding come around to get you and Sam, et cetera, working on this and involved? Yeah.
Isla.
Yeah, so we had Karen McKinnon and I wrote an NSF4 grant, and we were able to get, the only funding we could get to come here was software engineering resources, because we wanted to use SLIM. So that's how we got the first part, and then there's been some more through this NSF cyber infrastructure coupled idealized modeling grant, because that's to make coupled idealized models, and then if you want to set up your land in those models with CLM, it's very complicated, whereas this will be much easier for coupled idealized modelers to use.
Great.
Yeah, awesome.
Joshua?
So if I'm understanding, this is a hard fork where you threw everything out of CTSM, like they're permanently gone, right?
Yeah.
But there's still some shared code base there. So is there an intention to try to keep those things synchronized in some sort of way, or is that even useful, or is it just now that it's on its own, as its own repository, it's going to go off and live in its own special world?
We think it's going to live in its own special boat. So there is some duplicated code, but we think it's susceptible. So there's the history module is largely duplicated, and so one thing we might be able to do is if we have changes in the history module in CTSM, we might be able to port them over to SLIM a little easier because it has that shared history. But largely, there's not enough duplication that I think we're concerned about it. I think it'll be okay on its own. Yeah. So good question, yeah.
This is, I guess, maybe a question for both you and Isla, but she was talking about, it seems like from her results that the changes in VPD are driven by too much water coming from the land. Could you use SLIM to kind of evaluate that hypothesis to say, okay, if we change something about water fluxes in SLIM,
I guess you could.
First you have to replicate the patterns.
Yeah, right.
But then could you use it to test the hypothesis also?
I think that might be true.
Yeah, I mean, I feel like one thing to do is just to see what do you have to do to push the model to get it, and if you make no water availability, it like you could do in SLIM, can you even get it? I'm not even sure you could because of maybe the transports are
too much.
But I think it would be good to mess around with SLIM and see what you can do.
Yeah, that's a good example use. Yeah.
Great. Oh, me.
Adrian has a question online.
I don't know if Adrian can unmute.
Okay.
Yeah, sorry. Thanks a lot, Eric, for this presentation. It looks really cool. I just wanted to know, like, how far are you in developing Slim? Like, for example, can I use a regional grid instead of a traditional global grid, or it's still not it's still not, you still didn't code this part of the software?
It's been developed only with 1 degree and, and 1 degree and 2 degree grids. And we know that works. And recently Sam has tried it with some low resolution grids, and that actually works. It doesn't currently work with a single point, but with some of this work with a lower resolution, we might be able to get it to work. A lot of the infrastructure for different grids is actually in the coupler, and so it's actually possible that some of the more fancy CAM grids might work with Slim. So I'm not quite sure, but I think the answer might be yes for some of that.
Variable resolution Slim. Yeah. Marissa's got,
She's excited. She's excited to.
Oh, Marissa's excited. Yes, awesome.
She said she already ran it without evaporation.
Oh.
Oh.
Okay.
Oh, she
What the
did.
comment says. Yeah.
That's way too
She
far
said she'll
away.
go back and look at them again.
Okay.
Okay. You want to do without evaporation in particular places, right? Because if you do without it everywhere, everything gets screwed up. So, I just a comment. I think, I hadn't thought about the exoplanet or whatever, the different planets option, but feels like we need to communicate then, when this is ready, we have to find a way to communicate with that community that would just interact with us that much, but it does exist out there, so. Just something to put onto the.
Eric went to a CAM meeting and presented this stuff, and they were, it's like, I don't remember who it was.
Dan Marsh.
Yeah, Dan Marsh was super.
Oh, cool, so there's some
But
connection.
it's on their radar, like Dan was one of the most enthusiastic people thinking about this.
I was gonna say, we run it for Snowball Earth also.
Oh, okay.
And Marissa did worked with some exoplanet people as well.
Oh, she has. Oh, okay. Awesome.
Cool.
Well, great. So that ends the session. We have a break until 3:15. Is there coffee?
There should be more
Still
snacks,
coffee?
yep.
Snacks? So be back. We'll be doing vegetation for the final part of this afternoon.
Thanks.
Can you start your presentation from the beginning,
Yeah.
please?
This is the first page, right?
Yeah, we're not seeing your first slide.
Oh, really? Now?
There you go. Yep, thank you.
Okay. So should I start my presentation now?
Yeah, Jody, please do start. So Jody Singh will be our first presentation after the break, improving ozone damage parameterizations in CLM5. Thanks, Jody.
Thanks. Hello, everyone. This is the presentation is on the topic improving ozone damage parameterization CLM5, and I'd like to acknowledge my collaborators, Danica from NCAR, Ella, Lily, and Alan from Rutgers. Why ozone damage on plants is important in CLM5 is basically ozone is a toxic gas, and in this figure, I'm showing how ozone is formed in troposphere. Basically, it's a photochemical reaction where NOx, sulfate, VOCs, BVOCs, they react with sunlight and they form ozone. And this ozone is taken by the stomata in plants, and when it enters through the stomata in substomatal cavities, it because of the short lifetime of ozone O3, it creates reactive oxygen species which further reacts with cell membrane and damages it, and it also leads to metabolism dysfunction, leading to reduced net photosynthesis and stomatal conductance, which basically results into reduced carbon assimilation, and also it might also lead to, sorry, there's something. This might also lead to then cell death, which is visible in form of injuries in the plants. So ozone damage parameterization in CLM5 is basically incorporated directly and independently influenced by photosynthesis and stomatal conductance based on the cumulative uptake of ozone. CO is a function of stomatal conductance of plant, ozone concentration in the air, and total duration through which the plant is exposed to the ozone. In CLM5, the damage function is for three broad PFTs: broadleaf trees, needle-leaf trees, and crops. So in this study, what we are trying to do is we are trying to improve the ozone damage function and also trying to extend the PFTs for more PFT types, for example, wheat, rice, soybean, tropical evergreen trees, and also seafood crops. So basically, in the current ozone damage parameterization was implemented by Danica. She gathered data from 1970 to 2011. Those experimental data, they saw how chronic ozone was impacting stomatal conductance and photosynthesis. So this is basically how she collected the data. These are the categories and levels describing the data. So for example, this is the category: plant type, crop type, control air, and these are the categorical levels of these categories. I will not go into detail. If you want more detail, you can go to to Danica's paper. And we have now a total of 235 papers from 1972 till now. And in these 235 papers, there are almost 1,600 data points. So the next analysis is based on those data. In this analysis, I'm just trying to replicate what Danica did in her paper to see if these added data do improve the ozone damage function in any way or not. So the first row is for change in photosynthesis value under chronic ozone exposure as percent of control experiment, and the first column is for all crops, and the second, third, and fourth column is for the crop categories, that is wheat, soybean, and rice. The second row is basically a correlation between cumulative ozone uptake and change in stomatal conductance value. So as you can see, on every plot, there is value. The first line is the regression equation. The second is the R square, and the third one is the number of data points used to do the correlation analysis, regression analysis. So as there we I couldn't find any like meaningful correlation between cumulative ozone uptake and both change in photosynthesis and stomatal conductance under ozone exposure. And this finding is in line with what Danica found in her paper. Most of the categories there was no strong correlation. There was very weak correlation, or either if the correlation was there, it was not significant for most of the categories. And this is also what I'm finding. So I also extended this analysis for tree category, and all the tree not all the tree types, but tree types that had a significant number of data points, which is temperate, deciduous, evergreen, temperate evergreen, and tropical evergreen. Again, I did not found any significant correlation except for tropical evergreen, which is also a new category. We found this data was mostly after 2011, but in other categories there was no significant correlation. So what I thought, what if I change the predictable uh, predicting variable from cumulative ozone uptake to ozone concentration? Do I see any improvement in the correlation between change in photosynthesis and ozone concentration? I found some improvement in correlation, but again especially for rice and soybean, there is some improvement correlation. Now the correlation is 0.25 and 0.3 for change in photosynthesis. Not very significant improvement for stomatal conductance. So there is something missing. Like ozone concentration and cumulative ozone uptake alone are not able to predict especially the variance in the response data, which is change in photosynthesis and stomatal conductance through the independent predictor data. So what might be the reason, I thought, and then I thought uh, how there is a so cumulative ozone uptake is not measured in a lot of experiments. Some experiments did measure the cumulative ozone uptake, but for most of the experiments, I think maybe more than 80%, cumulative ozone uptake is a calculated value. So CO calculation is directly proportional to stomatal conductance of plant control stomatal conductance on the plant's ozone concentration and total exposure time. However, it's a I mean, a plant can have similar CO values for various conditions. For example, if a plant is exposed to lower ozone concentration but for a longer duration of time, high ozone concentration but for a shorter duration of time. So in both conditions, if the plant has similar stomatal conductance, CO values can be same, but the condition is not same. And in third, for example, the plant is exposed to high ozone concentration for a longer duration of time, but it's a different crop, different plant, which has a low stomatal conductance value. Again, these three experiments might have same cumulative ozone uptake value, but the experimental settings will be different. So this might be a reason that CEO is not basically able to capture the variance in response data, because it is not able to exhibit what is the underlying experimental conditions. So to analyze this hypothesis, what I did, I tried to do principal component analysis on the whole experimental data set for crop, specifically this for crop category. And the motivation behind this was to find a trend in data, if there is, and if there is any trend also in the predictive variables. So here I am taking the predictive variables, cumulative ozone uptake, and all the independent variables which are used in deriving cumulative ozone uptake. So it will be CuO, control stomatal conductance, ozone concentration, and time. So here the first figure is principal component analysis, and we have 4 principal components here, and the first 3 principal components are able to explain almost 95% of the variance in the data. And the figure on the right side is showing what is the contribution of each predictor variables in each principal component. On x-axis there are principal components. On y-axis there is the predictor variables. So if you see here, the colors are different because the red color is basically for the variables which have positive correlation. Blue shows they have negative correlation, and the gray rectangles here are showing the variables which are dominating the, which are contributing dominantly in the principal component. So in principal component 1, cumulative ozone uptake is dominating, but in principal component 2, ozone concentration is dominating or explaining the principal component. Similarly, likewise in principal component 3, time is dominating it. So there was again one question: what if the trend in this data is because of different crop types? Because this data is for all the crops. So I also did principal component analysis separately for wheat, just to see if this variation is coming because of different crops. But again, for wheat as well, there are the 99% of variance in the data is explained by first 3 principal components. And again, the principal components in the dominating predictor variables are different. They're not just CO, they are different. In some it is CO, for some it's ozone concentration, for some it's time. So it becomes very important if we want to capture the how chronic ozone exposure is damaging the plant. We need to do an analysis in which weight of these variables is taken into account. So this is what I tried to do in the next slides. So this is the regression for change in photosynthesis due to chronic ozone exposure for rice. The first plot here shows the correlation regression analysis between CUO and change in photosynthesis, which you also saw in the previous slides. And as expected, the correlation is really poor. And it's also not significant here. It is R squared. This is root mean square error, and the last one is statistical significance. And so I added ozone concentration in the predictor variable, and to my surprise, the correlation was now 0.649. I mean, from 0.015 to 0.649. It is like very significant and very good correlation. And root mean square error also decreased. Now, another thing was, what if, because CuO is calculated based on ozone concentration, stomatal conductance, and time. So instead of CuO, what if I take these 3 independent variables and try to draw a correlation, try to do a regression analysis and see how it works. And the correlation coefficient is improved again. It means that the problem of cumulative ozone uptake is not able to capture the variance of the data. So and root mean square error is less than the regression where the predictive variable is only cumulative ozone uptake. But in the last plot, I took all the predictive variables: cumulative ozone uptake, ozone concentration, stomatal conductance, and time, and it has the best correlation with the response variable, which is change in photosynthesis, and root mean square error is also reduced. The similar kind of similar kind of analysis was done for change in stomatal conductance, and the same thing was found, that the correlation coefficient increased and root mean square error decreased. So so the basic main takeaway from this study would be cumulative ozone uptake alone, or any most of the models, what they do, they try to see how ozone is damaging the plants through deriving a correlation between any ozone concentration metric. So I think the main takeaway is any ozone concentration metric alone won't be able to capture the damage on plants. So what I found in my study was CuO combined with controlled stomatal conductance, ozone, and time explained the ozone damage significantly. And also that the predictive variables interact differently for different crop types. So it's also important to have different parameterization schemes for different crop types. The next step in this study is to add and test the new and improved ozone parameterization in CLM5, and also add the parameterization for new PFTs which are not there: wheat, rice, soybean, tropical evergreen trees, and seafood crops in CLM5. So that's my presentation.
I will take any questions if there is.
Thanks, Judy. Do we have any questions in the room? Okay, anyone online? No? Okay. Well, Judy, thanks so much. We'll move on to the next talk. Looks like great work. Okay, so next up.
Hang on, Nick. Nick,
Nick?
can you unlock this computer for us?
So
I guess our next, Nick, it maybe doesn't matter now because our next talk is online.
Oh, yeah. Okay. So, you're ready to go? Are you going to share your screen? Is that right?
Yes. Can you hear me?
Yes, you're coming through perfectly. This Xiaolu Li will be giving a talk on characterizing leaf phenology of different vegetation types from local to hemispheric scale in CLM. Thanks, Shelley.
Hi. Hi, everyone. Oh, can you see my screen all right and hear me all right?
Yes, you're coming through perfectly.
Okay. Yeah, thanks for confirming that. So hello, everyone. Thank you so much for the opportunity. My name is Grace. This work is based on my postdoc work at Cornell University, and I'm now transitioning into a new postdoc position at Penn State. So here we are mostly interested in plant functional type level comparisons of phenology from a local to hemispheric scale. So first, you may ask, why should we care about phenology? Well, phenology measures the time of biological events and forces that cause their variations. It's one of the most visible indicator of seasonal transitions and also of climate change impacts on ecosystems. It's important in natural ecosystems for pollination, migration, and human health. And then it's also very important in climate models because phenology regulates land-atmosphere interactions. In a previous study, we found that the timing of plant phenophase change alone would influence boundary layer dynamics through both direct influence on energy and water exchange, and also indirectly change cloud feedback and cloud cover, and therefore cloud feedback and albedo. And then also phenology influences primary production and therefore the carbon cycle through both modulating growing season and leaf development, and potentially influence ecosystem structure and functions. And probably not surprising to this group, land surface models differ a lot in their RAI simulations. So here on the right-hand side, you are seeing historical RAI simulations from 7 CMIP6 models at the same grid point. And then the left-hand side are showing the RAI from the same grid point from remote sensing records. So as you can see, models differ a lot in their RAI simulations. So the good news is none of the 7 model is CRM5, but then the bad news is, however, we still found large differences between between RAI simulated by CRM and those derived and RAI estimates derived from remote sensing records. And then previously we've done grid cell averages. We've compared grid cell averages, and what we found is that different plant functional types differ a lot in their RAI simulation, and the grid cell average may not show may not tell the full story. So here, each colored line is showing RAI simulation from the same grid point for different plant functional types, and then the black line is showing the grid cell average that we see as a grid cell level output. And this has caused large differences also in GPP estimations. So therefore, here we are mostly interested in across plant functional types, how well can CRM simulate RAI variabilities, and then how sensitive are the results to environmental factors like temperature and soil moisture, and then how may these disagreements influence how influence GPP simulations. So we've run both CRM 4.5 and CRM 4.0 with JSWP3 historical forcing, and then we also use MODIS RAI for comparison. So I'm going to present a few sets of indicators. So first of all is the RAI ratio, which measures how well RAI amplitudes agree between CRM and remote sensing records. And then the RAI threshold-based day-of-year records is a measurement of spring onset timing in a wave seasonal circle, and is measured by day of the year when RAI reaches its 50% threshold of its annual dynamical range. And then we also developed a overall seasonal ratio that's measured by the RMSE between normalized CRM and MODIS RAIs. So as you can see in the red box, it measures how well the seasonal circle agrees between CRM and MODIS RAI. And then we also, to measure the phenology-induced GPP differences, we also calculated GPP simulated by CRM, drawing the difference window between CRM and MODIS peak growing season. So we are not using MODIS GPP here, but it's CRM GPP that's produced, drawing the difference in the peak growing season. And so this is just to show you how this looks like at a hemispheric scale. And then we calculated each of these indicators at each grid point for each plant functional type. But I'm going to show you more summarized results so here we are showing the RAI ratio and the seasonal ratio. So on the x-axis, it's showing the log RAI ratio. So just to remind you, when log RAI ratio is close to 0, it means that CRM and MODIS RAI amplitude agrees with each other. So a negative number means CRM underestimates RAI, and a positive number means CRM overestimates RAI compared to MODIS. And then for the seasonal ratio, a lower value means a better agreement between CRM and MODIS RAI seasonal circle. So from the first look of it, overall, across all the plant functional types, we see best agreement between CRM and MODIS in area amplitude and seasonal circle in seasonal deciduous plant functional types. And then if you compare 4.5 to 5, then CRM clearly improves in its area amplitude simulation. However, you can see that there are larger disagreements between the seasonal circles, especially for some evergreen and stress deciduous plant functional types. And then, so here is to show that how the different ratios looks for different plant functional types, and then also how they are influenced by temperature and soil moisture. So here on the x-axis are showing the different plant functional types divided by their phenology types, and then the y-axis here is showing mean spring temperature. And I should mention that the results are largely the same, even if we are using mean annual temperature. So, first of all, as you can see, so here the upper panels are showing the RAI ratio, so how well CRM and MODIS RAI agrees with each other, and then the lower panel is showing RAI is showing phenology-induced difference in GPP simulation. And I'm putting those two together on this slide because first of all, they are largely determined by the plant functional type, but then also especially for plants in colder regions, both RAI ratio and GPP GPP bias improves with higher temperature in the colder regions. And then it's in a way still the same for only spring onset simulations. So if you look at the two lower panels here, the correlations between the correlations between day of the year when spring onset happens in CRM and MODIS is better in colder regions. Is better in colder regions. However, if you look at the two upper panels, what you will see is that how well the seasonal circle agrees between CRM and MODIS mostly only depends on the plant functional type and is less influenced by temperature. It's for soil moisture though, what we have found is that CRM5 is generally wetter than both CRM 4.5 and then also reanalysis from NRDS. So and then what you would imagine is that we see less sensitive of the indicators to soil moisture in CRM5 than CRM 4.5. And then, but here on the y-axis, it's still is showing mean spring soil moisture. And then, as you can see, it's still the indicators largely depends on the plant functional type. And then the estimations improves a little bit when you have a higher soil moisture, but it's much less sensitive in CRM 4. In CRM 5.0 than in CRM 4.5. And then for the seasonal indicators, as you can see here, how well CRM and MODIS seasonality agrees mostly only depends on the plant functional type and is little influenced by soil moisture. And then, so we've taken a closer look into the GPP differences induced by phenology disagreements, and I want to draw your attention to the green-blue regions in the two red boxes. So as you can see, different PFTs differs in the phenology-induced biases in GPP, and then for some plant functional types, the bias is actually negative, and then in the same region for other, so as you can see here, especially in evergreen plant functional types, and then also in some stress deciduous plant functional types. And what that happens is if you look at the grid cell average, because there may be both negative and positive values, the results might cancel out, and therefore you see a overall better estimation. But we also looked into what happens at the evergreen size using flux tower measurements. So here, the left panels are showing the comparisons between RAIs, and then the green rectangles are the flux tower measurements, and then the black dots are MODIS measurements, are MODIS estimations. And then the right-hand panels are the GPP estimations. So as you can see, so first of all, even though there might be larger differences in RAI estimations, overall, the bias in GPP estimations is smaller than those we see in RAI. However, the mismatch in RAI seasonality also changes into GPP, also reflects in GPP estimations, but as you can see, there might be a decouple between GPP and RAI simulations, especially in evergreen plant functional types. Therefore, in conclusion, we see the best agreements in seasonal deciduous PFTs and especially deciduous broadleaf trees, and then area amplitudes are sensitive to environmental factors, but area seasonal circle are mostly determined only by the phenology scheme. And then CRM can display large cross PFT variations. And therefore, the grid cell averages may not be telling the entire story. And then there are smaller biases in GPP than RAI, but they may be decoupled, especially at some of the evergreen sites. And then with that, thank you for your attention. And I'd also like to thank my collaborators and the NSF for funding this research, and I'm happy to take any questions.
Thank you, Grace. That was great. Do you have any questions in the room?
I have a question.
Yeah, Ryan?
That was a great talk. Thanks, Grace. I was curious about the MODIS product and the LAI that comes from it. And I know back in the day, MODIS had a lot of passive measurements, and you wouldn't be able to really penetrate a canopy and see what's in the understory. But are there corrections these days? Are there, I guess I'm asking, what is your error bar that you place on MODIS for LAI?
It's definitely very high, and then also especially, so we had a discussion about this. So we think, especially a lot of the differences we see in over evergreen plant functional types may actually be attributed to MODIS uncertainties, MODIS area uncertainties. So, but we but we do have comparisons at flux tower sites between MODIS and the flux tower site measurements, and a lot of MODIS area is tracking GPPR pigment rather than the actual area changes. So yeah, that's definitely an uncertainty. Does that answer your question?
Yeah, definitely. Thank you.
Okay, well, thanks, Grace. We'll move on to the next talk now, and I think it's just another, oh no, it's not, it's in the room. Yeah, great. Lafu, yep. She'll be giving us a talk on responses under climate change. And oh, we need to unlock the computer. Great. Yeah, okay. Thanks.
Okay. Hi, everyone. Thank you for having me here. My name is Ayala Lu. I am a PhD student at Columbia University under Pierre Gentine's lab. And today I wanted to show some of our work on modeling leaf phenology under global climate change. So this project is mostly still in the development phase, but I was thinking to perhaps share it with you guys, and also I would love to get your insight on how to go on with it. So the previous presenter just did a great explanation on the motivation behind modeling leaf phenology, so I won't go that much into details about it. But yeah, leaf phenology is one of the main indicators of climate change nowadays. It has a great control of our carbon uptake. So modeling leaf phenology can help us have a better understanding of the impacts for predicting the future state of ecosystems, including changes in species composition, productivity, and carbon upcycling. And also, one of the main importances of this project is that leaf phenology at the end is pretty difficult to predict because of the wide variety of biotic factors that go in play, as well as abiotic factors that we cannot observe. However, the main goal of this project is to predict the interannual variability of leaf out and senescence across different climate regimes. So I wanted to talk a little bit about the drivers of leaf phenology. There are multiple drivers, as I have just mentioned, but temperature, precipitation, air humidity, and photoperiod are usually considered some of the main drivers of leaf phenology. Temperature specifically has been one of the main one used, but in this research project, we're looking into deviating from just the normal modeling of temperature, specifically because we've been noticing, or there have been recent studies that have showed that leaf phenology, the sensitivity of leaf phenology to temperature has decreased as climates have been warming up. Also, the relationship between all of these drivers and leaf phenology is far from being linear. It has a different impact on it during the chilling period or during the heat accumulation period. And in this correlation matrix, you can see at the bottom row, this is our vegetation indicator, and it shows a great correlation with the minimum temperature in the day and the maximum temperature in the day from, in fact, the importance of this number of days below a specific temperature threshold in leaf phenology modeling. So let's talk a little bit about the methods that we're using in this project. So for the data, we're using satellite observations as our vegetation indicator, which is our main predictant. And so we're specifically using contiguous solar-induced fluorescence from MODIS that was also put together by my lab at Columbia. And CSIF, or contiguous solar-induced fluorescence, is a great proxy, has been shown to be a great proxy for photosynthetically absorbed radiation. And this proxy have also shown great efficiency at tracking phenology across radiation, temperature, and different water climates. We also have our climate data, which include temperature, precipitation, radiation, and moreover, to the modeling side, we're using machine learning models that include time recurrence because of, once again, the importance of the successive number of days under or above a specific temperature threshold or also precipitation threshold for leaf phenology. Specifically, we're trying to use long short-term memory model and fit that across different plant functional types or different climate regimes. And so I wanted to talk more about this, fitting this model across different climate regimes. Leaf phenology, or the pattern of that, changes drastically from different climates and plant functional types. It can sometimes be bimodal in, for example, the Sahara Desert and also around regions and around Nepal. And it can also be very straight and like a short peak around the United States. So for that, we cannot make a model that is very generalizable at first sight. So we're looking into clustering different climates. And so far, or one of the main climate classifications that have been used in the industry is the Köppen-Geiger classification. Though this classification uses broad empirical averages of climate data, and sometimes we feel like it does not reflect recent climate changes. Instead, we're trying to use data-driven processes of clustering these climate classifications, such as k-means. And what we like about this specific method is that it is very adaptable. We could be using our main vegetation indicator to specify these clusters and not only go by temperature or precipitation, and also adapt it for different time spans if we want to look at the last 5 years to specify the regions that we are interested in. So once we have our climate classifications and clustering, we can go through with the modeling. As I said, we don't have a lot of results in terms of the long-term modeling, but these are some of the initial results of the forecasting that can be done. So here we did some forecasting of the vegetation indicator in Denver, Colorado, only based on 10 years. And we have been using seasonal autogressive integrated moving average, which is a model that adds the seasonality by adding a seasonal differencing component on the ARIMA model that have been widely used in forecasting, and we achieve a decent RMSE of 0.09 for the seasonal ARIMA. As you can see in this plot, I know it's slightly hard to see, but the ground truth is in red, and we are able to get to the approximation in blue. So I wanted to talk about some of the next steps in this project. Of course, some of it would be defining the metrics, but also the thresholds of these phenological events. When can we start defining the start of season, leaf out, senescence, but also how how can we best have these metrics that can help us in model validation. And we hope to also be using the CML benchmarks, such as in iLamp. For model improvements, we are thinking about using meta-learning to be able to get a more generalizable model. So from refracting and having models that are fitted through all of these climate classifications, we want to use meta-learning, which is basically a branch of machine learning that can put together that can put together different machine learning algorithms that were already trained, and such as ensemble learning, to have a more generalizable model that can predict this interannual variability for wider regions. We also hope to try out new attention mechanisms that are more evolved than LSTM models to further look at this time occurrence importance in leaf phenology modeling. And finally, I wanted to talk about model testing. So this machine learning model will be evaluated, first of all, offline, outside of the training samples, against satellite observation to first test this sample generalization. But also we want to test it offline in the community land model for long-term simulations. And from here, the resulting carbon pools will be compared to current observations with a goal in mind would be to help address the deficiency of the CESM in terms of interannual variability of terrestrial carbon cycle, and sinks of anthropogenic CO2. And this is all for my presentation. Questions are welcome. Thank you very much.
Thank you, Aya. Yeah. Do we have questions in the room? Anyone online? Oh, Will.
So I really like your suggestion at the beginning that you're interested in capturing more of the interannual variability in phenology. And I'm curious how well the SIF measurements or other observations, remote sensing products, actually see that on the ground variability that we know is happening in the real world.
Right. That's a good question. So far, the CSIF that we're using, the spatiotemporal resolution is of 0.05 and then 8 days, and we have a span of about 40 years. So in terms of the accuracy of each specific measurement, I wouldn't be able to know a lot about that, but in terms of the larger span and capturing, at least if it's not year by year, the evolution of this variability in leaf phenology, I believe that CSIF is a great proxy to predict that. Yeah.
Cool.
Thank you.
Dave?
Really just comment, just because I'm not sure everyone here is aware, but I was coming from the LEAP project, Learning the Earth Artificial Intelligence and Physics, NSF SDC. So I just wanted to make sure everyone knows that. I don't think you said that during your presentation, maybe you did, but that, LEAP is trying to move into CSM, and this is one of the ways. And so I'm glad that I came to start making that a tighter integration.
Excellent. Well, thank you. Thank you. Okay, so we're going to move to, I need to look at the mic back. Sorry. You're still mic'd up. That's right. Sorry. It's off right now. That's the on there. Great. And so Gordon is our last speaker. He'll be telling us about testing the CLM-ML multi-layer canopy model at a walnut orchard.
Okay, well, thanks. Thanks, everybody, for this is the last talk of the day. It's always kind of interesting to be in that slot. But I'll try to make it worthwhile. Thank you for sticking around, and everybody online, too. Thank you. It's been a long day, but we had some really fun talks. And so I hope I can continue that tradition of having a fun talk, and we'll see. But this is some work I've been doing with Sean Burns and Ned Patton here, also at NCAR, in the mesoscale Okay, forget that. We just call it M cubed. But testing the multi-layer canopy model that we've been developing for CLM. I really want to call out Sean Burns. He's been leading the data analysis side of this, putting together the observational data sets, running the model, comparing the model to observation. So really, thank you. Sean's online, I think, and so thank you, Sean, for doing that. And I also want to mention longtime contributors are John Finnegan and Ian Harmon, who developed a lot of the turbulence parameterizations, the theory behind the turbulence parameterizations that go into the model. I don't want to get into I'm not going to go into any details about what the model is doing, other than to say you can see on the left schematically what it's dealing with. It's taking the volume of air from the ground to some reference height above the canopy. It's discretizing that into multiple layers, and it's calculating source sink fluxes within a layer, vertical transport between layers. The thing I really want you to think about as we go through this talk is over here on the right, this idea that the physics and physiology of the model are simpler and more consistent with theory, and also directly observable than is the CLM big leaf canopy parameterization. And then also it enables a lot of new science. Think about that as you're looking through some of these results. And then we have a series of papers that talk about the theory behind the model and the improvements that come about from the model. And this is just one example here for the Michigan Biological Station. But the data set we're working with today, or for this project, is a walnut orchard in California. Ned was the lead on that project, and Sean Burns was involved with it too. It's a walnut orchard in California. It's very homogeneous in terms of its canopy and the spacing of trees, but it was very heavily instrumented. And so there's a lot of information, vertical profiles of fluxes and scalars at different heights in the canopy. And it can also generate some very complex sort of temperature patterns, as you can see in that lower right one. This is just looking at one day from 4 o'clock in the afternoon to early evening. And you can see a really large change in the temperature gradient, temperature profiles within the canopy. Okay, so I'm going to get straight into results here. This is stuff that is sort of, I just saw this stuff on Friday, and you know, I'm pretty happy with it. We'll see what Sean and Ned think about this, but I think things are looking pretty good. This is the sensible heat flux profile. To orient you, the bottom is the magnitude of the heat flux, sensible heat flux. The vertical axis is height from above the ground. The canopy is at 10 meters, which is what the green line is, and what this little tree or plant is supposed to represent. And then what the blue is the observations, and you can see an increase in sensible heat flux as you go up to the top of the canopy, and then the constant flux layer above the canopy. This is red is the model, and I'd say that's a pretty good simulation. I'll take that any day. This is actually under medium wind conditions during the day. This is looking at, and I should say also, I forgot to say, the simulations are only for the month of May. The data was collected for April and May and early June of 2007. We're only looking for the month of May. So these results are averaged over the daytime for the month of May, medium wind conditions. This is the nighttime profile. You see a more complex pattern of sensible heat flux where the upper canopy cools down and is actually gaining heat from the atmosphere, and then you actually have a source of heat lower in the canopy. And again, the model is doing a pretty nice job of picking that up. If we go to this is the latent heat flux profile. And again, I would say we're doing a pretty good job of this. Again, you see in this is daytime, medium wind conditions. You see an increase in latent heat flux as you get higher in the canopy. This is where most of the source of transpiration is coming from. And the model is picking that up very nicely and then into the constant flux layer. You can actually argue about whether this is like a 75 watt per square meter bias. That may be large, it may not be compared to the uncertainty in the observations. But what I want to do is I want to contrast this simulation with this one over here. This is using the default, we used a SPA, stomata conductance parameterization and water use efficiency optimization. That basically says the stomata are open to maximize water use efficiency until they reach some minimum leaf water potential where they close. In this simulation, that minimum leaf water potential is minus 1.6 megapascals. This is a simulation over here where we're using a different sort of observationally based responsive stomata to leaf water potential. It has a more continuous stomata closure as the leaves become drier. And you can see that it gives you a different result, much closer to the observations. I'll show these two different functions a little bit later in the talk. But I would say this is an estimate of the uncertainty in model structural uncertainty is what I would say. Both of these are equally plausible simulations. This is looking at friction velocity. The profile friction velocity is related to the momentum flux. And again, you see constant flux above the canopy. Then as you get into the canopy, the absorption of momentum by the plant elements. And the model's doing a really great job. This is medium wind conditions during the day. It's closely related to the wind speed profile. And this is, again, the wind speed profile during the day under medium wind conditions, where you're seeing the wind really decrease sharply as you reach the top of the canopy and momentum being absorbed, and then really weak winds within the canopy. I put this one up just to contrast with the low wind conditions, where you see less of a steep gradient, less of a change of winds with height. But the model's able to capture these two different ranges of conditions. And then finally, what I want to talk about here in terms of results is the temperature profiles. This, again, medium wind conditions during the day, and we see temperatures increasing through the canopy as you get down to the ground. And the model's doing a really nice job of capturing that. We have problems at night. There's a more complex structure. Again, the canopy, upper canopy is cooling down, and then within the canopy, the temperatures are fairly constant. The model has biased warm. It picks up this upper canopy cooling, but we have warmer temperatures under the canopy, and that's related to the turbulence scheme that we use in the model. So this is something we've seen in all our papers. I would say this is like the only really noticeable thing that I could say that's like a real deficiency in the model. But what I want to switch over to and end with is just this idea of what parameters are really important to get this going. This is sort of out-of-the-box simulations, generic sort of forest canopies that we've worked with in our other papers, except for a few things. And two key parameters are VC max, the maximum rate of carboxylation for photosynthesis, and what this iota parameter, this is the marginal water use efficiency for optimization. Again, in the SPA, stomata conductance water use efficiency optimization, there's a target water use efficiency. These are the parameters we were using in the default model, sort of out of the box. But there's a lot of good data on leaf gas exchange in walnuts. You can see in this paper here, there's very high rates of photosynthesis, very high stomata conductance. We can fit the leaf photosynthesis model to this, and what we see is we get these parameters here. Much higher VC max and a much lower marginal water use efficiency for optimization. But that's gotten by fitting the model to the data. The other thing that's really important that we changed was the stomata response to leaf water potential. We're using, again, the SPA plant hydraulics in the model. What SPA does is SPA basically optimizes water use efficiency till you reach a minimum leaf water potential, and then the stomata close. That's sort of represented by this black line here. It's sort of slightly changed from what SPA does to give us a family of curves, but it's sort of like this thing here. A lot of data suggests that show that walnut closed their stomata at about negative 1.6 megapascals. So that's what this that's what this yellow line represents. This green line is that other function that I was showing that is more of a continuous response of stomata to leaf water potential. So you're seeing this gradual stomata closure. And then the blue line is another paper that has a really sharp stomata decline with leaf water potential. The blue and the green and the yellow are those two plots that I showed you earlier. I think what we're finding is that these two are sort of somewhat indistinguishable from one another in terms of the simulations, at least comparing to the data. And then the final thing that we changed was the leaf optical properties. We use the two-stream radiation, similar as in CLM, but a multi-layer version of it. Started with the same optical properties as CLM, but there was this paper that came out a few years ago based on observations of leaf optical properties, and we switched over to that. And what that's basically doing is it's making the leaves more horizontal, and they have a higher transmittance in the near infrared, but the stems have a higher reflectance. Those are the only three sets of changes we've made to the model so far. They made really big improvements to the simulation. And so I'm pretty happy with what we're doing. And I should say, by the way, I think this is being used in CLM. The next version of CLM is this paper. I think that the PPE starts from these properties too, but they seem to be working much better. Okay, so I just want to end with this slide here, which is sort of like this. The good news is it works, and I'm pretty happy about it. What we can do with it. The bad news, the reality is it's really hard to, this is standalone code. It doesn't run in CLM yet. And it doesn't run in CLM because of this. These are all the routines in CLM that are in one way or another related to calculating surface fluxes. I'm not going to go into all of this stuff. If you look at the canopy fluxes itself, there's a whole nother layer of complexity within that. What I want to leave you with is just the idea of this, like the Kraken devouring the ship. This is the problem we have. There's no clean interface to surface fluxes in CLM. You can't just pull out a surface flux mod and put in a new one because there's so many interdependencies on all these different routines. But there is a hope, I think. There's a there's a possibility. There is no possibility. There is no hope. Let's see if I could do this, get it back to slideshow. Okay, there is hope. So I think what we can do is, despite all this, what I've done in the past, I've actually put the multi-layer canopy into CLM. You can actually add it as a new routine, standalone routine. After CLM does everything it wants to do, you just call the multi-layer canopy and calculate fluxes. This is what I call a diagnostic calculation. It's in parallel with the existing flux code. It does not overwrite CLM calculations. It doesn't, more importantly, it doesn't update soil temperature and soil moisture. But it allows you to at least run the model and sort of start playing around with this. And the idea is maybe if it gets actually into CLM in this capacity as a diagnostic calculation, then maybe we could actually start talking about all these other dependencies and how to fix them. It's been implemented. I did this in CLM or CESM 2.1 a few years ago. It just needs to be ported over into the latest version of CLM to get it done. But I think there is possibly hope. There's a lot of, if we did this, there'd be a lot of sort of problems of, yes, people will be misusing this and trying to do things with it that it's not intended to do at all. But on the other hand, if it's in there, it's out there for people to use, and maybe other people can start working with and start tackling all these other sort of list of challenges that we have with it. So there's maybe hope of slaying the Kraken, we'll see. But that's all I have. And so thanks.
Well, thanks, Gordon. That was great. Oh, yes, Chris?
Yeah.
That's great. Have you tried this model with a really tall canopy, like 40 or 50 meter canopy?
No. Okay, so this is the tallest ones. We've done it at some of the Ameriflex sites. The tallest canopy there, I think, is maybe 20 meters or something like that. What I've actually always wondered about is like tropical forests, where you see, particularly when you see like the tall emergent trees, and so you have a few skinny trees sticking way above the canopy. I've always wondered what it would do with that. Yeah.
I ask because like the Wind River site itself thought to be really decoupled, the under and the overstory, and I'm just curious how it might do in a situation like that.
That would be a nice one to think about, because one of the new sciences is just that, how much is the understory sort of decoupled from the overstory? And so maybe a tall canopy like that would be a good one to look into those type of issues.
Monica?
Yeah, this relates to something that you just said as you were concluding, but it seems like if you go about certain implementation routes that you gestured towards this being subject to misuse, do you think that there's any easy ways to possibly prevent that, to open it up to the community, but maybe reduce the amount of risk with it being inadequate for certain applications?
Yeah, that's an interesting question. There's a simple answer and there's a more provocative answer, and I guess I'll go with the provocative one.
All right.
Which is, the simple answer is you shouldn't use a model if you don't understand it, but I can say that because I'm a modeler and I'm a developer, so I understand it. But what I've noticed is a lot of people CLM has been very successful, so a lot of people sort of think we know what we're doing, or believe we know what we're doing, or whatever, and use the model. And maybe they're not using it in ways that we intended to. And I don't think they really know all the subtleties about it. In this case, the key thing that's going on here is that the soil temperature calculations are highly tied to the surface flux calculations. In fact, you actually don't get the final surface flux. The canopy fluxes are After you go through the soil, you calculate canopy fluxes, you calculate soil temperature, then you do soil fluxes, but then you update everything again to correct for the changes in soil temperature. And so there's just no way you can couple this to the soil temperature routine in CLM. That's the key thing, is that you're conserving energy, but it's not conserving energy in the same sense of the full energy of the system because it's not tied to the soil temperature. So I only run the model for short periods of time where energy imbalance isn't really that important. Or so the energy imbalance doesn't really become a long-term problem. It's also decoupled from the soil moisture. These are the big scientific problems. And I worry that people who don't understand that will start running with this and start getting answers and saying either the model looks good or it looks bad and stuff like that without really understanding how it was actually coupled together. So the answer, but the way you do that is you put like big warning statements all over the place and you hope that people, look at the source code and read those warning statements.
Yeah, thank you.
Right.
Thanks, Gordon. It was a great talk. I was curious about CO2. Is it represented or discretized inside the canopy? And I asked this because I was curious about flushing and overturning of CO2 concentrations, and if you think that's important, and how it would feed back on stomatal conductance.
Yeah, the CO2 fits in, perfectly in this framework because what it is doing is for each layer in the canopy, you have a source flux, in terms of like sensible heat or transpiration, or in this case it would be the CO2 flux. And then there's vertical transport between the layers. That fits entirely in this framework. It's not in the model right now because the only source and sink fluxes I have is photosynthesis and leaf respiration. So there's no stem respiration. There's also no soil respiration, at the soil surface. But you could put it in easily into this framework.
Do you think it's a first order thing that we should get cracking on, or is it kind of secondary?
So numerically, algorithmically, it's easy. The code will work for this. You just have to put in it's another sort of scalar in it. Yeah, the exact same way you're doing temperature and water vapor, you just add CO2 to that too. It's just I don't know what those fluxes are, so I've never done it because I would have to know for each layer in the canopy what the stem respiration is. Or I'd have to have some equation for smoke respiration from the soil surface. If you have that, then you can add that easily. But those are the pieces that are missing.
Right. And all the transport's the same as the other scalars.
Yeah, so it's just another scalar. So it's just exactly the same at temperature and water vapor.
Thanks.
First, I'm curious whether you actually meant the pun, the Kraken. Because that was good with Kraken anyway. But that's not my question. My comment was related to Chris and Ryan. I guess it's like exposing the number of things you could do if you had this working. I was curious about snow underneath the canopy and how, if you started representing this full multi-layer canopy correctly, you might actually have a better representation of, the melting or retention of snow underneath the forest canopy.
Yeah, no, that's a great question. That's another one. And then the caveats, the limitations is there's no snow in this model at all. That's fine with me because I'm looking for when the vegetation is physiologically active. That's mostly going to be, in the growing season, around here, July and August and so forth. So there's an interception of water in throughfall because you need that for the evapotranspiration, but there is no snow in the canopy. So that would be another one of these limitations. Yeah, you can put it in CLM and you can run it, but by the time you get to the wintertime, there's no snow around. So you're gonna get crazy results. So that would be one of those things that has to be added. But I suspect that's what you'd actually begin to see, is you might begin to see sort of different behavior of a snowpack under the canopy in a multi-layer case than you would in the CLM big leaf canopy.
Sean?
So there's always a desire for a simpler model. Is there anything that you can take from this to help maybe improve some of the parameterizations of the stability and like the canopy wind speed, for example, is right now just the friction velocity, which is really weird to me. But could you learn anything from this that you could then apply to the big leaf model, which will probably have probably going to have a lifetime that's.
So Sean raised a really interesting point. The parameterization for turbulence within CLM, basically, the wind speed in the canopy is friction velocity. That goes back to the 1986 version of Bob Dickinson's Biosphere Atmosphere Transfer Scheme. But, which is, yeah, it's like a crazy thing, like there's not much of a physical basis for that. But if you look at this result, the friction velocity is point like 6 or so is what it is at the top of the canopy. The wind speed, the wind speeds within the canopy are say like 0.5 meter per second or something like that. You know, so maybe this idea that the friction velocity is the wind speed isn't that crazy of an idea. It doesn't have much physical basis to it, but it maybe is an approximation that works. So, no, you know, Sean, I hate, you know, I'll go back to, it's this statement here. Yeah, it's just, this is simpler. Yeah, I can write these equations on a whiteboard. And they're actually they're in a paper. You know, somebody has to go through the CLM tech note and figure, yeah, there are like 30 pages of stuff going on in terms of surface fluxes in CLM. And there's all this stuff of like, well, this is what we're trying to do and it doesn't quite work, so we're gonna make this change to it. And that's what I mean by these ad hoc parameterizations. So, you know, the answer to this is no, because this is the simplification. This is, in my mind, this is a simpler version of the model. It's more, physically it's more simple. It's more complex because now you're modeling this airspace. And as your forest grows, that airspace changes, you know, over time. And so how do you deal with things like that? But in terms of its physics and the parameterizations, I think it's much simpler than what's in CLM.
Chris, one more comment. It seems like it's really improved the ball heat storage issue you raised earlier and also the canopy interception issue. Wouldn't it be easier and more correct to do canopy interception this way?
Yeah, it's interesting. Thanks for bringing up the heat storage because this model has, there are 3 different sort of versions of heat storage. One is the leaf heat capacity itself, part of the leaf energy budget. This model has that in it, but let's face it, that's a really small term. The other is the storage of air or storage of heat and moisture in the airspace itself. So there is a storage of sensible and latent heat flux in the canopy. And then the final term is, you know, what Sean put in, the biomass heat storage, the woody biomass. That's not in the model yet. At the chat site, there is data on that for each of those 3 terms. And we're getting the storage in the canopy air is that's about 20 to 25 watts per square meter. We're nailing that pretty nicely. The leaf storage is really small. What we're missing is about still like 25 watts or so square meter for the biomass heat storage. Yeah, we haven't put that into the model yet. It's possible that we could take the ideas that Sean put into the CLM and sort of put that into this framework too, but we just haven't gotten around to that yet.
Oh, well, I think we can kind of transition from grilling Gordon to maybe grilling Gordon, but also having a broader conversation. And I guess I'm struck, Jyoti's talked about, you know, work that Donica did during her dissertation that now she's updating for CLM 5. You have citations of your own work that go back almost a decade now. The chat site is like 12 years old. And like, I guess I'm kind of constantly struck in my own work, like the first Mimics paper was almost 10 years ago. Like, even for those of us that are here to do model development, it's still really hard. It takes a really long time. And I guess I'm curious, like, which makes, I think, the work that graduate students and postdocs do even more impressive. It's like, it's taken Gordon 10 years to get the multi-layer canopy in, and it still isn't really game time. And I guess I'm just, yeah, like, how do we, maybe there's not a way to make that better. It's like science is hard, development's hard. I guess there's not really a question there, but I'm just struck that like, this is hard stuff. Like, and you're really good at it.
Yeah, I should just put that, I did want to say one thing. Yes, the first publication was 2014. That was when Matt Williams came over here for sabbatical. And that's what started this whole thing, because I'd always seen the SPA model. I never knew how to I knew about it. I never knew how to code it up. Matt actually took the time to sort of pull it out, put it in a framework. We could put it into CLM, and that's what actually sort of led to all this stuff. And then the SPA model is multi-layer in terms of radiative transfer, but that it doesn't do the turbulence within the canopy. So that then led to work with Ned and M-Cubed and John Finnegan from CSIRO. You know, what I'd say to answer to your question, Will, is it really unfortunately comes down to funding. You know, this is just sort of a side project for me that I do when I have time. If you really want to get into it, what actually originally funded this project was something called CMAP, climate modeling, multi-scale modeling across, I can't even remember the acronym, but it was something that Dave Randall, Scott Denning, and others were leading at CSU. And CAR had some funding on it, and they were looking for collaborations between CGD and M-Cubed. And so that's what started this whole thing, you know, working with Ned. So unfortunately, it sort of comes down to like people and time and money and stuff like that.
Can I comment on that?
Yeah.
Well, actually, I want to first start by commenting on something completely different, which is I just was realizing that it might be fun to go for a beer after this. So for anyone who wants to go. So I know that actually the dinner's tomorrow night, but I at least am happy to go down to the Southern Sun so we can have the upstairs experience of having a beer and then have the downstairs experience tomorrow. So if anyone wants to go, think about it over the next 30 minutes and anyone wants to go, I'm happy to go down. I can give a few people a ride. But to get back to that question, you know, I think we should do the exercise, which I don't think we've ever done, really is try to put a number, like how many FTE for how many years would it take to rewrite CLM to allow us to like be faster on model development. And I think we should just have that number in our back pocket so that we can actually talk to people in power with influence, like with real numbers. And you know, I am getting some sense that NSF is understanding at a very low level the scale of the problem that CSM is under and CLM being within it, and that they may be willing to devote resources to it. So if we had that number, we could start pushing that out there and see if anything catches. Because, and I'm presuming that it's software engineering, which is the challenge. I think it's like combined software engineering science, but I think most of these things we're hitting up against the software barrier before we're coming up against the scientific barriers. If people feel differently, that would also be important to know that too.
Well, I guess this is in response to Dave.
Yeah, a little bit. So I think that with respect to kind of allocating resources or figuring out what allocation of resources would need to be in order to speed up development of model components is really important. But I think there's other elements of modeling practice that also need to be considered as you're seeking to improve development. Not just speed. So I think what Gordon brought up at the end of his presentation, we've been talking about in some of the other working groups, there's this certain inaccessibility in terms of understanding the model. And largely that's a part of kind of what the culture of model development has been, where we write these papers, we submit them to BAMs, right? They give an overview of what we've included in the model. We provide some minimal justification for what that inclusion is. But there's not really a lot of transparency around why certain development decisions are made, what the purpose of that decision is in terms of how it's going to improve the model's adequacy and stuff. So I would just as an outsider think that that's kind of an additional layer to the conversation of how can we do model practice better and where resources need to be allocated, because there's not currently a place for that in practice. And so it can't just necessarily be handed over like, oh, developers, you have to take on this additional kind of burden by documenting in this kind of systematic way what you're doing in your development decisions so that people can understand whether the model's adequate or inadequate for various applications. I think that you need to have like facilitators or translators that are working at the interface of developers and users. And so thinking about how to also include that as you're thinking about reworking kind of the business aspects, if you will, of kind of model development, that also should be a piece of the conversation. I just want to put that out there as an additional point of consideration in thinking about the future of development.
I guess one of the things that came up when Gordon said, I would like to be able to do the stuff which ties into the soil physics and everything else, but it's too hard. That seems like obviously, it's not, you don't choose not to do it. You just do it because it's a barrier. And it would be good if we could work out what the barriers were, like to being able to do those sort of developments. You know,
why is that barrier there? Is it just inherently because it's historical and it's entrenched in the way the model was developed, so it's got all these pieces everywhere that have to connect? Or is it just we haven't had the resources to be able to fix it?
It's a coding infrastructure problem. You know, there's parts of the soil temperature and the soil fluxes actually require pieces of the canopy fluxes, and then those pieces have to fit together. So you see hardwired things in the soil fluxes that entirely depend on how you parameterize, say, long wave radiative loss from the canopy.
Right.
And that's hard. And so the thing is, it's the way it was, CLM is like close to 25 years old in terms of the original coding. That is the original coding. Yeah, that's still in there.
That's sort of monolithic.
And it worked at the time, and it was fine at the time. But now, as we want to add more things to it and add more sort of complexity or even change things, the code wasn't ever designed to do that.
Right. It'd be kind of nice, as you were saying, if you had different kernels you could just put in, you know, like just be able to say, we're going to use this particular radiation scheme or this particular like canopy turbulence scheme. That'd be really nice.
Or even, you know, the nice thing, I didn't mention, the nice thing about the multi-layer canopy is it generalizes from one layer to n number of layers. And so could you have something that has that kind of adaptability to it, but then everything has to be all self-consistent again. You know, you can't, it doesn't reduce to the CLM big leaf canopy because the CLM big leaf canopy is so convoluted in terms of how it's distributed across all those multiple routines.
Right.
But you could try to do something like that.
And so the energy balance issue that you brought up, is that something you could solve, or is it inherently a problem within the way the scheme is set up?
It's inherently, ultimately, I have to have my own soil temperature code to get this to run,
right,
because I do need to conserve energy. So I have my own soil temperature routine, because there's just no way you could use the CLM one. You can't pull that out and use it. You know, also the CLM soil temperature has the urban model built into it too.
right.
So you can't just sort of replace one soil temperature scheme with another, because then you lose the whole urban model. So there's all these kind of things built into it. These routines do many things in addition to what they were originally intended to do. And that's sort of been, you know, this is the technical debt issue that has been built up over years.
Right. Yeah, it seems to be there's individuals who have knowledge of these things, but we don't actually have it explicitly in one place. Like we have in the tech note sort of, but not really, you know.
Well, you know, there is one person who might understand all this stuff. Yeah, but Keith.
Yeah.
But we got to work fast.
Half time, right? Well, I think we're at 4:30 now.
Yeah.
Yeah. Do you want to call it for the night?
Sure.
Yeah.
Yeah, so tomorrow we'll start off at 8:30 again, and it's packed with all kinds of good stuff, including we're going to lead off with fates. We haven't heard a lot about fates yet, so I'm excited to see that discussion. And then the seminar is at 11, so with a bunch of other talks. So thanks to all the speakers today, and looking forward to hearing more.
So can I quick just get, does anybody want to go get a beer? And if no one wants to, that's totally fine if you have plans already. But if everyone want to raise their hands, or everyone's like, I'm ready to be done.